Hello everyone and welcome to the new series, Aircraft, Instruments and Systems. Now, this series talks about aircraft instrumentation, different devices on board, indicators, the different systems when it comes to pneumatic, hydraulic systems, electrical, computerized systems, monitoring, all of these stuff, okay, all of these aspects. And as a disclaimer that you're gonna see in the next page, this series is not meant ever to replace the actual manual for aircraft when it comes to maintenance or ground operations or air operations. It's not a replacement, it's just for information, okay? It's an informative series on how things work on the aircraft, how different systems when it comes to the mechanical aspects, the mechanical part, the electrical, electronic, different sensors, different devices, different the alarm system, the indicators, etc. Let's start at first with the purpose and classification of aircraft systems. Okay, as a purpose of aircraft systems exist to support, to control, to monitor, and to protect the aircraft and its occupants, so that flight can be conducted safely, efficiently. An example of efficiency is the reduction of fuel consumption and reducing the strain on the engines or the stress on the engines, reducing drag, etc. And reliably under all operating conditions, such as under rain, icing, good weather. Their main purposes can be summarized as follows: enable safe flight, which provide pilots with accurate information about the aircraft attitude, which is the bank, the roll, okay, whether it is banked to the right and how many degrees or to the left. Altitude is the height from the sea level, okay, or from the reference point of the airport. Speed, which is airspeed, vertical speed, vertical descent or ascent, and direction or heading. Okay, in order to allow precise control, also another, which goes hand in hand with the first sentence, is allowing precise control of the aircraft during different flight phases, and also preempt the early detection of abnormal or dangerous conditions in order to repair the fault or to troubleshoot the problem before it becomes more dangerous, okay? Like at times, you have problems that require an immediate landing, emergency landing. Okay, so here you have the avionics system, which is the electronic system, which is the gear system, okay, the landing instruments, the hydraulic system, which controls the different parts of the wings, okay, the different, wing controllers, such as the aileron, the elevators, etc. The fuel system and monitoring of the fuel electrical system. You have environmental system, ECS, which is responsible for the air conditioning and other things. Anti-ice and de-ice systems to prevent the accumulation of ice on the fuselage, which can decay the lift and other aerodynamic properties during the flight. And auxiliary power unit, also emergency systems. Another purpose is to support aircraft operation, such as supply power for the aircraft, whether electrical, hydraulic, to move the controls. Controls again are the different parts, the different dynamic or moving parts of the wings, such as the rudder, the elevators at the tail section, and the ailerons, which allow the aircraft to roll, to bank to one direction, and pneumatic, which is responsible for the gears and the braking system, okay, on the ground during landing or during emergency abortion of the takeoff, okay, to operate the equipment. Control the engines, such as the throttle and the fuel system, okay, adjusting the fuel flow via the throttles to control the power of the engines and propulsion systems, manage environmental conditions inside the aircraft using by controlling the different air conditioning systems. Second, actually that would be the fourth because we have the previous page. Enhance performance and efficiency. Okay, so optimizing fuel usage and reduce the waste of fuel and engine performance, meaning trying to maintain the maximum, the most optimal performance of the engine. Improve aerodynamic efficiency via the flaps, the slats, the spoilers. Okay, now the flaps are the rear part of the wing, which is dropped during takeoff and during landing, okay, which in a way help decelerate the aircraft during descent, and also using the airflow for the lift to reduce the descent rate of the aircraft, but at the same time to decelerate it. Okay, this is during landing. Now during takeoff, it is used to maximize the lift to lift off, to help lift off the plane during takeoff. Okay, and the slats are the forward part, you have the flaps are in the rear end and at the trailing edge of the wings, but the slats are at the front leading edge. Okay, so flaps are at the trailing edge and slats are at the leading edge of the wing. They both are used, they are dropped together to maximize the lift of the airplane. And spoilers or air brakes to increase the drag in order to decrease the speed, the airspeed of the aircraft. Okay, so they work to reduce pilot workload and errors through automation. Ensure passenger and crew comfort, like cabin pressurization and air conditioning. Pressurization is needed because as you go up in the altitude, the density of the air decreases. Okay, so a human cannot handle breathing or living at high altitudes due to low air pressure. That's why the pressurization of the aircraft is required to imitate the same conditions on the ground at level 0, at sea level, so to speak. Okay, or acceptable condition of air pressure when you are on the ground, not on the air, miles away, miles up high. Okay, above the ground. Reduce pilot workload and errors through automation. Okay, ensure passenger and crew comfort, cabin pressurization and air conditioning to mild the temperature, the living temperature within the aircraft. Lighting, ventilation, and noise reduction. Also provide noise reduction by controlling the engines as well. Okay, and provide protection and emergency capability, fire detection and suppression, ice and rain protection, because ice can lead to an aerodynamic stall by increasing drag and reducing the lift on the wings. And finally, warning, alerting, and monitoring systems. Okay, to monitor, to warn. These are the indication systems. Okay, along with the instruments to indicate if there's a fault, if there's a problem, like an overheat of an engine, in order to mitigate or to jump right at the problem and solve it before it can escalate to something even more dangerous within the aircraft. And monitoring systems, monitoring the performance, monitoring via different sensors, the temperature, the oil pressure, the engine rotation like N1, N2, etc. Second, classification of aircraft systems. Okay, you have at first classification by function. So, for example, flight control systems. These systems control the motion and attitude or the bankroll of the aircraft. Also, the elevation and the noise up, noise down, pitch up, pitch down motions, okay, are controlled, for example, by the elevators. The rudder actually, along with the ailerons, control moving, turning right and turning left. The ailerons alone, they control the roll. Okay, so when the aircraft roll, or it banks at a specific angle in order to turn and to change its heading, okay, what happens is that a part which is a component of the weight becomes distributed, or it becomes divided into two components. Okay, so at first it was vertical. Now, when the aircraft turns, a component of the weight becomes horizontal, another component like vertical in reference of the aircraft wing, okay, and you have the weight which is like the horizontal and vertical component added together. The weight, it is vertical in reference to the ground, not to the aircraft. So the horizontal component is what moves the airplane to the right or to the left. This is how it skids to the right or to the left, or it turns to the right and to the left. Okay, now the elevator, what it does is pitching up and down the airplane. So when it moves upward, okay, so the air pushes the elevator, pushes the tail via the elevator when the elevator moves upward, which makes the tail go down and the nose pitches up. Now, if the elevator goes down, the air would push it upward. So when the tail goes up, the nose of the aircraft goes down. This is how it pitches down. Okay, and it changes the direction. So the first motion, it would be climbing if there's enough airflow. The second motion, which is the nose down, it would be diving, okay, and decreasing in altitude. Okay, so the primary controls, ailerons, these are the ailerons, the orange ones here. Elevator, that's the elevator. The rudder, which is the moving part of the vertical stabilizer here, okay, that turns or moves the aircraft right and left. It turns the aircraft right and left along with the ailerons. Now, the rudder is used during landing at times when you have a crosswind that pushes or throws the aircraft to one side and, throw it off track from its alignment with the runway. So the pilot would correct this heading, okay? It would correct the alignment of the nose of the aircraft with the runway by applying a right or left rudder so that it would remain aligned to the runway during landing, but also during takeoff, because if you have a crosswind, it would have the tendency to move the aircraft sideways, which is dangerous, okay? So the pilot would correct the heading, the direction of the nose by applying rudders so that it would remain on the center line of the runway all the way to the takeoff point. Secondary controls are the flaps, which are the gray parts here. They are lowered down in order to, again, increase the lift during takeoff and during landing. The slats are the front parts of the flaps, okay? The flaps are at the trailing edge of the wings, but the slats are at the leading edge. So they go down also, which along with the flaps, they maximize the lift, but they increase drag, okay? So usually they are used during takeoff and landing. You have the spoilers, which are the air brakes, parts of the airplane that goes up. Not in every aircraft they are available necessarily, okay, especially in heavy Boeing 737, 747, okay, in these types of aircraft it is needed to reduce the airspeed and by increasing the drag, okay, that would be the spoilers, another name for the air brake. And the trim is a small part of the different controls, okay, which is applied, you see, because if we are flying, the weight of the airplane would be going on one side all the time, okay? It's never the same weight. So you would feel the tendency to keep pushing up or pushing down. In order to reduce that, we apply a trim, which is a small part of, let's say, the elevator, so that instead of keep on pushing the elevator to pitch up the airplane in order to remain in a leveled flight. Okay, we apply the trim so that a part of the wing would go down. Okay, and that would be, it would stabilize the flight, so to speak, instead of us always applying the controls. Now you have the control mechanisms. Okay, now the control mechanisms, you have different types of controls. You have the mechanical, where the power of the pilot himself would be applied and would be needed in order to move the controls. That would be in small airplanes such as, the Cessna, for example. You would be applying by your own strength in order to change the rudder, or to pitch up or down, or to move or to roll the airplane. You have the hydraulic, which assists. So you would apply the force and the hydraulic system would move the ailerons and the rudder. That would be in larger airplanes where you wouldn't have enough force yourself, enough strength to move these controls. They would be so much heavier and they would have much more strain on your own muscles. You wouldn't have the ability to move these controls. They would be heavy, especially when you're flying a very heavy airplane. Okay, and finally, the most advanced system of all is the fly-by-wire, where you apply a command, and that command on the yoke, for example, which is the steering wheel, like the steering wheel in an aircraft, and that command would be read by a computer. The computer itself would go into an actuator and generate the motion. Okay, it would be like powered. It would read your motion and then amplify it and give the command to a generator. Okay, give the command, like it would be a generator or an alternator rather, that would move, that would rotate the rudder or the levels or the ailerons. Okay, this is what fly-by-wire again means. It would read, you have a controller that would read your input and then plug it into an actuator, which is it will convert it into an amplified signal that will actually control. So it would be the strength of that actuator, like a motor, that will rotate the different parts of the different controls of the wings. Classification by function: instrument and indicating systems. Okay, so their main purpose is to provide real-time information to pilots and crew concerning what? Concerning altitude, airspeed, turn or roll, how much is the aircraft banked, and also this would be the attitude. So if it's rolling, banking, or if it's horizontal, okay? But also if it is leveled, meaning if it is nosed up or nose down, if you're pitching up or pitching down, because especially during the night you cannot see the horizon, so you won't have any reference to your flight except for the instruments. That's why they need to be very reliable. Now, what are these instruments? You have PITOT-STATIC instruments such as the airspeed indicator, or ASI, that measures the airspeed, because the speed of the airplane is actually the airspeed, the speed of the air moving through it. Okay, so this is how you measure the speed. Unlike when you have a car, it's on the ground, you measure the speed of the car based on the rotation of the wheel. Okay, here your reference is the air. Now, another is the altimeter, which would define the altitude, okay, the height from a specific reference point of the aircraft, and the VSI, or the vertical speed indicator. Now, the vertical speed indicator is, along with actually the attitude indicator, would define for you, would show you whether the aircraft is climbing or diving. Okay, because when we talk about the attitude indicator, which is part of the gyroscopic instruments, okay, along with the heading and the turn coordinator. So when the aircraft is turning, for example, the turn coordinator would give you an angle here, okay, now, and it would show up also on the attitude indicator. Now, if it is pitched up, so the yellow dot here would be in the blue zone. Pitched up meaning the nose of the aircraft is up. So it is forming an angle, positive angle, in reference to the ground or to the horizon. It would be like this. Okay? Now, if it's pitched up, it doesn't necessarily mean that it is climbing, because there might not be enough airflow for it to climb. Climbing meaning it means that it's increasing altitude. Okay? So, in order to verify it, we need to look at the VSI, the vertical speed indicator, should be showing a positive rate. This is what we call it. Okay, a positive value, meaning the needle is upward. So it's showing a positive vertical speed. And this is when you can confirm it is climbing, because it can be nose up, but yet descending during a stall. Or it can be nose up, but during a level flight, which is, by the way, almost during the landing. At times you would have it like next near to the runway in a level to flight. It is flying at the same level, not descending much when it's about to land, but yet the nose is up in order to increase the drag and reduce the speed of the airplane so that it won't hit hard on the runway. Okay? And at the same time, by the way, it would be increasing lift, so to reduce the descent rate during the landing. Now, again, so the attitude along with the VSI and the altimeter would be increasing in value. This would show you that the aircraft is indeed climbing, not diving. Now, during a dive, the nose would be down and the VSI would indicate a negative value, so the needle would be going downward, or it would be indicating a negative value if you have a digital VSI. That would be in the ECAS, okay, engine indication and a computerized system. Now, you have the engine instruments. Okay, what are the engine instruments? The RPM or tachometer, which would give you how many revolutions per minute the engine or the motor is rotating, just like the RPM of a car. Okay, especially you would see that in turboprop aircrafts. It would show you the revolution or the speed of rotation of the blades of the motor of the turboprop engine per minute. Another important indicator is the EGT. The EGT is the exhaust gas temperature. Okay, so it would show you if it is overheating or if there's a problem through by monitoring the EGT. Okay, to check if it is within the nominal values or if there's something wrong. Another important indicator, very important, is the oil pressure. You see, when there's a problem with the engine, okay, the oil pressure would drop, usually. When there's a problem like a rollback or the engine is shutting down, okay, or you're having like a problem, what we call engine flame out, due to running out of fuel or due to a specific shutdown, like the blades have been broken, it's no longer turning properly, you would have an oil pressure problem. Okay, so these are the different warning and annunciation systems, which are very important to observe and understand the status and the performance of the aircraft during the flight. Power plant and engine systems, okay, they are required to ensure safe and efficient engine operation. You have the fuel system, the ignition system, engine control and monitoring, lubrication and cooling systems. So here, if you look at a jet engine, as we're seeing here, you have the air intake, which is like a giant fan that sucks the air to the inside. That would be the first stage, okay, from the external air. Now, then the second stage is the low pressure compressor. That would be fans that would compress the air so that it would become more dense, okay, and thicker on the inside of the engine. Another stage would be a high pressure compressor, also sets of fans. Some of them are stators, which are which means they are static fans, static blades, and SAR are rotor, which they turn and compress the air against the static fans. Okay, and they have like the cavities of the air between the blades would be even more tighter to increase enormously the pressure of the air on the inside. So the temperature of the air would drop enormously. Then you have a mixture of this air with the fuel system and an ignition. Then after it is ignited, and with this very high enormous pressure, it would explode, and the combustion would generate the exhaust, okay, a hot air rushing rushing with a very high speed and screaming outside of the engine. That would create the motion forward of the airplane. And when it moves forward with a specific speed, the air flowing against the wings would create lift. Okay, so this is how it works. So the exhausted hot air would be thrown out of the engine, going out with a very high velocity, and this is what will push the aircraft forward. This is, by the way, called momentum. Okay, so the mass of the aircraft times the velocity of the aircraft moving forward would be equal to the mass of the air being exhausted from the engine times the velocity of the air moving outwardly. Now, the air doesn't have that large mass, that large weight. So how to compensate in order to force the aircraft to move forward? You would have the air going out at a high speed due to that type of combustion after being mixed with the fuel. And this is what will create the forward motion, the forward force, along with the air flowing around the wings and the different fuselage sections. This is what will create the lift within the air. For electrical systems, which have the purpose of generating and storing and distributing electrical power, you have mainly the parts that play a role in this electrical system are the generators and the alternators. Now, they are slightly different. We'll explain that afterwards. You have the batteries to store the power. You have the APU, auxiliary power unit, by which you can restart the engine during mid-flight if there's a problem. You have the bus bar and circuit protection, okay, in order to protect against electrical surges, to prevent incendiary events, okay, and fire events or short circuits. Lightning, also lightning protection, and avionics power. Avionics are the different electronic systems for measurement and monitoring. Now, if you look at this graph to the right, you have the different circuit. You have at first the different circuit breakers. Circuit breakers in order to protect against an electrical surge, and these circuit breakers are displayed between the primary bus and avionics bus. Now, the primary bus is connected to different controls, and then to the right it's connected to different monitoring systems, okay, like fuel quantity indicators, flashing beacon, pilot heat, different switches and different indicators for different systems of the airplane. You have, for instance, here indicator of the battery power, the alternator that generates power here, okay, connected to the circuit breaker, and circuit breaker pull off, push to reset, like this one. You have the starter or the igniter, battery contactor, okay, that can switch automatically to the battery in case there's a problem on board, oil pressure switch, okay, the battery on, battery off system, etc. Okay, we're gonna dive deeper afterwards to understand the different parts of the electrical system. 5. Hydraulic and pneumatic systems. Okay, so you have high force power transmission. For that high force power transmission, it is required to have the hydraulic system so that it can relay the power, like the control from the pilot to, or like the command from the pilot all the way to the different controls, different parts of the airplane, such as the flaps, the ailerons, the rudder, the elevators, etc. Okay, you have hydraulic pumps, actuators, reservoirs, pneumatic and bleed air systems. 6. ECS, or environmental control system. It controls the internal aircraft environment. It is responsible for cabin pressurization to make sure that the pressure of the cabin is comfortable for the different, the crew, the flight attendants, and the different people that are on board. You have the air conditioning system through the gasper, the ventilation system, etc. 7. Landing gear and braking system. It supports the aircraft during ground operations. Also responsible for landing gear extension and retraction. Retraction during takeoff, of course. Braking and anti-skid systems to prevent the airplane from sliding on the runway. Steering and shock absorption. You have a damper also to absorb the shock during landing, during touchdown. Also, you have protection and safety systems, detect and mitigate hazards, okay, fire detection and extinguishing system, especially within the engine, okay, when you have a problem with the engine, it's on fire, you have an extinguishing system that will turn off the engine. Of course, when that happens, there's no way to turn it back on, okay. And finally, you have ice and rain protection, which are the de-icing system, like the pneumatic, the de-icing boats that inflate and deflate in order to break the ice forming on the wings, on the front edge, the leading edge. And also you have overheat and smoke detection. So looking to the right illustration here, you have engine fire overheat detection system, the sensors that are within the engine. APU, fire overheat detection system. APU again is the auxiliary power unit that is needed to restart the engine, whether on the ground or during flight if there's a problem, if they for any reason flamed out. And left and right pylon thermal switches, okay, aft equipment area thermal switches. You have rear and rear thermal switches, different thermal detectors, forward cabin, underfloor thermal switches, etc. These switches are required in order to turn off, for example, the power that's feeding, for example, the lavatory. The breaker would open up in case there was a problem of a fire or a short circuit or a kind of overheating. It will pop up in order to break, create an open circuit and prevent a fire if there was a surge, an electrical surge, and if the current increased to a specific level above the level tolerated by the circuit breaker would pop, because that would be an indication of something problematic going on, such as a short circuit, for example, or an electrical surge or overcurrent consumption, which can heat up the cables and cause a fire. Okay, this is another illustration for the different hydraulic systems. You have left and right engine switches. You have, for the fire here, you have fire extinguishing, MAU1, okay, left fire, right fire extinguishing agent bottle, okay, that are placed near the engines, the cartridges. Okay, a little bit more complex system. I won't go into detail. The power source, the fuel control shut off valve, etc. Okay, to control the fuel, to shut off the fuel, to display the fire alarm. Okay, you have APU fire extension, etc. Yeah, that would be the extinguishing or a fire protection system within the aircraft. This is its architecture. Avionics and navigation systems. 9. Okay, their main role is to enable communication with the ground, to get vectors, to get different, the guidance in order to land, which runway, to get different information and assistance in case of an emergency, etc. Communication is very important. And for the navigation meaning understand where you are on the map, what are the different, what is the characteristic of the terrain that you're gonna land over, where is it located, and where you are, like your own heading in respect of that terrain. Okay, but also your attitude, your altitude, all of that is part of the navigation. Okay, mainly the navigation refers to your own position on the map. Okay, so you have the navigation systems are the VOR, very high frequency open range radio, okay, which is like a checkpoint that you can cross, and it's not as accurate, but you cross that checkpoint as a reference that you're heading towards the airport, and then you locate the airport visually, okay, usually via the VFR if the airport if the airport or the runway is not equipped with the ILS. Now the ILS, or the instrument landing system, is made of two beams, like it's projecting two beams. One is vertical and the other is horizontal. Now the vertical beam is called the localizer. The localizer is necessary so that you can align on the runway. So you would see like a vertical line on your instrument. When it's moving to the right, you need to move to the right to align with the runway. When it's moving to the left, you need to move to the left. It needs to be centered on the display. The glide slope, the other beam, is the horizontal beam, which is the glide slope. Glide slope is like a how can I say it? A virtual plane. It's not virtual, like it's a projected plane, projected communication beam that once you track it, okay, on its center it has the maximum power, okay, you need to be going down that center. Now if you go below it, it goes up on the indicator. It means that you need to climb to intercept it. If it goes down, it means that you're way above the airport, you need to go down. Okay, so this horizontal line needs to be at the center also of the attitude indicator usually. And as for the glide slope, the glide slope needs to be, which is this horizontal line, needs to be at the center of the attitude indicator, and the localizer also at the center. They need to cross at the center, which means for the localizer, you're aligned at the runway. For the glide slope, you are descending at the correct descent rate, so that you can be neither above the runway nor below the runway. Okay, you are perfectly aligned and you're gonna land perfectly on the runway, okay, at the right position. And finally you have the GPS, which can locate you on the map. You can understand where you are. Okay, you have the FMS, flight management systems. Okay, then classification by power source. So you have the mechanical systems, direct mechanical linkages, cables, rods, pulleys that are common in light aircraft. Here we're talking about the classification of different aircraft. Okay, so classification by power source. You have the mechanical systems, direct mechanical linkage, cables, rods, and pulleys for light aircraft. Electrical systems, you have sensors, motors, avionics. These are for the instruments, okay, increasingly dominant in modern aircraft. Even the control is electrical, which is called, again, fly-by-wire. And the hydraulic systems, you have high force systems such as gear, brakes, and large control surfaces. okay, controlled by hydraulic power. Pneumatic systems, you have the bleed air for pressurization and anti-icing, the de-icing boots. Classification by level of integration, independent systems, standalone instruments or subsystems, okay, how they are integrated. Or integrated systems, meaning you have centralized monitoring, EFIS, ACAS, engine indicator and crew alert system, and ECAM, okay, that share data via aircraft data buses. Okay, what does that mean? For the independent systems, you would have one instrument for the attitude indication, another instrument placed right next to it, especially in the small airplanes, okay, for the altitude, one for the attitude again, one for the airspeed. They are separated. Meanwhile, in the integrated system, especially in large aircraft, you would have, for example, the ECAS, which is the engine indication and crew alert system. On that display, you'd have multiple displays concerning the engine, whether the oil temperature, oil pressure, EGT, exhaust gas temperature, the N1 and 2 rotation. Okay, all of that integrated in one system. In one, of course, you have different sensors, but the display is on one display, on one single screen. That's the difference. Okay, and ECAM. Okay, so they all share data via aircraft data buses. Now, EFIS, by the way, is Electronic Flight Instrument System, and ECAM is the Electronic Centralized Aircraft Monitor. Okay, so the ECAM is the Electronic Centralized Aircraft Monitor, which will have in the middle the attitude indicator, but along with it to the left you'd have the altimeter, okay, the measurement of the altitude. To the right you would have, to the left you'd have the ASI, okay, the airspeed indicator. To the right you would have the altimeter that would display your altitude, along with also another display, which is a vertical display for the VSI or the vertical speed indicator. And within that same instrument, you'd also have what? The directional heading, okay, the heading. You would have, when you are using an ILS system, instrument landing system, both the localizer and the glide slope that should be centered to the middle during the landing. So different, also the third coordinator would be displayed on the ECAM. So different displays have been integrated in large aircraft on one monitor so that you can check, you can have a situational awareness over where you are in flight and how you're heading and how is your performance when it comes to the ECAS, when you monitor the ECAS, okay? And also the ECAM to check your altitude, to check your airspeed, even the different warnings such as the stall and other things, other behaviors of the engines are indicated on these integrated screens. That's why we call them integrated systems. You'd have one computer display like integrating different functionalities, different instruments at the same time. Meanwhile, for the independent systems, you would have different instruments that are stand-alone. They are independent. You have the airspeed indicator alone on one part. You have the altitude indicator also stand-alone and separated, etc. Here in this display, we see the pneumatic system, which is driven by hydraulics from the motors, the engines of the airplane, okay, that transmit the power via, again, hydraulics to apply pressure on both, on the gear, okay, on both wheel parts during the landing, during, to break them, okay, so they are also during retraction of the landing gear or pulling down of the landing gear. Retraction, of course, is right after takeoff. So this is like a small animation. You see the bleed, the overheat sensors here. You see also the APU is involved, okay, for cargo heat. Wing anti-ice, because the anti-ice, the de-icing system is driven by the pneumatics, especially in the Boeing 737 and, bigger aircrafts. Why? Because you have the de-icing boots need to be inflated and deflated in order to keep breaking the ice formation on the wings, which is like the inflation and the deflation are driven by the power of the engines, the motors, okay, as we see here. You also have the icing systems on the engines themselves that are also driven by the same power, okay, of the hydraulics. Usually, actually, the anti-icing on the engines is through the heat of the oil engine. This is what breaks down the ice. Okay, so it's a more complex system. You have the ground pneumatic. Also, it is connected to the same hydraulics, okay, for cargo heat. You have the wing anti-ice, both on the right wing and the left wing. So this is how it basically works. And of course, all the sensors that are responsible for measurement and the instruments within the cockpit for monitoring the hydraulics and the temperature, okay, and whether to check if the icing system is working or not, okay, all the instruments that go along with this system, whether for monitoring or for control. Relationship between instruments and aircraft performance. Aircraft performance is directly monitored and managed through a variety of flight and engine instruments. Okay, so these instruments have the responsibility of data collection, of measurement, and you have the indicators within the cockpit are to display these measurements to indicate whether there's a problem or alarm. Okay, so these instruments provide the pilot with real-time data that reflects how the aircraft is responding to different controls, to control inputs, environmental conditions, and system limitations. Okay, among these instruments, of course, you have the altitude indicator and the VSI, which would indicate for us whether if the aircraft is climbing or diving. Okay, VSI stands for vertical speed indicator. Okay, if it is a positive speed, it means that the airplane is climbing. If it's negative, it means it would be diving, along with the altimeter that will indicate a gradual decrease in altitude during descent or an increase during climb and during takeoff, of course. Now, you have also attitude indicator, you have the airspeed indicator. For example, by the way, during takeoff, the co-pilot would need to notify the pilot whether the VSI is positive or negative, okay? Or it won't be negative, it would be perhaps 0 or negative, okay? Which means that once the VSI indicates a positive value, it means that the aircraft is climbing. So the co-pilot would tell the pilot, positive rate or positive climb, gear up. So now it would be safe to retract the landing gears because the aircraft has a positive climbing rate. It means that it is increasing in altitude. It is taking off correctly. Okay, it's getting away from the ground level. Okay, it's climbing. Okay, now primary flight instruments such as the airspeed indicator, the altimeter, the VSI, vertical speed indicator, and attitude indicator allow the pilot to evaluate lift generation, whether the aircraft is creating lift. If it's creating lift properly, it means that it should be climbing correctly, okay? Altitude control, climb or descent rates. So climb rate, let's say 500 feet per minute. That would be a positive climb rate, or a minus 500 feet per minute. That would be a negative climb rate, okay? Negative descent, actually. Negative rate, but a descent rate, okay? Which means that the aircraft would be descending. It would be decreasing in altitude. For the first case, it would be increasing in altitude. And aircraft orientation, which is indicated by the directional gyro or the compass, commonly named, okay, which would give you the direction, the heading of the airplane in respect of what? Of the north vector. Okay, now from the north, when you rotate, okay, I think the rotation is, yeah, the heading would be measured clockwise in reference to that north. So when we talk about heading 90 degrees, that would be 90 degrees heading from the north direction, from the magnetic north. Okay, of course, the perfect north and the magnetic, there may be some degree of error between them, okay, that the pilot will have to account for. Now, for example, airspeed indication is critical for maintaining safe margins above stall speed and below structural or regulatory limits. Okay, what is the stall speed? Stall speed is the airspeed at which the air would no longer have a laminar flow around the wings. It is the speed, and it would be a low margin, okay, a low level of speed at which the air is no longer able to generate lift around the wings. So the aircraft would stall, it would lose its upward force vector, so to speak. Stall, it means it will start falling down to the ground. It's no longer generating lift. Now, it can either happen due to a large angle of attack, okay, so the air is no longer able to flow around the wings because you've, most of the air is now dragging, causing a drag effect on the wing instead of lift, or it can be slow flying speed during, for example, due to an engine flame out, or another possibility, it would be the icing formation on the wings. It would degrade enormously the performance of the aircraft, causing a stall, okay, by increasing drag and reducing the lift properties of the wing, okay, because it would disturb the laminar flow of the air around the wing section. So it is critical to measure the airspeed in order to know whether you're above stall or stall speed or at the stall speed, because once you hit a stall, there's another warning system, by the way, within the aircraft. Other than the indicator, you have the stick shaker, which means that the yoke would start shaking violently to indicate that you are entering a stall. Okay, so in order to correct it, you need to lower down the nose by pitching downward, okay, by moving the yoke forward or the steering wheel forward to gain more speed to reduce the angle of attack, okay. Gain more speed by using the horizontal component of the weight of the aircraft as a forward force, okay, to make the airplane cut through the winds and to generate more lift. So once you gain enough lift by increasing the speed, the velocity of the aircraft, you would gain more lift. This is how you would be able to get out of stall, okay. But also, very high air speeds can be way dangerous for the aircraft. Why? Because it would damage its structure, okay. It would be structurally damaging, meaning that different controls of the airplane would start flying off, like even the doors of the landing gears would start ripping apart, okay. So it would inflict a structural damage, okay. That would be the overspeed. This is why you need to stay within the acceptable margins. But not only that, based on regulations, there are certain speeds that you cannot cross over, otherwise you'd be fined, even as an airline pilot. Okay, so while altitude and vertical speed indications ensure compliance with flight profiles and air traffic control clearances, okay, so you have different instruments for different measurements concerning airspeed, altitude, VSI, so as to remain within the regulatory confinements, okay, of flying, but also to keep the aircraft airworthy, meaning flyable and avoiding any structural damage while increasing the efficiency of the aircraft as well. Engine and system instruments further influence performance management, okay. So parameters such as the engine RPM or tachometer, which measures the number of revolutions of the blades per minute around the axis, the turbine, at first you have the manifold pressure, the pressure generated by the engine, the EGT or exhaust gas temperature, which is the temperature of the exhaust, okay, can detect an overheat within the engines, turbine inlet temperature, okay. So turbine inlet is the section of the engine where there's the air intake, okay. So it is the head of the turbine, okay. Actually, no, not at the front of the engine, at the head of the turbine, okay, where the intake air is measured for the temperature, okay. So it would measure the turbine inlet, okay, where the air suction is performed. That would be measured temperature wise. The oil pressure would indicate whether the engines are properly running or not. So when you have a flame out, you would have a decrease, like a significant drop of the oil pressure, which means that the engine is not or is no longer running. Fuel flow also provides insight into the engine efficiency, how much fuel flow is being received by the engine. Thrust output, okay, how much thrust is being generated, and thermal limits. Now, deviations from normal indications may require performance adjustments, okay, such as adjusting the throttle, power reductions, reducing the flow of the fuel to the engines, or emergency procedures. Let's say you have an engine on fire or an engine backfire. So the proper thing is to reduce the engine at first to idle, set it to idle, try to solve the problem. Now, otherwise, if it was not solved, you need to extinguish the fire, which will completely turn off the engine, and you cannot undo that in mid-flight. In modern aircraft, performance data is often integrated into electronic flight displays such as the ECAS, the ECAM, okay, and the flight management system or FMS, which constitutes the ECAS or engine indication and alert crew system, plus the ECAM or electronic centralized aircraft monitor, okay, enabling performance calculations such as takeoff distance, climb gradients, fuel consumption. Consequently, aircraft instruments serve not only as monitoring devices, but as essential tools for optimizing performance while maintaining safety margins. Aircraft system redundancy and safety philosophy. Now, why is redundancy very important? Because you see, for every system, I need a backup for it on the plane. Why? Because if you have a breakdown, you cannot fix the airplane in mid-flight. You need something running as an auxiliary, whether power or an auxiliary unit, okay? And to provide redundancy is for safety measures, so that in case an instrument broke down, you would have an alternative in order to monitor the performance and the attitude and other controls, like the status of other controls of the aircraft, and to have a situational awareness, to have to understand how your aircraft is performing, basically, okay? To check the performance, to check the different indicators, okay, on alternative instruments in case the main instruments broke down, so that you can still have control over the airplane, and especially during night flight, because you would not have a reference for the horizon when there's no visibility. So you need instruments to understand where you are situationally, so to speak, okay? So aircraft systems are designed according to a layered safety philosophy that assumes failures are possible and must be mitigated or reduced. One of the core principles of this philosophy is system redundancy, having more than one system running, which ensures that the failure of a single component does not lead to a catastrophic outcome. Redundancy may be implemented through multiple independent systems on board performing the same function. So And why do they need to be independent? So in case one of them shut down or broke, okay, or malfunctioned is the more accurate technical word, you can rely on the other being operational and still running, okay, independently. Because in case they were attached to the same cable, let's say, okay, in case you had two instruments and you have layers of redundancy, but let's say these two instruments are almost the same device but two different display, it won't work. Because in case the main instrument shut down, both display would go out. That's why we need that standalone and that independency between the different instruments that are redundancy, that are the same thing, the same type of instrument but replicated. Okay, the same instrument having, but we have two of that. Okay, two pieces of that on board, so that you can monitor and you can verify the performance via two main instruments. In case one broke down, you can still follow the other and rely on its measurements, okay, and remain confident that you are getting accurate values. So examples include dual or triple hydraulic systems. Also, it's not only the indication systems, but also the hydraulics. Multiple electrical generators like the APU, like the ram air turbine, in case you have engine flame out, and we know that the engines is what generate power. It is the power generator on board during mid-flight. So in case both engines flamed out, you need an alternative power, and that is usually by deploying what is called the RAT or ram air turbine, which is a turbine that falls beneath the beneath the airplane. Okay, it's deployed from beneath, and the air going through it would generate enough power to keep running crucial, essential instruments that are very necessary in order to maintain, in order to maintain a situational awareness over the performance of the aircraft, over the altitude, the VSI, okay, necessary to make at least an emergency landing. Okay, you have two independent PITOT-STATIC sources, which are the same. This is actually the device that measures airspeed, altitude, and VSI. Very important. In fly-by-wire aircraft, you have flight control computers are often arranged in multiple channels with voting logic to detect and isolate faulty data. So if you have a faulty data, it would be relegated to another computer, to another processor to manage the flight, okay? Instead of relying on only one source of computing, which can be sending falsified measurement data. In addition to redundancy, system segregation or separating between systems is used to prevent a single event, such as fire or structural damage, from disabling or taking out multiple systems, especially redundant systems, simultaneously. Why? Because if you had a fire and you have two systems that are a redundancy, meaning they are the same thing but distributed among or divided into two instruments, okay, that do the same functionality. Let's say you had a fire. It can take out the original system and the redundant system as well. So you wouldn't have done anything because it would no longer be a reliable architecture. Why? Because you had taken out the same vital system twice, distributed among two separate instruments. So we need to ensure that if one instrument failed, its backup, that's the word I was looking for, should be working properly. Why? Because you had isolated its wiring and its installation from the first. They should be completely segregated and independent. So the failure of one should not take away or take out the other. Very important. Now, this includes physical separation of wiring, physical separation of hydraulic lines. So if one rupture due to the impact of a solid object or something breaking in the plane, the other one would not rupture. Why? Because it's positionally separated, okay, geographically within the airplane or anatomically, to be more accurate, separated from the other hydraulic line. And also electronic components throughout the airframe. So you would have multiple computers distributed in different places of the airframe as a backup. That would be something usually done in fighter planes, okay? Multiple computers back up each other. Now, the safety philosophy also incorporates fail-safe and fail-operational concepts. Fail-safe systems revert to a safe condition following a failure. So if a failure took place, you have a fallback to another system that is a backup, okay? It might be the next best thing after the failure, okay? While fail operational systems continue to function normally despite certain failures, okay? Together, these design approaches ensure that aircraft remain controllable and safe under a wide range of abnormal and emergency conditions. As an example, let's say during landing the ASI for whatever reason had failed, the airspeed indicator. You have another device measuring airspeed, which is not actually airspeed. It would measure the speed of the airplane based on the ground. Okay, it's called the ground speed indicator. Okay, the GSI, if we can call it that. So how does it work? It sends signals to the ground and it measures how long it took the signal to be reflected on the ground and then to get back to the receiver on the plane. Okay, this way you can measure the approximate speed of the airplane based on the ground. Okay, now of course in this case the aircraft should be close to the ground relatively. Okay, that would be during the landing phase, but that would be a backup, okay, an alternative to the ASI in case the ASI had failed. That would be the fallback. Now the fail operational, that would be the fail safe system. Okay, the fail operational is that it continued to function normally despite certain failures, meaning you have a backup within the system. Yeah, it can be explained in different ways depending on the system again. Okay, like if I'll do without the jargon here, if I'll set it aside, okay, that would be like, for example, a fault within the hydraulic system, but you have another hydraulic pipeline, okay, that is driven by manually instead of the one driven by the autopilot. That would be, you would take over, disable the autopilot, and continue to fly manually on the second hydraulic line. Certification standards, FAA and EASA, okay. FAA is the Federal Aviation Administration, which is in the United States, and EASA is the European Union, okay, Aviation Safety and Agency. EASA is basically the one that governs flying in Europe. So aircraft instruments and systems must comply with strict certification standards established by regulations, regulatory authorities to standardize. Okay, this is mainly to standardize flying, so that it won't be that each agency would be, or each company, airliner, would be going on one level, like doing their own regulations. Okay, it would be standardized. The two primary organizations, again, are the FAA in the United States and the EASA in Europe. Okay, both authorities issue regulations covering aircraft design, production, operational limits, and maintenance. Okay, key certification documents include FAA Title 14 for federal regulations and the EASA certification specifications. These standards define requirements for system reliability, failure probability, environmental qualification, also the standard for creating, for designing airports, but that would be in another book other than this. Okay, now human factors, like how many hours should a pilot sleep before being allowed to pilot an airplane. Also, we know that drinking is not is prohibited for pilots. Okay, especially hours before flight. and continued airworthiness. Okay, airworthiness meaning is the airplane still flyable, okay, and how many hours is it allowed, or how many cycles is it allowed to fly. A cycle is one compression decompression, okay, so each time it flies and it lands, that would be one cycle. Now instruments must remain accurate and readable under vibrations. This is another important caveat for the standards. Temperature extremes also should not, block the instruments or prohibit the reading of different values such as the ASI, the airspeed, the altitude. It should not be generating errors due to extreme weather conditions. Okay, and we're mainly here talking about the pitot tubes, but other devices also follow suit. Okay, electromagnetic interference also should not shut down the capture and reading of values on board by instruments, different values, different measurements, and also varying pressure conditions. Although FAA and EASA standards are not identical, they are largely harmonized. Okay, so aircraft certified under one authority can often be validated by the other with minimal additional requirements, facilitating international aircraft operation and manufacturing. Basic aircraft terminology and system architecture. Understanding aircraft instruments and systems requires familiarity with basic aircraft terminology and system architecture. What are the different systems on board and that make part of the aircraft? Okay, what are the different devices of these systems and the necessary jargon and terminologies that go along with these systems. An aircraft is generally divided into major structural components, including the fuselage. Okay, that's everything within the airplane, like the airframe without the wings. Okay, that's the fuselage. The wings, the empennage, landing gear, and power plant. Power plant is the engine. Okay, now you have also the vertical stabilizer. It's part of the fuselage, and the elevators are part of the wings. The rudder is also part of the wing, you can say. Now, aircraft systems can be broadly classified into several functional groups. You have flight control systems, primary and secondary controls. You have the power plant, the engine generating power and propulsion systems. You have electrical power generation and distribution through the engine. Usually the engine is the same source of electrical power because it's at the same time a generator for power to drive the power, to feed different instruments on board. You have the hydraulic and pneumatic systems that also drive their power from the engine. Okay. Avionics and navigation systems, which are the different displays on board within the cockpit, and environmental control and pressurization systems, among which you have the air conditioner, the gasper, all of these systems that drive or control the environment. Okay, the temperature and the pressurization, the air pressurization of the cabin. System architecture describes how these systems are arranged, interconnected, and controlled. Traditional aircraft rely on mechanically driven systems with analog instruments, so analog measurements. It's not digital. Meanwhile, you have digital data buses and centralized monitoring systems are different. Okay, so you have analog instruments, while modern aircraft use integrated modular avionics, which means a screen that displays multiple measurements, multiple instruments at the same time. Okay, like digital data buses, you have digital data bus that collects from different instruments, and you have a centralized display, and you have centralized monitoring systems mainly like the ECAS and the ECAM, the engine indication and the crew alert system, or crew crew alert system, and also the ECAM, which is the electronic centralized aircraft monitor that monitors the aircraft, monitors different instruments such as the altitude indicator, altimeter, ASI, VSI, etc. For the ECAS, it monitors the engines and the oil pressure, the oil temperature, etc. Okay, and the EGT, exhaust gas temperature, among other things that I might not have remembered at this moment. So, clear terminology and a structured understanding of system architecture allow pilots, engineers, and maintenance personnel to interpret instrument indications correctly, okay, diagnose faults efficiently, and correctly localizing or locating and isolating a problem and a fault, and operate the aircraft safely and effectively. Second chapter of aircraft instruments and systems. Here we're going to talk about principles of aircraft instrumentation. Okay, this is like, so this is the second module, principles of aircraft instrumentation. Let's start at first with the measurement fundamentals. Okay, aircraft instruments are designed to measure physical quantities and convert them into usable information for pilots. Okay, physical values or physical quantities such as like the pressure, the temperature, things like that, and based on these readings they would provide alarms or warnings, or it would display what is an analog info into a readable info that can be used and understood by the pilot. Okay, let's say you have a binary system on an instrument that is electronically being displayed. It cannot be displayed as binary in the binary format as zeros and one. It should be converted like computers basically to a readable format, okay, like in an ASCII system, so that you can read real numbers and real words, okay, that should be meaningful to you as a pilot or as an aircraft maintenance engineer in order to be able to troubleshoot and to assess the performance of the aircraft. Okay, the accuracy and reliability of these measurements are essential. They need to be accurate, giving you real, accurate, precise measurements, and reliability meaning they should be reliable or trustworthy under whatever flying conditions that you are under, whether icing, whether hot weather, whether rain, okay? Now, which is essential for safe aircraft operation. The most common physical parameters measured in aircraft instrumentation include air pressure, temperature, speed, and position. By the way, through the pressure measurement, okay, in the PITOT-STATIC system, through that reading, the altimeter can actually get the value of the altitude. So the altimeter converts that the pressure differential between the pressure from the outside, okay, and the static pressure, which is the air that has been kept and sealed when the airplane was still on the ground before flying into a specific altitude. Okay, so the difference between that static air, which is the pressure at ground level, and the dynamic air during flight, that differential can get us to calculate the altitude, the VSI during movement of the air, okay, vertical speed indicator, and what? The airspeed. So these instruments can measure that, can evaluate that, and display it in a readable format to pilots based on these measurements of the pressure, okay? Because through the difference of pressure, we cannot understand, okay, at which height am I? The instruments do that, okay? Like by changing the needle based on that pressure differential, I can actually read on the display the value of the altitude, the actual altitude, the airspeed, okay, speed of the air moving through and around the aircraft, which is actually the speed of the aircraft within the air, okay? And also the VSI or vertical speed indicator, okay? So temperature as well, speed and position. Position is mainly based on the GPS, for example, another instrument, or position in respect to the runway when we talk about the ILS system, instrument landing system, like your position in respect to the localizer, which is the vertical plane crossing the middle of the runway, okay? So if you are to the right, you should be correct to be aligned, so that line should be at the center of the attitude indicator, and the glide slope, which is the horizontal line. If like the golden point on the attitude indicator, that cursor is underneath the glide slope, it means that you are very low, okay? You are beneath the descent slope. If this dot is above the horizontal line, it means that you are over the glide slope, so you're about to shoot the runway, okay? So you need to adjust in a way to access the glide slope, to enter the glide slope in a perfect way, and to stay there until your final touchdown and landing. Pressure measurement. So pressure is one of the most fundamental parameters in aviation instrumentation. It is defined as the force exerted over a surface area, okay? Force exerted per unit area, and is commonly measured in Pascal or PA, okay? You have another international system measurement unit, which is Pascal per square inch, okay, or PSI, okay? So it would be Pascal per square inch, because the PA, Pascal, is per square meter, okay, or inches of mercury in Hg. Now, in aircraft, pressure measurements are primarily obtained through the PITOT-STATIC system, okay, the pitot tube and the PITOT-STATIC system. Static pressure is used to determine altitude and vertical speed, okay? So the static pressure is used to determine altitude and vertical speed, VSI, while dynamic pressure, which is the ram air going through the PITOT-STATIC tube, is used to calculate what the air speed, okay, the speed of the airplane. Pressure sensors may be mechanical, such as diaphragms and capsules, or electronic, such as piezoelectric or strain gauge transducers. Okay, we're gonna understand it better in the further slides. Now, accurate pressure measurement is critical for flight performance, okay, navigation, and compliance with airspace requiremements. Errors in pressure sensing can lead to incorrect altitude or airspeed indications. So it would give false assessments to the pilots, and distort their situational awareness on whether they are flying too high, too low, too fast, too slow. These are very crucial and important pieces of information, okay? Potentially, it can compromise the safety of a flight. As an example here, so let's talk a little bit about the altimeter, how it measures the altitude. You see here, this compartment is where the stored, is where we store the static air from the ground level. So the static air, which was collected when the airplane was still on the ground before taking off, before increasing and climbing in altitude and actually starting the journey, this is where the air is stored and locked within this diaphragm-like compartment. Okay, now, as the altitude increases, what happens is that the difference between the pressure stored inside the diaphragm and the pressure of the surrounding ambient air, okay, at a specific altitude, this difference increases. So what happens is that the air on the inside would start pushing, dilating, because of that pressure differential, okay? It would start extending and dilating these aneroid wafers. as it dilates, it will motorize, or it will move something, this rotor-like mechanism. This in its turn will rotate these gears that are connected to the needles within the altimeter, and hence the altimeter would, the needles would rotate, indicating the value of height or altitude based on what? Based on that difference between the external pressure and the internal pressure that is locked within this sealed compartment. This difference of pressure would again rotate this internal mechanism. I don't know what do they call it here, like a rotating gear, which is connected to the needle on the inside of the altimeter, that in its turn will display current altitude. Now, to the left, you have the VSI, or vertical speed indicator. To the right, you have the airspeed indicator, ASI. And by the way, the three of these instruments, whether the VSI, the ASI, or the altimeter, the three of them depend on the pressure measurements in order to display or to give us the values, the different values of the parameters that we are after, whether the speed of the air, the airspeed, or the VSI, okay, the climb rate. Okay, VSI give us the climb rate. So climb rate, how many feet per minute are we climbing in case the airplane is climbing, or the descent rate if it's diving. And for the altimeter, it gives us the altitude. So for the VSI, because we've already explained the altimeter, how does the VSI work? And you have a common denominator, which is the diaphragm locking static air on the inside that has been locked and sealed when the aircraft was still on the ground, which is used as a reference point to measure the altitude, the ASI, the airspeed, and also the vertical climb or descent rate of the aircraft. Okay, at first, if we look, so you have the direct static pressure here. You have a calibrated leak in order to readjust the pressure of the air when you are on the ground before you seal it. Okay, now once the aircraft becomes airborne again, so what happens is the difference between the pressure of the air that's locked on the inside of the diaphragm and that which is on the outside, okay, that pressure starts, the difference of that pressure starts increasing. Now, as the airplane goes up, so the pressure of the external air or ambient atmosphere becomes so low to the point that this diaphragm will start extending, dilating. Now here it dilates and then retracts, by the way. Why? Because when it changes, if it changes rapidly, it dilates quickly to display a positive climb rate. Okay, it dilates. When it dilates, what happens is that it rotates this needle, so it will display a vertical speed, okay, a positive climb rate. And then once it stops climbing, so it will return, so it's somewhat elastic. This diaphragm will retain its original shape. Okay, now meanwhile, when it's descending, this is what happens. The opposite happens. It means that it will collapse. Okay, why? Because now the pressure, the external pressure, is increasing, so it will start becoming more extreme than the pressure of the air on the inside. Okay, so it will collapse it, which will make the needle rotate downward. Okay, so it will rotate upward for positive climb rate, which is due to the extension or dilation of the diaphragm, and it will collapse. The diaphragm will collapse, will crush, will compress, rotating the needle downward during descent. This is how the VSI works. Airspeed indicator. Now, for the ASI, how does it work? You have, again, for the PITOT-STATIC system, everything like the ASI, VSI, and the altimeter, the three of them are connected to the pitot tube. Okay? Now, for the pitot tube, it receives a ram air, or like the dynamic air, through that inlet. Okay? It enters via the pitot tube, and then for the ASI, it will start pushing against this diaphragm that has static air locked on the inside of it. Okay, again collected from the ground level atmosphere. So as it pushes it, and this is how it works, the ram air, okay, it has a dynamic pressure, which is, by the way, the dynamic pressure, or Q, is 1/2 rho v squared. So as it pushes it, or pushes against the static air within the diaphragm, it will start rotating a lever that in its own turn, it will rotate the hand staff pinion, okay, through a gear. This is a sector here, and this will rotate, the hand staff pinion again, which is connected to the needle that will indicate the air speed. And usually the measurement or the measurement unit is in knots. All right, it can be converted to miles per hour, but usually the official system is in knots. Okay, and this is how it works. So it depends vitally on the ram air, the dynamic air being inhaled by the pitot tube. This is why, if in any case the pitot tube gets like pinched, or it gets stuck on something, or something gets into it, it will prevent the air from moving freely on the inside, which will cause wrong measurements. Okay, it can lead to, actually there was an air accident that led to large fatalities due to a static tube getting, I'm trying to find the correct word, it got sealed, okay, due to one type of birds that usually creates, or one type of a bug, okay, an insect that creates its nest within these types of any type of cavity, and they had forgotten to seal it, to seal the air, the pitot tube. That's why it got to that point where it led to a great accident. Temperature measurement. Now, temperature measurement is essential for monitoring engine operation, air density, because density and temperature are interrelated, especially when it comes to gas. So when we're talking about the atmosphere, when we're talking about the engine, the air within the engine, it all depends on pressure, okay? So pressure and temperature are correlated. And system performance. Now, common temperature measurements in aircraft include outside air temperature, or OAT, EGT, or exhaust gas temperature, which is the temperature of the air at the exhaust of the engines, okay, which is the exit of the engine. It can tell us whether the engine is overheating or not, okay. And you have the turbine inlet temperature, which is the inlet of a turbine where it's sucking the air, okay. So it is at the level of intake of the air where we're measuring the air temperature, okay. Turbine inlet temperature, or TIT. And also the oil temperature. So if it's overheated, we might be suffering from an overheat of the engine, and the engine might have a big problem, okay. So if you have an overheat of the oil, it means that there's no cooling within the engine, or there's a big problem developing, okay, depending on the scenario. So mainly, the temperature of the oil should be nominal. The temperature of the EGT, exhaust gas temperature, also should be nominal. If we are going above specific limits, it means that the engine is overheating, okay? And a bigger, more serious problem can be developing on the inside. Now, temperature sensors typically operate based on changes in electrical resistance or voltage. Exactly. You see, you have what is called the thermistor, okay? Thermistance in French. Okay, the thermistor is a resistor that changes in value as the temperature increases or decreases. In other words, consider a thermistance, okay? So you have during cold or in normal operating conditions, the material, which is, by the way, made of conducting material that is stitched together. Okay, so during cold weather or normal operating conditions, when you have a low temperature, this material, the molecules of this substance are stuck together, which is a conducting substance, by the way. So the current would go easily. It would act as a short circuit, conducting the current perfectly. Meanwhile, as the temperature increases, these molecules would start going apart, like dilating, because the material would start dilating and the molecules would start growing apart from each other, which will create more gaps. So the current will drop. The resistance against the current would increase. To give you a more clearer picture, if you imagine the temperature rising to 1000 degrees Celsius, for example, okay, what will happen is that this resistance would dilate indefinitely to the point that it will snap, it will break, which will create an open circuit. So the current going through it would be completely zero. Why? Because it became completely resistant, meaning it's now an open circuit. It's no longer allowing any current to pass through. Why? Because you have, pure air, pure void between the two connectors of this resistance. Okay? Now, of course, that would be the extreme case. However, when you have, and it can happen, by the way, but even as the temperature increases, this material would start dilating more and more, forbidding more current to go through it. Why? Because the molecules are no longer intact and interconnected with each other, so less current would be going through, or the resistance value of that resistance, okay, would grow, okay, it would increase. Now, we can easily, in such case, interpret the dip of the current to a specific level as an alarming thing, as, an overheat having occurred to the engine or wherever this measurement device has been installed. Okay, so as this current decreases, you get to a point, okay, now we know that you have a very high temperature. This is when the alarm overheat, okay, would be the overheating alarm would be signaled or warning. It can be warning if this dip in resistance or dip in current, okay, increase in resistance, but a dip in current is not as serious. But when you have it snapping completely and completely cut, it means that you have a fire on board that had completely melted this resistance, okay, and you would get within the cockpit a fire alarm. So hopefully this explains it. Now, another type of sensors can be, by changing voltage. Actually, yeah, you can connect a voltage to that resistance when it opens up, or it would be connected to another thing. So the change of this resistance would also change the voltage. Okay, but it's not necessarily only this type of sensors. You can have another type which is voltage based. Okay, so when you have a change of voltage, it means that you have a change of temperature, and based on that, you would have an alarm signaling off in the cockpit, or a notification, or like a LED being set off. So devices such as thermocouples and resistance temperature detectors, RTDs, this is what we were talking about, thermistors or resistance temperature detectors, are widely used due to their reliability. So you can account for them, you can count on them to accurately describe what's happening, okay? And they have a high accuracy over wide temperature ranges, meaning that the resistance would definitely change only based on the value of the temperature it's being exposed to, which will give us a good estimation or good estimated measurement of the temperature. Okay, so it's not only for alarms, it's not binary, whether you have fire or not, or you have overheat or not. No, you can get an accurate measurement of the actual temperature within the engine or within any part of the airplane when you have this kind of RTD installed. Now, temperature data influences engine control. Also fuel efficiency, because when you have an overheat, it changes things. Okay, and icing detection. Okay, when you have when also the resistance is so low, it means that you have icing. So the current not passing through is not always, or the current fully passing through the conductor is not always a good thing. If you have a maximum current, it means that it's so cold and freezing, okay, that you need to de-ice where you have placed this sensor. Okay, so the temperature data is very important. It can influence engine control during icing conditions, icing detection performance calculations, okay, because based on the EGT, for example, the exhaust gas temperature, you would assess how much is being burned, okay, if the fuel is being effectively burned or if there's a residue within the engine, meaning that, and which can result in engine backfire. This is usually when you have broken blades stuck within the engine, which will disrupt the airflow, forbidding the airflow from moving freely within the inner parts of the engine. So the fuel would not be fully consumed or burned up, which will cause an engine backfire. So it will fire on the inside, okay? It would not fully be burned out, okay? Or front fire even. It would start projecting forward. This is when you have a lack of oxygen, okay? So you don't have a full burnout of the fuel that's being mixed on the inside, okay? Due to that choking. It's like when you burn wood, the wood would not completely burn. You don't have a blue torch. Meanwhile, when you burn gas, okay, you don't have residues. The gas would fully burn in a blue torch. This is why, by the way, when you look at the engine of the airplane, you don't see fire because it's fully burning. It's fully being consumed. That's almost very clean, okay? Of course, with some toxic gases, but the consumption of the fuel is full. You have full burnout, okay? But when you have a problem, you would start seeing the fire, meaning that the fuel is not being properly combusting. Now, temperature data influences engine control, fuel efficiency, again, icing detection. For example, air density variations due to temperature directly affect lift, correct? So the lift would be affected due to these fluctuations of temperature. Why? Because for colder air, you have a denser, a cold air is denser than the hot air, okay? So it will increase the lift and thus it will affect the performance of the entire aircraft, okay? It will affect also the thrust. So in hot conditions, the aircraft needs to have an increased thrust in order to maintain the same lift. And the climb performance is also affected by these temperature fluctuations or by the changes on the temperature, okay, depending on what temperature you have on the inside or on the outside in the atmosphere, you'd have different performances for the aircraft. Speed measurement, we've already discussed that, but let's read it again. So this is the airspeed indicator, and we've seen how the instrument is made on the inside, okay, the anatomy of the instrument, how you have a diaphragm which is exposed to the ram air that is coming from the inlet of the pitot tube, and when that air pushes against the diaphragm, it will rotate the needle of the ASI or the airspeed indicator. So it's depending on differential of pressures. So the speed measurement in aviation can refer to airspeed or ground speed, which again works in a completely different way. Why? Because it sends a signal towards the ground, and then by measuring the distance or the time it took to go from the airplane to the ground all the way back to the airplane, okay, and by measuring the time and the distance, you can get the velocity, all right? So The airspeed is derived from the difference between pitot pressure, which is the pressure of the ram air, and the static pressure, while ground speed is determined through variations or through navigation systems such as GPS, okay, global positioning satellite. This is how it works, okay? This is basically how the ground speed indicator works. Now, also another type is rotational speed, which is actually the RPM, okay? That is the measurement read by the tachometer. Engine speed is measured using tachometers, okay? Which indicates revolutions per minute, RPM, or percentage of maximum speed in turbine engines. Speed measurements allow pilots to operate within structural and aerodynamic limits in order to avoid stressing the structure or the airplane, or when you have a high speed, or avoiding the stall when you have a low speed. The stall is again when the aircraft can no longer generate lift because the incoming air, the flow of the air around the wings is no longer enough, okay, is no longer within the limits of the acceptable value of the speed, the dynamic speed, in order to lift up the wings, okay? It's no longer flowing with enough momentum, with enough speed in order to generate lift. So speed measurements allow pilots to operate within structural and aerodynamic limits and ensure engines are producing the required power. Position measurement. Position measurement refers to the determination of an aircraft's attitude, which is whether it's banking left or right and how many degrees, because the bank is an angle between the surface of the plane, okay, and the horizontal reference, okay, the horizon, which is parallel to the Earth, the ground surface. And the control surface position, meaning the different controls, whether the flaps, the ailerons, the elevators, and the rudders, their own position. The landing gear status, whether it's dropped or retracted, okay, and navigation position. So it detects the different positions of the controls. So when you have a rotation, okay, and when you're applying a rudder, the rudder adjustment will, like the rudder value to the right or to the left, it will appear, it will be measured. The elevators would be measured, okay, how many degrees, the flaps, so when you apply a flap of 5 degrees, you will see it changing on the display. The ailerons, etc. More than that, okay, you have the attitude indicator, which again present to you whether you're flying level, okay, so if the aircraft is pitched up, this dot here, you see this orange, okay, line on top, it would go above to the part of the blue circle. So here it's pitching up. Now, if it's pitching down, it will go to the brown disc, okay? This indicator, the orange line, it would go to the brown disc. Now, if it's rotating left or right, you see the banking here, bank to the left, bank to the right, and how many degrees. You would have the roll, the pitch indicator, etc. Okay, now, so these are common measurements of positions that are very necessary and important within the aircraft. Now, what are the different devices that perform that within the attitude indicator, which is the instrument? You have, first of all, the gyroscope, okay, like the rotating disc, which is the reference point of the horizon. It keeps rotating, and as the aircraft moves left and right, the rotating disc remains static, okay, it remains horizontal to the ground. That would be the reference on how many angles, how many degrees the aircraft is rotating to the left or to the right. Also, you have, as for the the pitch up and pitch down, the same thing. So as the aircraft is pitching up, you have the accelerometers and potentiometers that resolve that display, okay, to show you, to give you again a situational awareness whether whether the nose of the aircraft is up or down. Okay, if it's up, it means it's like this, usually during a climb, but not necessarily during the landing. It would be pitched up, despite the fact that the aircraft would be descending. Okay, so it would have a negative descent rate, which is a negative feet per minute. Okay, or during the climb, it would be pitched up, but again, not necessarily. Also, okay, so you have nose down during the descent, okay, during normal descent, but before the landing phase. So modern aircraft increasingly rely on IRS, or inertial reference system. Okay, inertial reference system is what gives you the position on the earth. Okay, its name is ADIRU, I believe, Air Data Inertial Reference Unit. That would be the device, which is in the Boeing 777, I believe. It's also in the Boeing 787 or Dreamliner, the same device. And satellite-based navigation systems to determine aircraft position with high accuracy, which is very important. Position measurements are vital for flight control, autopilot operation, because the autopilot relies on the measurements to control the airplane. If the measurements are faulty, it can drag the airplane to the ground. Okay, that's why the human factor will always remain important on the inside of the aircraft. Okay, so position measurements are vital for flight control, autopilot operation, and situational awareness. Now, what is the anatomy of the attitude indicator and how does it effectively work? Okay, how does it work? So, at first you have the roll gimbal here, which is when the aircraft is rolling, that would be rotating left and right. Okay, you see here the gimbal rotation. Now, you have in the middle, okay, here you have the horizontal disc, the accelerator that would keep rotating, okay, and that would be rotating horizontally as a reference plane, okay, as an horizontal reference. So as it rotates, it will remain always parallel to the horizon. This is why it is so important, okay. Why? Because you see this, yeah, and it's called a gyro, by the way. Okay, so the gyro, as it accelerates, it will remain always in the horizontal position. Okay, this is something that was discovered in physics. So it doesn't matter whether the airplane is banking left or right. This gyro will always remain on the horizontal position as it rotates at high speed, which is very important. Why? Because we need it as a reference position. So when the aircraft rotates, as you see in the picture here, okay, to the right, let's say to the right, okay, you're standing behind this attitude indicator here, and it's rotating, the aircraft is rotating to the right, okay, like this. So as it rotates to the right, there would be a different angle between this roll gimbal and the gyro, okay, which would steady the horizontal reference arm. Why is it called reference? Because this arm needs to always be horizontal, parallel to the ground at all positions. So the difference between these two, the horizontal arm, okay, and the rotating gimbal, that would give you how many angle you are rolling. You're banking to the right or to the left, so that you can have a situational awareness to know whether you're up or down, or you're rolling, or if you're slanted. Because during night operations, you can never, and especially that the gravity would change based on the direction of the airplane. You can never realize, okay, or understand whether you are on leveled flight or whether you're rolling. So if the aircraft is rolling, you won't even notice it without this instrument. That's why it is very vital. Now, when it comes to pitching up or down, the same thing. So as you pitch up, as the aircraft pitches up, so the noise goes up. However, the gyro will always remain horizontal. Okay, so as the noise pitches up, it would be noticed here. Okay, why? Because this indicator would go upward. Meanwhile, the gyro would be fixed, which is, by the way, this is the orange line here. It's connected to the gyro. It will remain on the horizontal position, the perfect horizontal position. But you would have like this sky. Okay, so it will show you as if this horizontal line, which is the reference plane of the aircraft, okay, the reference line of the aircraft, it would go up to this blue area of the disk, the blue and brown disk, which it would indicate to the pilot that the airplane is pitching up. And by the way, it will also give you how many degrees it's pitching up. 5 degrees, 10 degrees, 15. 15 is acceptable, but above, especially for small aircraft, it can lead to a a stall prematurely, especially on high altitudes. Okay, so now when it comes to the roll, we've already explained it. Okay, so both the roll, and these are the degrees for when the aircraft is rolling. So the roll would be measured, and also the pitch up or down. So when it's pitching down, you would have this reference head going downwards. Okay, I'm sorry, the reference, it would be, yeah, like this here would go, yeah, the reference head, sorry, the reference would remain on the horizontal position. However, this line here, this orange line, okay, would appear to be going downward. In fact, the brown area would be going up, which means what? Which means that you are diving, okay? Which means that you are diving. So this area would be going down, okay? Meanwhile, the disk is still on the same position, but this area, this orange area, would be going down. Why? Because the disk position is always fixed by the gyro that's accelerating and rotating on the horizontal plane. So this orange line would go to the brown area, indicating that the plane is in the dive position. I hope it is clear, and sorry if I carried a little bit too long, because it's a little bit complicated sometimes to understand. 2.2 Mechanical, Electrical, and Electronic Instruments. Aircraft instruments can be classified based on their operating principles into mechanical, electrical, and electronic instruments, but they are distinct. Okay, they are completely different, even among, between the electrical and the electronic. Each category has distinct characteristics, advantages, and limitations. Now, for the mechanical instruments operate using physical force or forces and movements without the need for electrical power. So like what we've seen with the altimeter and the attitude indicator and the ASI, okay, you see the instrument, okay, being moved by the air pressure itself to indicate a specific value for the airspeed or the vertical speed or the altitude. Now, examples include the Bourdon tube pressure gauge. Okay, so you have mechanical airspeed indicators, and gyroscopic attitude indicators work this way, mechanically. Okay, they display the values mechanically. These instruments are valued for their simplicity, reliability. They are inherently reliable because everything that is digital and electronic are more prone to malfunction. You can think of your own car. Cars used to be more handy, more practical back in, before 2013. But when the electrical systems started getting into cars and vehicles, especially automation and these things like that, afterwards, okay, the number of faults became more evident, okay, and the system became more prone to different errors, to different malfunctions. Even the cost of reparation became higher, okay, in comparison to a more controllable, more reliable mechanical system that did not use to depend so much on an electronic board, okay, that we call it in for the cars an electrical board, okay, electrical controller. So that's why the mechanical instruments are valued as simple and reliable. However, they are susceptible to mechanical wear out, meaning that vibration can affect them. They can wear out mechanically and break due to friction, due to the gear mechanism being, starting to break down after being used so many times, okay, because there is pressure being applied to these systems. And also limited accuracy compared to more modern electronic systems that are more reliable, more accurate, because computers are usually more accurate when it comes to calculation and measurements. Electrical instruments use electrical signals generated by sensors and transmitters to drive indicators. So we have electrical sensors and transmitters. These are the ones that drive indicators. Okay, examples include electrical fuel quantity indicator. Okay, you have an electrical sensor that once the fuel touches the sensor at a specific level, it will indicate, okay, the fuel is at this level, okay, at 50%, because the sensor is installed halfway depth wise, okay, within the fuel tank. Or you have another sensor on the top when the fuel is, to the top when the tank is completely full. It's at 100% saturation or capacity being filled. It will also light up, which will indicate to you that the tank is completely full, is at 100%. So, okay. Also, you have the electrically driven gyros that represent the horizontal line electrically. Okay, so electrical instruments offer improved accuracy and flexibility compared to purely mechanical systems because they won't wear out mechanically and they are more accurate when it comes to mechanical vibration, unlike the mechanical instruments that are susceptible and prone to vibrations and to wearing out because of excess of use. Okay. Meanwhile, the electrical instruments, the problem is that they depend on the availability and stability of the electrical power. So that's why when the main engine that's actually generating power flames out for whatever reason, you would have an immediate loss of instruments during flight. That's why the RAT or the ram air turbine would be deployed in such case in order to keep running these essential and vital instruments, so that at least you can, the aircraft can provide some control to the pilot so that he would know whether he's pitched up or down, whether he's banking, especially during the night when you cannot take the external horizon as a reference during flight. Electronic instruments. Now, the electronic instruments process sensor data using solid-state electronics and digital systems. So you have an electronic circuitry going on which these instruments depend for their own measurements. So you have the glass cockpit displays, engine indication and crew alerting system, or ECAS. We've already discussed that. So ECAS is the engine indication and crew alerting system, which is a unified display for engine pressure and temperature, EGT, oil pressure engine rotation, oil pressure and temperature, and EGT, which is the exhaust gas temperature, especially in the heavy airplanes such as the Boeing. Okay, and you have the electronic flight instrument system, EFIS, which fall into this category. Now, electronic instruments provide high accuracy system integration, meaning you can have multiple displays on one screen, as we've already discussed, and self-monitoring capabilities, which means that this system will immediately notify you when there's something wrong with a value being collected from a sensor. So when there's an overheat, it would alert you, okay? and if there's something extreme going on, it will fire the master caution alarm so that you would be, you would notice what's happening. Another example, like when you have an engine going down, high oil pressure, all of these, okay, for the electronic systems, they have the capability to self-monitor, okay, to monitor all of these indications so that whenever a value is beyond nominal and it's wrong and it's dangerous, okay, it display for you an alert, or also it can also like trigger a sound alarm, a sound buzz, so that you can pay attention that something is not going right in order to fix it, to fix the problem immediately, to troubleshoot. Okay, just like the alarm systems within, networking devices and routers and these other things, just like when you have, different types of devices or computers, your computer displays errors. The same thing is for the electronic instruments. Okay, it detects errors and then displays them on the screen. So electronic instruments provide high accuracy, system integration, self-monitoring capabilities, and advanced failure detection. So they can detect failures or values outside of nominal acceptable values in an advanced, more intelligent way. Their complexity, however, requires robust redundancy. Why? Because if something fails within the display, multiple displays can be, lost altogether. Okay, so we need redundancy and protection against electromagnetic interference. You need to have redundant, displays, redundant devices, instruments, so that you can back it up, because the electronic display is susceptible to faults. Like it can itself be at fault, or it can be prone to, being affected by electromagnetic interference and no longer work properly. Accuracy, precision, reliability, and errors. Now, understanding measurement quality is essential when interpreting aircraft instrument indications. Okay, several key terms describe instrument performance. So at times you would have an excursion, a different value, okay, a difference or a gap between the actual value of a parameter being measured, such as the airspeed, okay, within the airspeed indicator. So you'd have a difference between the airspeed being displayed and the actual airspeed, which is the actual speed of the airplane. Also, in the same way, you would have a difference between the magnetic north and the perfect north when we're talking about the heading of the airplane. Okay, so the direction of the magnetic north is different than the perfect north. So you would have the excursion when it comes to the directional gyro, okay, the heading of the aircraft. So here is why we need to talk about these indicators or these differences, because when we talk about accuracy and precision, this will affect the performance of the aircraft altogether. And it's not only for key instruments, it's actually everything. Okay, when it comes, it's not only for like the heading and the ASI, it can be also like the engine power, how it's running, if it's measuring correctly the EGT. Okay, you might have faults within the indicators at times. Okay, like if the RDS, the resistance display, okay, for the thermal display, for the resistance, if it snaps, it will indicate fire. Meanwhile, there is no fire. Like the resistor itself had broken. So let's start with accuracy. Accuracy describes how close a measured value is to the true value of the parameter being measured. Okay, so it would be the measured value minus the actual value divided by the actual value. That would be the error rate. Okay, so 1 minus the error rate, it would give you the accuracy. Let's say you have a measurement of 3. Let me try to write it. You would have a measurement. I'm not able to access the pen, I'm sorry. So 3 is the actual measurement, but or the current measurement, but the actual value is 4, correct? So the error would be 3 minus 4 divided by 4, which is the real value. It's 1/4, which is 25%. Okay, so the accuracy would be 1 minus 25 or 75%. An instrument can be precise but inaccurate if it consistently provides the same incorrect reading. Okay, so it's precise, meaning it's always performing in the same way. However, its own performance is inaccurate. Okay, the precision is the ability of reproducing the same results over and over, so it's consistent. However, that precision does not mean that the measurement is accurate. Okay, because you have a constant error rate always, so you need a correct adjustment so that it can measure well. Okay, now precision refers to the repeatability or consistency of measurements, as we mentioned. High precision means that the instrument reproduces the same readings, the same values, under the same conditions or circumstances. That's the important point. Reliability. It is the ability of an instrument to perform its intended function over time without failing. This is what reliability means. So, the aircraft instruments must meet strict reliability standards, okay, after stress testing and different tests. They need to withstand all of these tests to prove their reliability, to prove that they are consistent, that they can outlive different conditions of stress, of high pressure, of extreme operating limits, such as under hot temperatures, hot weather, under icing. Okay, they need to survive that so that they can be reliable during the flight. They can be trustworthy, and because the pilot depends on them for correct readings. Okay, so it is critical to have safety there, okay, and the correct values being read. So they need to meet strict reliability standards due to the safety critical nature of their operation, because all of the decisions made by the pilot are based on the readings of these instruments. Measurement errors. Errors in aircraft instruments can arise from multiple sources, including mechanical errors due to friction, electrical interference when we're talking about electrical instruments, also temperature effects, because the temperature, by the way, can create noise, especially in receptive systems like an antenna, receiving antennas, and different electronics. The change of temperature can change the different value of impedances or the resistance of different components, leading to errors in reading. Okay, but also you have the aging components. So when some components, especially electronic components such as resistor, capacitor, wear out, it would start, leading to erroneous readings. Okay, to error readings, and also environmental conditions. So when you have changes in the temperature, or especially the icing, can affect the instruments so badly at times. Okay, so it could affect the accuracy. At times, the performance altogether is affected, not only the accuracy, but the operability of these instruments. Now, when it comes to mechanical friction, it can affect the rotation of these handles when it comes to these instruments that we've spoke about earlier, such as the ASI, the altimeter, and the VSI. So, errors are commonly categorized as systematic errors, random errors, okay, and gross errors. Understanding these errors allows pilots and maintenance personnel to detect abnormal indications and take corrective measures or actions. Now, if we want to talk a little bit about these three types of errors. So, systematic errors, we would be talking about something within the system, within the instrument, okay, that is systematic, due to a malfunction, due to a component that is no longer correctly performing and allowing a good reading, an accurate reading to be carried out. For example, a resistor, a capacitance, a diode has worn out, so it would lead to an error within the measurement, like a resistance that has broken off, that measures the temperature. It would display an overheat. Why? Because it has suddenly become an open circuit. Okay? So it would be something within the instrument or the sensors. That would be the systematic errors. Or, for example, the mechanical attitude indicator or altimeter or the VSI, the handle broken or the gyro, okay? The horizontal gyro or accelerometer would be stuck in some way, so it would lead to error in reading. Let us not forget that you have the friction problems, you would have electrical interference, all of that, okay? Now, random errors can be random, like, for example, when we talk about electronic system, okay, you have a binary system that becomes in display as, converted to system of numbers when it comes to readings of different instruments. So it can be fault, a binary fault, for some reason that would lead to an error value, okay? Or it would be a component that at times it's defected, okay, but then it becomes back, it becomes like active. For example, there was a problem once on Turkish airline where you had, I think it was in the attitude indicator, okay, and the altimeter, which is an integrated instrument. So they had a break in the circuit. So at times, due to the vibration, the circuit would be separating. It would show a false reading of the altitude, which is, by the way, this reading is what the autopilot depends on in order to guide the airplane when it comes to the landing. So at times it would break, it would show false readings of the altitude, and at times, due to vibration, it would go back and rejoin the circuit. So that broken circuit, it would contact again, like it would get in contact again on both sides. So it would appear to be working. Why? Because the current is now working, like penetrating properly through this conductor. Okay, so at times, due to vibration, it would separate, acting as an open circuit on the plate, this electronic plate. At times, it would be working properly. Why? Because it's touching and separating. Okay, so this led to false measurements. It brought down an airplane. So again, that would be a kind of random errors. And finally, you have gross errors, like errors that are not only systematic, they are large scale errors, okay? They are multiple things together or on a large scale, something vital affecting the instrument, okay? It's not a minor fault, it's something vital, all right? So we need to understand these errors and the scale of these errors. What systems do they affect in order to be able to troubleshoot and also understand what's happening, and on the ground to replace the part that is malfunctioning with a new part to fix the problem. 2.4 Instrument calibration and limitations. Okay, let's talk about instrument calibration. What is calibration? Calibration is the process of comparing an instrument's output with a known reference standard and adjusting it to that standard in order to maintain accuracy in measurement. Okay, as an example, when we talk about the altimeter, you need to adjust the altimeter to set it at 0 meter, and this would be on the ground level. Okay, we set the air pressure of the static, compartmentalized air within the altimeter. We set it to the air pressure on the ground when the aircraft is still on the airport. That would be the reference pressure, okay? And that would be the 0 meter height of the airplane. From that, okay, now based on that kind of reference, the aircraft, when it climbs in the air, it would be able to accurately measure its height in reference to this static pressure, which is the pressure of the air when the height was 0. This is how the diaphragm within the altimeter would be expanding, okay, in reference to the external air, which of course it will have its own pressure decreasing as the aircraft climbs. But as this external pressure decreases, you would have, due to the differential or the difference between the static air on the ground and this external ambient air, a correct reading of the current altitude. This is why we adjust or we calibrate, okay, the altimeter on the ground. The same thing for the airspeed, the same thing for the entire PITOT-STATIC system. Why? Because all measurements shall be done in reference to that point on the ground, to that current air pressure. Okay, now if you go into a different zone, you would have a different calibration for the air pressure based on which you can get accurate, fairly accurate measurements. Okay, now aircraft instruments are calibrated during manufacturing, maintenance inspections, and after repairs, after repairing. Now, regular calibration ensures compliance with regulatory requirements and maintains measurement integrity. Okay, meaning the measurement should be transparent, should be correct throughout the instrument's service life. Instrument limitations. All instruments have inherent limitations. This may include response time delays, meaning that the value won't be real time. Okay, there would be a delay between the actual value of the air pressure, for example, or the current altitude, and this value being updated on the instrument. It won't be indicated immediately. There's a lag between the current altitude of the airplane and the displayed altitude, to make it simple. The same thing goes for other instruments, but when it comes to the altitude, this is one of the most common problems, or the most common examples where you would have a lag between the current value and the actual displayed value. Also, you have limited operating ranges, meaning that for some airspeeds, they won't be displayed on the indicators, okay? You have sensitivity to environmental factors, so sensitivity to different like changes, like fluctuations and sudden changes in air pressures can falsify the current data being collected. Why? Because it's actually, the aircraft is actually depending on these variables, on these values, okay, to display the current airspeed, altitude, VSI. So changes in air pressure would change these values and display something that wouldn't be accurate at the moment, okay? Even if it's momentarily, it won't be an accurate value. It can be a little bit confusing at times. And also dependence on power sources, meaning that for especially electrical instruments, you would need a consistent power coming from the engine to have an accurate display. So if you have a power cut or an electrical problem or of some sort, or a short, okay, it can give you a false alarm, a false measurement, etc. Now, pilots and engineers must understand these limitations to correctly interpret instrument indications and avoid unsafe operating conditions, meaning making decisions based on false premises. Instrument limitations are documented in aircraft manuals and certification data so that you can follow these guidelines in order to try to understand and interpret a problem when it doesn't make any sense. This is why you go through a checklist when a false alarm fires. It might be false, it might not be, or when you have like an instrument acting up and you don't understand what's happening. That's why we need to go down the checklist. Now, operational awareness. Effective use of aircraft instruments requires not only technical accuracy, but also human awareness to understand quite clearly how they work and why at times they might be displaying values that do not make any sense. We need to understand how they operate. We need to be aware, for example, of the lag, the delay between the actual altitude that you're hitting with your airplane, the actual level, and the altitude, the value of the altitude being displayed on the altimeter at that moment. Okay, so cross-checking multiple instruments, we need to do that, and understanding system behavior under abnormal conditions are essential skills for safe flight operations. For example, we need to verify and cross-check the behavior of the VSI and the altimeter to make sure that they are both positive, indicating a correct climb rate, and also the nose along with the pitch. Okay, if you're pitching 5 degrees and the aircraft is not climbing, you might be entering into a stall soon. And in order to verify that, you need to also be checking the ASI, because at low speed, the aircraft would no longer be climbing. It can enter a stall, which will degrade its lifting capabilities, and that's when you need to correct it, okay, before even the sounding of the stick shaker. That would be the alarm for that that's about to happen. Chapter 3 or Module 3, PITOT-STATIC system, going in depth or in detail into that system, although we kind of covered it before. So what are the principles of air pressure measurement? Because as we mentioned, ASI, the VSI, and the altimeter, the three of them depend on the measurement of air pressure, okay, and the difference between the static air pressure and the dynamic air pressure. Also, dynamic being 1/2 rho v square, the moving air, the pressure of the moving air, and the static external air, okay, like the pressure of the air from the outside. So the difference, yeah, basically, exactly. The difference between the dynamic air and the static air is what gives us the airspeed, the altitude, and the VSI, vertical speed indicator value, or the climb or descent rate. Okay, so the PITOT-STATIC system is a fundamental aircraft system. It is very critical. You cannot go without it. This is how fundamental it is. It is used to measure air pressure and convert it into meaningful flight information. It operates by sensing pressure differences, as we mentioned before, caused by aircraft motion through the atmosphere and changes in altitude. The air pressure in the atmosphere decreases with the increase in altitude, as we also explained prior to this slide, due to the reduction of what? Of the density of the air. So as you go upward, the density, the air density decreases. This is due to the factor of gravity. So as close as the air is to the ground, it would be more dense. Why? Because it's closer to the gravity, to the center of the gravity of the entire, globe. Meanwhile, and due to the rotation of the Earth, the air would be moving like it would be more condensed and concentrated on low altitudes, and then due to the rotation, which generates a centrifugal force, it would be thrown, okay, in lower densities around, it would be scattered around the globe. So as you go up in the altitude, you would have lighter and lighter densities of air, okay, lighter concentration of the air molecules as you go up. Meanwhile, as you go down into altitude and as you close up to the ground surface, like the level 0, altitude 0 of the globe, anywhere in the world, you would have the higher density of air, okay? It would be more condensed due to the weight factor, okay? So it would be weightier and more condensed close to the ground, okay? Again, you have two forces in action here. You have the gravity, which pulls the air downwards, and you have the centrifugal force, which is a force generated by the motion of by the rotation motion of the globe, of the Earth, which pulls everything outward. So these two will make the air molecules more dense, okay, closer to the Earth's surface, and when you go outwardly, they will start to scatter more and more. All right. Now, so air pressure in the atmosphere decreases with increasing altitude due to reduction in air density. Aircraft instruments exploit this predictable variation to determine altitude, airspeed, and vertical speed. The PITOT-STATIC system consists of two primary pressure sources. You have the total pressure, which is static plus dynamic pressure, by the way, and the static pressure, which is the pressure of the closed air within the static source, okay? This is where you have wrapped and sealed the air when the aircraft was still on the ground, on the runway, before climbing, okay, before starting the journey. So these pressures are transmitted through tubing, which is the pitot tube here, to flight instruments where mechanical or electronic mechanisms convert pressure values into readable indications, which are airspeed, vertical speed, and altimeter. Okay, so as we see here in the pitot tube, you have the ram air entering through that tube. Okay, a baffle plate, like the eardrum somewhat. Okay, pitot tube. It's conducted inwardly. You have a heater. By the way, why is the heater, which is in both locations here, heater at 100 watts and at 35 watts, it is necessary in order to prevent icing conditions. Otherwise, that would lead, the icing would lead to the blockage of the tube. So the air would be constricted, which will lead into unreadable data or erroneous data, okay, erroneous airspeed measurements, which would affect the three of these instruments, especially the ASI. Okay, the airspeed would be faulty, which happens once on an aircraft, okay, where one of the pitot tubes were blocked, which drawn down the airplane. It crashed the airplane due to that factor. So now, speaking of which, how does the blockage of the pitot tube affect the airspeed indicator? You see, when you have a blockage of icing in this case, any type of blockage is bad. And this is why, by the way, you have the heater in order to melt the ice to prevent any blockage of the pitot tube. But when you have icing, okay, during takeoff, the airspeed would be very slow, appearing to be very slow, okay? Why? Because the density of the air on ground level would prevent the air from flowing in an efficient way within the tube, depending on how much is the rate of the blockage. Now, the funny thing is that when the aircraft becomes airborne and as the density of the air goes down, okay, this small cavity, which has not been blocked, given that the ice has not blocked the pitot tube at 100%, but this remaining cavity within the tube that is still allowing air to go through it, okay, when you have low density air, it would flow through that cavity at a high speed. That will actually show to you on the display an overspeeding, okay, speed value, an airspeed value way above the actual real speed value, airspeed value. So this is how faulty the indicator would be. So you would be getting an overspeed reading, meanwhile the aircraft is stalling. And this has appeared on that flight, I don't remember which one, a conflicting reading. So you had an airspeed, an overspeeding indication, okay, and then the stick shaker. Why? Because the actual real airspeed was much lower than the one indicated, and the one indicated was too high, okay, was actually overboard due to the fact that the pitot tube that was blocked led to a wrong measurement, a very wrong measurement, giving a very inaccurate and overly high airspeed. Alright, now let's start talking about the static pressure. So what is the static pressure? It is the ambient atmospheric pressure surrounding the aircraft, sensed through static ports mounted flush with the aircraft fuselage, okay, to minimize airflow disturbance. Now, static pressure is used directly by the altimeter and vertical speed indicator, and indirectly by the airspeed indicator. So static pressure is used by the altimeter to measure the difference between the ambient pressure and the locked pressure of the air that is sealed within the diaphragms, okay, the diaphragm, this compartment. So by measuring the difference, we can get the altimeter, and the speed of change of this measurement, okay, the speed of change of the rate or the difference between actual pressure on the outside of this diaphragm and that on the inside, the rate of change would give you the VSI or vertical speed indicator. And finally, you have the ASI, which works based on the dynamic pressure of the air flowing that's pushing against a diaphragm. This push would give you the dynamic pressure, which is Q equal 1/2 rho V square, from which, and given that we know the density, okay, the exact value of the density, you can get the velocity of the aircraft, which is the velocity of air or the airspeed, okay, the same thing, using this very same formula. Pitot pressure. So pitot pressure is the pressure measured at the pitot tube opening facing the airflow. It represents the total pressure, which is the static pressure plus the dynamic or ram pressure, the pressure of the air entering. Dynamic pressure is not measured against a surface, is the pressure of the airflow or the air flowing through the pitot tube, which is again 1/2 rho V square. So the pitot pressure is the sum of both static pressure plus the dynamic or ram pressure created by the aircraft's forward motion through the air. Okay? Total and dynamic pressure. According to Bernoulli's equation for fluid motion, for the motion of fluids, and it's not only aerodynamics. Okay? Aerodynamics is one application, but it is applicable for different types of fluids, such as water, such as different other types of liquids, different other types of gases. So, based on Bernoulli's equation, the total pressure, PT, is equal to static pressure, which is force divided by area, where the force is being applied, plus dynamic pressure, or Q, which is 1/2 rho V squared. Okay? So, to give you an example, imagine the air around a wing. Okay, so the total pressure would be equal to static pressure, which is the force per unit area against the wing, plus the dynamic pressure or the air flowing around the wing, which would be dependent on the velocity of the air and the density, 1/2 rho V squared. So Q, or dynamic pressure, is equal to 1/2 rho, which is the air density, times V squared, which is the true airspeed of the air. So PT, or total pitot pressure, is equal to static pressure plus dynamic pressure. Q, which is the dynamic pressure, is 1/2 rho air density times V squared, true airspeed. This pressure difference forms the basis for airspeed measurement. Again, as we mentioned before, the difference between the ram pressure and the static pressure is what gives us the airspeed and other indicators. The ASI, or airspeed indicator. So how does it work? The airspeed indicator measures the difference between pitot pressure, which is the pressure of the incoming ram air, and the static pressure. Okay? Now, and we mentioned before that internally a diaphragm connected to the pitot pressure expands or contracts relative to the surrounding static pressure. Okay? Now, the indicated IAS, okay, indicated airspeed, is proportional to the square root of the dynamic pressure, correct? So this is basically V equal square root of 2 times Pt minus Ps divided by rho, correct? So if you basically place, if I want to resolve it, this is the application to the same equation that you've seen it before. So we have P total equal Ps plus Q, which is 1/2 rho V square. So you have Pt minus Ps times 2, okay, equal rho V square, correct? So V is equal to the square root of 2 static total pressure minus static pressure, 2 Pt minus Ps divided by rho. This is how you get the velocity. In practice, the ASI is calibrated assuming standard atmospheric conditions, which is done on ground level, as we mentioned before. So it is calibrated based on the air pressure at the ground level, which introduces errors at non-standard temperatures or altitudes. So when the temperatures change or specific altitudes change, it would produce some errors. You won't have accurate results. Why? Because you're depending on, or the dynamic pressure from which you get the velocity, the airspeed, is dependent on the density. And the density, when it changes everything. It changes the dynamic pressure, but it also will change the velocity or the airspeed value being measured within the instrument. That's why you would have an error margin that should be accounted for, and this is why we need to recalibrate the instrument based on these varying conditions. Now, types of airspeed. You have indicated airspeed, which is the value read on the instrument, calibrated airspeed or CAS after calibration, okay, after readjustment, true airspeed, the TAS, okay, which is the real airspeed, the true value, which is rarely the exact value, the 100% value, exact value measured by the instrument, and the ground speed, which depends on the GPS system, okay, and other things. You have also a ground measurement based on a transmitter and receiver that transmits to the ground a signal, then this signal is received back, okay? So by measuring the time it took for the signal to go down then up, okay, and by comparing it with the altitude, you would get what? The distance traveled, okay? Now, before that, so the true airspeed can be approximated from the indicated airspeed using the TAS, or true airspeed is approximately equal to the indicated airspeed square root of rho 0, which is the sea level standard density, around 1.02 kilograms per meter cube at sea level. That would be the nominal air density at sea level, okay, at specific temperatures, divided by rho, which is the actual density at that specific level, okay, the actual density or the current density at that specific height. Now, going back to how do we measure the speed based on, the ground speed instrument, okay? So based on the transmission to the ground method. So you'd have the airplane here, okay? It would send a signal, then it would receive back the signal, correct? So how long did it take the signal to go up and down? That would give us this full distance traveled, and you would have what? The height here, okay? The altitude, which we can get from the altitude. So what we need is the distance from here to here, okay? That distance. So let's say, okay, I'm getting one section here. Okay, so you would have, so how long did it take? So you have this distance over here, let's say, okay, yeah. So d square, we know that d square is equal to h square plus, let's say the travel distance is r, plus r square. And this is how you can get r. R would be the square root of a square plus h square. Okay? Altimeter. Okay. The altimeter measures aircraft altitude by sensing static pressure, correct? It contains one or more sealed aneroid capsules that expand as pressure decreases. Why? Because the difference between the internal pressure, which becomes higher than the external pressure as you climb, as you increase in altitude, as the aircraft goes up in altitude. So the difference between the internal pressure within the diaphragm and the external pressure increases, which makes the diaphragm, okay, or causes the diaphragm to expand. Why? Because the pressure on the inside has become greater than that on the outside. So it dilates. And as it dilates, it rotates. You know, you have like a gear. It rotates this handle that turns the gears, which is in its turn connected to the needle that measures the altitude. Okay, that goes for the mechanical instrument. Okay, mechanical type of instrument. So the relationship between pressure and altitude in the international standard atmosphere ISA can be approximated by. Okay, so h or altitude is equal to T0, which is the temperature at sea level, divided by L, which is the temperature lapse rate. Okay, the temperature excursion. Okay, how much the L is has a lapse. Okay, the different temperature being measured, multiplied by 1 minus PS over P0. PS is the static pressure at that altitude, divided by P0, which is the sea level pressure, okay, to the power of R L divided by G. G is the gravitational acceleration or gravity. Okay, R is the specific gas constant of the air, and multiplied by L, which is the temperature lapse rate again. So now altimeters require barometric setting adjustments to account for local pressure variations, commonly set as QNH or QFE or standard pressure, which is 1013.25 HPA. Okay, so they need readjustment in order to keep them producing accurate results, accurate measurements. I feel the need to reiterate on this formula because it might look a little bit ambiguous or hard to understand. I felt that we have passed over it a little bit too quickly. So again, this is how the altimeter would display for us the current altitude of the aircraft based on these parameters. These are the parameters, or at least some of them, that I've seen or perceived as a little bit complex to understand. Okay, little bit ambiguous. So h, which is the altitude of the aircraft, is given by T0 or sea level temperature divided by L. L is the temperature lapse rate, or in other words, how much is the temperature changing per unit altitude. In other words, to make it simpler, how much degrees is it changing per kilometer. So let's say you have a change of 0.005 degrees Celsius per kilometer, or degree Kelvin per kilometer. I'm not sure about the international system unit being used here. That would be the lapse. Okay, so it would be 0.005, and you place it within this equation. Okay, multiplied by 1 minus PS over P0. PS is the static pressure within the compartment, within the diaphragm, the current static pressure, okay, which will expand, okay, it would change due to dilation because of the external air having a lower pressure than the one that is locked or sealed within the diaphragm, okay, that has been sealed from the ground level. So PS is the current static pressure divided by P0, which is the pressure at sea level, okay, to the power of RL divided by G. R is the gas constant, we know it, okay, each gas has a constant, multiplied by L, which is the temperature lapse rate, divided by G, which is the gravity or gravitational acceleration. VSI or vertical speed indicator. Now, as we probably have already mentioned, that the VSI or vertical speed indicator measures the rate of change of static pressure, not the difference between the static pressure and the sea level pressure, okay, the actual PS and P0 at sea level, but rather the rate of change or the speed of change, okay, providing the aircraft's rate of climb or descent. So the VSI operates on the principle VSI value is proportional to the derivative or the rate of change, in other words, of the static pressure, okay, of the static pressure in respect of time. So it's delta PS divided by delta T, or P final during a span of time, P final minus P initial, divided by T final minus T initial, okay? Which again, it can also be looked at because it is the derivative of the pressure in respect of time, or in other words, less technically, it is the change, the speed of change of pressure in respect of time, the static pressure mainly. Now, so you have a calibrated leak which allows the pressure changes to lag within the instrument in order to be able to measure, okay, the difference between the actual static pressure and or the static pressure at this moment and the former static pressure. So for us to have a former static pressure, you have the need for a lag, like a little delay between the current pressure, okay, and the former pressure. So the current pressure of the air sipping outside from this bleeder, this calibrated leak, okay, the current pressure at this moment, and yeah, the former pressure from moments ago. This is how you measure the change rate, okay, of the pressure from which you can get the VSI. Now, by the way, how it works is that you have, let's say, if you're climbing, during the climb, the diaphragm would dilate, okay? So this dilation, this expansion would make the pressure of the air at that moment less than the static pressure that was formerly on the inside. So this motion, this lagging motion is what will move the needle, okay? And it will move it upward to display or indicate a positive rate, okay? So a reduction of air pressure would cause a positive rate, or the needle moving upward positively, indicating that the aircraft is climbing. And the opposite, you know, is you can reciprocate for the opposite, meaning that during the descent, what will happen is that the diaphragm would collapse under an increasing pressure, okay, which will cause also the needle to move, but this time it will move downward, okay, due to increased pressure, it will move downward, indicating a descent, okay, and how much it has moved, it will indicate a descent rate as long as this pressure is decreasing. Now, once the change of the pressure had stopped, the needle would stabilize again, or it would be leveled again to 0, okay, that would display or reference a leveled flight. Now, this leak is important for the needle movement, okay? This lag created by the calibrated leak is the reference, okay, is the action by which it is allowed, like the instrument is allowed to have pressure changes okay, that will actually affect the needle to rotate one way or another, causing the pressure differential across a diaphragm that drives the needle to indicate whether positive climb or negative climb. However, there's a trade-off. There's a compromise here. Due to this design, the VSI exhibits a time delay, typically 6-9 seconds, which is a delay between the actual altitude, okay, the actual vertical speed that the aircraft is experiencing versus the displayed or indicated vertical airspeed. So you would have a difference between the actual vertical speed during the climb or descent and versus the indicated one. Okay, so the indicated VSI value would need or require a little bit more time, some few seconds, up to 6 to 9 seconds, to be updated to the actual real value. That's the problem, okay, between a change in vertical speed and indication. So there's a trade-off, but this is the problem, that the VSI actually works using the bleeder, using the calibrated lead. That despite the fact that it induces a typical delay of 6 to 9 seconds, this is how it works in order to display the VSI value on, the instrument or on the indicator via the needle motion. Now, common errors and failures. Okay, let's talk about that. So, at first, we have pressure and instrument errors. Okay, for example, PITOT-STATIC instruments are subject to several error types. For instance, you have position error due to airflow distortion. You have miscalibration also on the ground level of the PITOT-STATIC system. Instrument error from mechanical imperfections, because as we know, you have the diaphragm motion is what we rely upon to measure different things, these different parameters such as VSI altimeter and the airspeed. So a mechanical fault within the instrument can lead to a misreading. Okay, it can break in flight at times. Nobody knows. Okay, so density error caused by non-standard temperature, also another factor. So a difference of density or density error due to a temperature that's not common. Okay, for instance, you have a phenomena above the desert. Usually you would get a hot air above a cold air which would be close to the ground. Okay, so an inversion may occur. Usually you have the cold air above, okay, and a hot air below. So this is what you're getting. You're getting a different false measurement. Lag during rapid altitude changes. So this lag due to sudden fluctuations of pressure, okay, would cause a misreading in altitudes also. Now, another factor is the blockages and leaks. So blockages in the pitot tube or static ports can result from ice, insects, or debris. We had that problem happen multiple times. Like, actually, there was an incident in which the pitot tube, I referred to it in former slides, it was blocked due to an insect that formed its own, like a fabric, like a housing for itself within the pitot tube, which led to the aircraft going down due to the misreading of the airspeed. So this blocked pitot tube causes the ASI to act as an altimeter during climbs or descents. Okay, so a blocked static port affects all pitot-static instruments. Leaks in the system lead to sluggish or incorrect indications and can severely degrade instrument accuracy. So leak within the diaphragm, for example, not the acceptable leak within the VSI, but if there's problems like that, these leaks would cause us to have a wrong difference between the static pressure, okay, the actual current static pressure, and the sea level pressure, okay? So it would lead to wrong measurements, correct? And the system would be, acting or giving sluggish values or incorrect indications, okay? Can severely degrade instrument accuracy again. Icing effects. One of the most serious problems that can occur, and it will seriously affect readings in instruments, not only, by the way, the instruments. It affects the entire airplane, especially introducing drag on the wings, and it can lead to stall by reducing the lift and increasing the drag factor on the wings, okay, deteriorating the wing characteristics, okay, and converting a laminar flow into turbulent flow. This will kill the lift force that is supposed to be pushing the plane upward, okay, and keeping it in the air. So icing effects. The icing is the one of the most hazardous PITOT-STATIC failures. Ice accumulation can block pressure sources, leading to false airspeed and altitude readings. We've already covered that. PITO heating systems should be introduced, and they are installed to prevent ice formation both on the front and the back, and ensure reliable operation of the instrument, the PITO-STATIC system altogether, even in icing conditions, which is very important. Operational implications. Pilots must cross-check PITO-STATIC instruments and recognize failure symptoms if the readings don't make any sense. Okay, for instance, they need to check these values promptly, and understanding system principles allows correct diagnosis and troubleshooting and safe continuation of the flight even under abnormal conditions by looking at the indicators, because since you have a redundancy, you can look at the indicators that seem to be working properly and normally, and these would be the indicators or the instruments that are the backup that you would rely on in order to continue the flight instead of going or referring to the main system that has a defect. Let's say one of the PITO-STATIC systems or the PITO tubes to the left or to the right has been blocked. Okay, you should isolate the problem, and by the way, you should also deactivate the autopilot, especially if it's getting its reading from the faulty PITO tube. Otherwise, it can bring down the airplane. So you would need to rely on the other instrument and then go back. It's preferably go back to the runway, to the airport, in order to fix the problem. Chapter 4 or Module 4, Gyroscopic Instruments. Now, we're talking here about the attitude indicator, okay? Concerning this part, the gyroscopic instruments, which is mainly the attitude indicator, we've already covered a little part of that in the intro, and we've explained how it works. Okay, so there might be a repetition, but follow through. It would be beneficial to get it on a deeper level in case it didn't make much sense before. Hopefully it would be more understandable this time. Okay, now as we see to the right, you have the anatomy of the attitude indicator made of the gimbal here, okay, the raw gimbal which rotates based on the bank of the airplane. You have the gyro, which is the part that as it accelerates, okay, as it rotates, it will remain on the horizontal position, okay, parallel to the horizon. That would be the reference, okay, and it will keep with it the horizon reference arm, which would be the reference based on which you can observe by looking at the attitude indicator whether the airplane is going up or down, or pitching up and down, or if it's rolling to the left, to the right, and at which angle. the angle of rotation is also called the bank index. Okay? Now, so again, as we mentioned, this part, the gyro, will keep rotating, maintaining this arm horizontally, okay? And as the airplane moves up or down, so if it moves up, okay, this part here, okay, this, or rather, let me say this, yeah, this part would be going down because this will be maintained upward, this part, okay? This axis, which is the horizon reference arm, would remain fixed, and the disc here would go downward if the nose of the airplane is pitching up, meaning it will place this orange line on the blue disc, on the blue part of the disc, indicating a nose up. Meanwhile, during a dive, it would go upward, which means that the orange line, it would be placed on the brown area, indicating that the nose is pointed to the ground. It's pitching down. Also, during roll, the horizontal arm would remain fixated by the gyro because it's rotating at high speed. So this arm would remain fixed. However, the entire instrument, like the roll gimbal, yeah, the gimbal would rotate, okay, indicating a bank between the attitude indicator or the airplane and the horizontal line, horizontal reference line. So gyroscopic instruments operate based on the physical behavior of a rapidly spinning mass, which is the gyro over here. A gyroscope consists of a rotor mounted in gimbals. These are the gimbals here, the pitch gimbal and the roll gimbal. Okay, so the aircraft would be rolling in reference to the gyro to the right and to the left. That would be the roll gimbal rotating right-sided, or to the right side or to the left side, to indicate the bank angle of the aircraft in respect of the horizon, and the pitch gimbal, which is to indicate the up down pitch, okay, or the nose up nose down movement. So when spinning at high speed, the rotor exhibits unique properties that are exploited in aircraft instruments. Okay, so the rotor, the gyro mainly, would be guarding its horizontal reference, okay, its horizontal position, and the gimbals would be, for the roll gimbal, rotating right side, okay, to the right side or to the left side, and the pitch gimbal would be rotating up and down in reference to this gyro. And this is how you get the indications of pitch up or nose up, nose down, and the rolling or banking angles. Now, the fundamental quantity governing gyroscopic behavior is angular momentum or angular speed, defined as L is equal to I, which is the moment of inertia, multiplied by the angular velocity. In other words, how many radians per second. Okay, how many radians per second this is rotating, the gyro is rotating. These are the quantities to be accounted for. So I multiplied by W would give us the angular momentum. A spinning rotor resists changes to the direction of its angular momentum vector. All right, so the spinning rotor, which is the gyro, it would resist the changes of bank, the changes of pitch. So the bank would be the right and left rotation of the rotating gimbals. As for the pitch gimbal, okay, it would be rotating downward and upward, not right side and left side. So this would be in reference to the rotor, giving us the measurements for the rotation gimbal. It would give us the bank, again, the angle at which the airplane is rolling to the left or to the right. And for the pitch gimbal, it would give you the degrees of nose up and nose down. So how many degrees is the airplane forming with the horizon when it's nosed up or when it's nosed down? Okay? Now, the thing is, which is the advantage and the necessity of the rotor, is that due to its rotation or rotating movement, it will keep steadily, okay, a rotation in reference to the horizon because it has been rotating in that direction, so it will remain steady and parallel to the horizon plane, to the horizontal plane, which is the ground plane, okay? It would remain parallel to the ground, and that would be the reference in respect of the bank angle and in respect of the pitch up, pitch down motions. So that would remain as our reliable reference plane against which we measure these other parameters again, such as the roll and the pitch. Okay, so it remains stable. It forms the basis for stable reference instrument used in aircraft attitude and direction sensing. So again, you have here the spin axis, the rotor on the inside, and two gimbals, okay? That would be again the pitch up and down gimbal, I believe. I'm sorry, that would be the roll gimbal, okay? And that would be the pitch up and down gimbal. All right. 4.2 rigidity in space and precession. Let's start with rigidity in space. So what are we exactly talking about? Rigidity in space is the tendency of a gyroscope or the gyro, the rotating gyro, to maintain the orientation of its spin axis, the axis around which the rotor is moving, it's turning, relative to inertial space, regardless of the aircraft motion. So in other words, whether the aircraft is rolling, it's banking, it's pitching up or down, the gyro will maintain the same heading, the same plane, okay? So the axis, in other words, the axis would remain fixated on the same orientation. It won't roll, it won't bank, okay? It will remain fixed thanks to a rotating gyro around it. So it will stay rigid in space. It doesn't matter what the aircraft is moving, where its attitude is going, okay? So whether the aircraft is banking or rolling or pitching up or down, the horizontal gyro, the gyro rotating horizontally, would remain steady and maintain the same axis of rotation, okay? So it will stay in the same position. This is what rigidity is referring to. So in other words, this property allows gyroscopic instruments to provide stable references for pitch up and down, for roll and heading as well, because this same gyro is used within the directional indicator, like the compass, so to speak, okay? Directional gyro, in other words. Now, the effectiveness of rigidity in space increases with a greater angular momentum. So it will remain more solidly fixated in the same direction, or in other words, the axis of rotation, it would be more rigid, more stable. So in effect, it will provide more accurate measurements when you have a higher angular momentum, when it's rotating at higher speeds, which is achieved by increasing rotor mass or rotational speed, okay? Because the rotation has to do with the mass, okay? With the, the potential force. When you have a heavier rotor, it would stay more stable, more rigid in space as it rotates, okay? Because, by the way, the inertia, which is the I, okay, rotation moment, the I is equal to mr squared, okay? So when you have a thicker mass, it would rotate with a good inertial force, okay? the moment, that's the rotation moment. And when you have a longer radius, which if effectively, okay, it will affect the mass as well, or when you have a higher rotational speed. So any external force attempting to tilt the gyroscope must overcome its stored angular momentum to affect the reading of the indicator on the inside, which is the purpose of having higher angular momentum so as to guarantee a stabilized reference plane within the gyro, okay, to provide, in order to provide accurate measurements when it comes to different parameters that we've tackled before, that we've referenced before. Gyroscopic precession. So what is this phenomena about? When an external torque is applied to a spinning gyroscope, here it is represented as a wheel, and this is the external torque that is causing the rotation of the gyro. All right? The pull, and this is a weird phenomena because the direction of the applied force, that you would suppose it would be the same direction of the torque itself, but instead the direction of the applied force would be 90 degrees in retard to the torque vector, okay? It would be at the right angle with the torque force. Instead, that would be the L vector that is illustrated in this picture. So this phenomena is called or known as the gyroscopic precession, in which the wheel, when it's rotating, okay, it would start to be pushed sideways instead of being pushed in the same direction of the rotation, or within the same plane of the rotating disc, which is very interesting. So, given an example, you have the rotating wheel here, which is spinning counterclockwise, meaning in the opposite direction of the clock needles. So, how to determine the direction and orientation of the force vector, of the precession force vector, which is also another name for the angular momentum direction. You would have, this is how you get it. So let's say it's rotating counterclockwise. We apply what is called the screwdriver method. In case, imagine that you are removing a screw from the wall, okay? The screwdriver would be rotating counterclockwise. However, the movement, the forward backward motion would be going back, okay? The motion of the screwdriver itself, other than rotating, it would be moving backwards along with the screw as you remove it from the wall. Meanwhile, the opposite, okay, the contrary of that would be the opposite direction. So in case the wheel is rotating clockwise in the same direction of the clock needles, so if you imagine the screwdriver and the screw, they would be rotating clockwise, and it would be pushing the nail or the screw forward within the wall along with the screwdriver itself. They would be both going inwardly toward or in the same direction of the wall. So it would be an inward force. So you notice that you would have an applied force, instead of being intuitively in the same direction and plane of the rotating wheel or gyro in our case, instead, which is counterintuitive, it would be applied sideways, 90 degrees to the torque itself. Only what is parallel to the torque force is the delta L, which is the change of the angular momentum. So the quantity by which we measure that gyroscopic precession is omega p, which is the precession angular velocity, is given by the torque, the applied torque that is causing the rotation of the gyro to begin with, divided by L, which is the angular momentum. Now, in aircraft instruments, controlled precession is intentionally used to align or indicate motion, okay? So when you have a controlled precession, it would show us, like, I think, yeah, it can be used within the turn indicator. It's used in the turn indicator to indicate that the aircraft is turning. Okay, now by the way, there's a slight difference. We don't want to mix the keywords. There's a difference between banking and turning. Okay, because the aircraft might be banking, so it might be rolling at a certain angle, 10, 20, 30 degrees, but not necessarily turning. It would be going like this. Of course, now, since the weight itself become divided into two components, vertical and horizontal, it would start turning the airplane. But initially, it is banking, not turning. In order to make the turn more effective, you need then to apply the rudder, and this is when the plane would actually be yawing, going to the right or to the left, along with the banking motion. Actually, during the landing, in order to correct the heading of the airplane, the pilot usually only applies the rudder when you have a crosswind in order to stabilize or like to make sure that the nose is centered to the middle of the runway. He won't apply any aileron controls. The rudder would be the only thing that would be manipulated in such case. So, in the turn coordinator, and when indicating if the aircraft is going to the right and to the left by manipulating the rudder, like the measurement of this turn would be received or would be measured based on the gyroscopic precession being applied to the fan, especially when you have the small airplanes such as the Cessna, okay, because when it turns, you would have the force being applied to the rotor. This is how you get values in the turn coordinator, in the turn measurements, okay, by measuring the force being applied to that rotor. Now, another thing, you have precession that would occur in instruments, but it's not favorable. Why? Because it would cause reading errors within the instruments and drift. For example, when you have the gyroscope, okay, due to the turning of the gyro, you would have a precession that will move the gyro along with horizontal arm, upward and downward. Okay, it has the tendency to do that. Meanwhile, it is not favorable. Why? Because I would need to have the gyro rigid and solid as possible. Why? Because this is the reference point for the roll and pitch. So I would want anything to move except that specific part. Now this is another illustration for the gyroscopic precession. Okay, if we see here, let's say you have a motion of a wheel rotating about an axis. Okay, now why do we have this axis seeming to be stranded or stretched in one way or another? This is a representation of the effect of the force that's pulling this axis in a specific direction. And this usually happens like this distortion, okay? Or not distortion, like, distortion of this axis is due to the fact that when this rotating wheel, for example, that's being held by this girl, if the girl would try to move it right-sided to the right side, the right side direction or to the left side direction. So if this girl would try to rotate the wheel, and I'm not talking about the original rotation motion that's already going. I'm talking about this girl moving her right hand backwards and her left hand pushing it forward, rotating the wheel like this, okay, in the in the horizontal direction. It's rotating in the vertical direction, correct? If she wanted to rotate it, to move it like this, it would resist this movement. Why is that? And we've already discussed and talked about this resistance of a gyro to be bent in one direction or another. Okay, why is that? Because it's already rotating, so you have a force, which is the gyroscopic precession, pulling it in a specific direction. If you try to change, like if you try to move it, to rotate it horizontally, like to change its heading, the heading of the plane in which the wheel is turning, it would resist you. Why? Because you already have a precession force pushing it, in a specific direction. So you are going against that force, it would resist you. Okay? Why? Because it's still pulling in one direction and you're trying to counter it by making it pull in another direction. So when the wheel is turning at much higher speeds, this vector would be much stronger. It would even resist you more from and prevent you from turning the wheel, okay, from changing the direction of the wheel. This is basically the gyroscopic precession. I hope it became clear in this slide. Now let's go back to the attitude indicator. So the attitude indicator, AI or ADI, attitude directional indicator, also known as the artificial horizon. That's another keyword, by the way, which is important. It provides the pilot with a visual representation of the aircraft's orientation, okay, relative to the horizon. And the horizon would be guaranteed as a reference by the gyroscope, the rotating gyroscope, as we mentioned before. It displays pitch. Pitch is nose up and nose down, and roll information, and is one of the most critical flight instruments. Now, as a reminder, the pitch is, for example, here you have a leveled flight where this orange line is at the center of the disk, okay? It's neither in the blue zone nor in the brown zone, which means that the aircraft is flying level. It's neither pitching up nor down. It's horizontal to the ground. Now, when it goes upwards, and here you see these sticks, these dashes, you can actually get, by reading these dashes, the angle, the current angle of pitch, whether it's positive, if it's climbing, if it's nose up. So that line with this orange dot would be in the blue part of the disk. If it's nose down, which is pitching down, it would be in the brown area. That is, the measurement or indication of the pitch. As for the roll, this is the roll. So if you have a roll to the left, let's say, by 15 degrees, I think this would be 15 degrees, okay? So the orange line would be like this. That would be roll to the left of 15 degrees. All right? Now, you can have both a roll and the pitch at the same time, by the way. So the ADI typically uses a gyroscope with 2 degrees of freedom, meaning that it can go up and down to indicate, not the gyroscope is what goes up and down, but the area, the gimbal, the pitch gimbal that goes up and down, because the gyroscope disc would be rigid. This is the stable and fixed part of the entire instrument. And the other degree of freedom is the rolling. Okay, so the rotating gimbal would rotate around the gyro to indicate the roll angle or the bank angle, whether it is, you have the bank angle and the pitch up and down. Okay, these are the 2 degrees of freedom, allowing the rotor to remain fixed in space while the aircraft moves around it. Okay, this is the necessity and importance of the gyro. The instrument case, the casing of the instrument, is connected to the aircraft, correct? Causing the horizon bar to appear to move relative to the aircraft symbol. Now, what's happening is, this is what is moving around, okay? Not because it seems to us that the aircraft symbol, which is the original line, the orange line, it appears to us that this is the part that is moving, but the reality is this is the stable or fixed part, and everything is moving about it, okay? So the external, or like the surrounding blue-brown disk, is the part that is moving around this reference line. So the instrument case is connected to the aircraft, causing the horizon bar to appear to move relative to the aircraft symbol. Now, Due to gyroscopic imperfections, the attitude indicator is subject to drift, okay, and must be periodically realigned. Okay, it would drift from its original position. Most instruments include erection mechanisms that apply small corrective torques to maintain the vertical alignment, okay, so that it will remain aligned correctly. Why? Because as it drifts, and why does it drift? Due to gyroscopic precession, the actual gyro would start drifting from its position due to these forces pulling it upward or downward. Okay, so in order to maintain correct measurements, we need to readjust it from from time to time, every now and then. Heading indicator or directional gyro, which is DG for as a short notation. It provides directional information based on gyroscopic stability rather than the magnetic north of a compass, okay, or magnetic sensing, in other words. That's why it is less prone to errors. It is less susceptible to acceleration and turning errors, which can erratically displace the needle pointing to the north. Okay, so it's more stable, more reliable, more accurate. Okay, why? Because it is based, or like it relies on the directional or the rotating motion of a gyro, directional gyro in the vertical plane, which becomes the reference point of all headings within this directional gyro instrument. Okay, so this is how it basically works. The directional gyro operates with a gyroscope, again, constrained to rotate about not a vertical axis itself, like the gyro itself is rotating in the vertical plane about an horizontal axis. This is the error here. Okay, so the axis itself is horizontal, but the rotation plane, the direction in which this gyro is rotating, is vertical, which is opposite to the horizontal gyro within the attitude indicator, where it rotates in the horizontal plane, but the axis itself is vertical. So again, the directional gyro has like a rotation in the vertical plane, but its own axis is horizontal. And through its rigidity, okay, in space, it provides a stable heading reference, and compared or against this reference, all headings or all turns of the airplane would be measured to like assess the current heading. Okay, all would be referenced to that stable, rigid, vertically rotating gyro. Now, however, remember that this reference cannot be solid 100% due to Earth rotation and other mechanical imperfections, like, for example, the gyroscopic precession factor. It would start drifting away from the magnetic north. Okay, so once you stabilize it in the beginning to the magnetic north, okay, it's reliable, but after a certain amount of time, it would start incurring errors. So it needs to be resynchronized to the magnetic compass. That's the only problem with the directional gyro. However, every now and then, when it's synchronized with the magnetic sensing compass, it would produce great results. Now, the apparent drift due to Earth's rotation is approximately omega E is equal to 15 degrees multiplied by cosine phi per hour. That would be the drift. And phi is the latitude. Okay? Phi would be the latitude, or like the position on the Earth. Okay? Horizontally. That would be, again, yeah, like it's a reference angle, okay, on positionally on the face of the Earth, okay, in respect of an original reference position, which I think, yeah, in the middle somewhere of the globe, okay? That would be the latitude. Actually, the latitude is measured in reference of a middle point. I'm not sure if it's Greenwich or something, okay? But you get what is being inferred here, what's being referred to. Turn and slip indicator and turn coordinator. Okay, so this device, turn and slip indicator, uses a rate gyroscope that responds to yaw rate. Yaw being when the aircraft's rudder is turning to the right or to the left, pushing it sideways, okay? So it's not the rolling itself. It is neither the banking and rolling are the same thing. It is pushing the aircraft sideways like the rudder of a ship, okay? The rudder of the ship doesn't rotate the ship, remember. It moves it sideways, either to the right, if the rudder is going like this, it moves it to the right. Why? Because the water would be pushing the tail to the left. Or the exact opposite, if the rudder is going to the left, the air would push it to the right, would push the rear end or the tail of the ship, so to speak, to the right, which is called the stern, by the way. So the heading of the ship would be going to the left. It would be turning or leaning to the left. All right? This is how it works. So this is the yaw. Now, the gyroscope is mounted so that the precession occurs. Remember, we've spoken about the precession being the measurement tool, okay, like the measurement parameter rather, by which we can assess or like collect the data on the rudder movement and whether, like how much, not the rudder movement, but the movement of the yawing of the airplane. Yaw means the left or right movement, like the side right movement or left movement, again, just like the rudder of a ship. So the gyroscope is mounted so that the precession occurs in response to aircraft rotation about the vertical axis. The rate turned is proportional to angular velocity, okay? That would be the rate turn. So angular velocity, the turn rate, I'm sorry, omega is equal to the true airspeed divided by the turn radius. That would be the turn rate, okay, or angular momentum. So omega equal V, which is the true airspeed divided by the radius of the turn, V over R. A bow in tube inclinometer indicates slip or skid by showing lateral acceleration. So you would have here a bow, okay, within a tube, inside a tube, inclinometer, okay, which is inclined. That would indicate if the aircraft is slipping or skidding. So if it's not turning properly, it would be slipping sideways. Meanwhile, okay, because why? Because if it's rolling but at the same time yawing, that would be on the center line. Why? Because it would be kept centered by the gravity. Meanwhile, if the aircraft is slipping sideways without rolling, so if it's not turning correctly, if it's only yawing, this would be indicated by the movement, the side movement of this ball within the tube to the left or to the right. Okay? The turn coordinator improves upon the turn and slip indicator by sensing both roll and yaw rates. Okay? Its gyro is tilted relative to the longitudinal axis, allowing earlier indication of turn entry and exit. The turn coordinators provide better situational awareness during instrument flight and are particularly useful during standard rate turns. So if we go back to the image here, this is the turn coordinator. You would have a banking here during a roll, okay? So it would indicate how much it is turning, how much it is banking to one side or the other. All right. So it provides better situational awareness during instrument flight so that the pilot can be well aware on the angle or how much is the angle of the turn, if it's acceptable or if he's going above what is an acceptable limit for the bank angle. Okay, if he's going like above the acceptable thresholds during a turn, whether to the right or to the left. Now let's dive deeper into how the turn and slip coordinator works. So at first, the turn and slip coordinator is not meant to measure the banking angle of an aircraft. It actually is used to measure three parameters, which are the direction of the turn, okay, the amount of the turn or the rate of the turn, that's second, so the direction, left or right, then you have the rate of the turn, how much it is turning, okay, how much is it banking, not the degree necessarily, but how much is it banking, that's second, and third, the quality of the turn. So if it has a slip on the inside of it, okay, if it's slipping or if it's turning correctly. If the aircraft is turning properly, so to speak, following a specific direction or changing heading to another heading, let's say from 30 degrees to 40 or 90 degrees azimuth. The azimuth is the horizontal angle, by the way. If it's turning properly, then it would be indicated within the inclinometer by this black ball that is within this tube. This ball would remain on the center position, okay? But if it's skidding, if it's slipping, it would be going leftwise, okay, or rightwise. That ball at the center. Now, going back to the anatomy of how it works, we need to dissect like the inner parts of the turn and slip coordinator. If you look at this picture to the left, okay, that would be the turn coordinator. So you have the gyro rotation, which is, by the way, inclined 30 degrees. If it's not like perfectly vertical, it's inclined at 30 degrees so as to detect two parameters, two changes, both the turn and the yaw. Yaw meaning if the aircraft is like heading rightwards or leftwards, like the rudder of the ship, okay? What the rudder of the ship does, this is the yaw. It yaws the ship, it doesn't roll it. It yaws it to the right or the left. Now, again, this gyro is tilted 30 degrees, so it would be sensitive to both the yaw and the roll of the aircraft, and this is detected through gyroscopic precession. Again, you remember we referred to gyroscopic precession, where a rotating disc, due to its rotation, it would incur a force that it would be counterintuitive. You would think that the force would be going in the same vertical plane of the disc, but instead it would be pulling it sideways, 90 degrees from the direction of the rotation. Okay, so that would move the needle, which will be how the detection of the roll and yaw would occur. Okay, the precession itself would move the needle so as to indicate the roll and the yaw. This is basically how it works. This is when, if you remember, we referred to the gyroscopic precession as an important factor that would affect the roll and the banking, okay, within the instrument. You have here the turn and slip indicator, also another like the same thing, okay, a different flavor. You have the gyro tilted, like you would have the gyro rotation, it's tilted 30 degrees to detect both yaw and rotation or rolling. Vacuum driven versus electrically driven gyros. Here we're talking about different types of gyros. Let's start with the vacuum driven gyro. The vacuum driven type uses air suction in order to spin the rotor, typically powered by an engine driven vacuum pump. Okay? These systems are simple and lightweight, but vulnerable to pump failure. If the pump fails, then the entire system or instrument would fail. That is depending on the gyro or the rotation of the gyro, the gyroscopic motion. Okay, so in case of pump failure or contamination, the system would fail. Loss of vacuum pressure results in the gradual degradation of the gyroscopic indications, often without immediate warning. So it would gradually fall, okay? It would gradually start veering off course until it, the indication becomes completely erratic, but it would be a little bit late before you realize that the actual instrument had failed, because it is gradual and without any prior warning system. Electrically driven gyros. Now, electrically driven type uses electrical motors that would be powered by a current in order to spin the rotor. They offer more consistent performance, more reliable, faster startup times, so it would prime much rapidly than the vacuum driven ones that heavily depend on the air suction by a vacuum pump. This is how they work. Okay, and they have an improved reliability, especially in multi-engine and modern aircraft. So electrical gyros are better suited for integration into electronic flight display. Why? Because you can actually detect a malfunction in this type because it's driven by power, by electricity, and can be powered by redundant electrical sources. That's the beauty and the advantage of it. Meanwhile, compared to the vacuum type, the vacuum driven gyro, first of all, you don't have a warning system that can detect that the instrument had actually failed due to loss of the vacuum pump pressure. Okay. Second of all, it's not completely reliable due to contamination, and it doesn't have an enough past prime time. Meanwhile, for the electrically driven gyros, when you have a fault, it can be detected immediately on your instruments, on the display. Now, the operational comparison. Understanding the differences between vacuum and electrically driven gyros allows pilots and maintenance personnel to anticipate failure modes, to anticipate the failures before they take place, and understand how these two different types can fail, and apply appropriate emergency procedures to troubleshoot the problem or to execute a swift landing, an emergency landing. Modern aircraft increasingly rely on electrically driven and solid-state gyroscopic systems to enhance reliability. Okay, so you can count on it. It remains consistent and stable throughout the flight, and safety, because you have early warning systems when you have an abnormal functioning or a detection of a fault. Chapter 5 or Module 5, Magnetic Compass and Direction Systems. We kind of scraped over this subject before. Let's see what further details can we learn from them. Okay, so magnetic compass and direction systems. Starting with Earth's magnetic field basics. The Earth behaves like a large bar magnet with magnetic field lines emerging near the geographic South Pole, correct? And entering near the geographic Northern Pole. So it behaves like a magnet with a South Pole which is the southern part of the Earth, the southern, the southern pole. And you have the North Pole, that would be the magnetic north of the Earth, to the north all the way to the North Pole, okay? Now, this magnetic field provides the fundamental reference direction for magnetic direction systems used in aircraft navigation, which is very important. Like, it is critical and necessary. You cannot excommunicate that or throw it aside. You have to truly 100% rely on these directional references, especially the magnetic reference, okay? So the magnetic field at any point on the Earth's surface can be resolved into two components. You have the horizontal component, okay, and the vertical component Z. So the magnetic field has two components, the horizontal one, okay, which is parallel to the Earth's surface, and the vertical one, which has to do with altitude, okay? It would be pointing, because you see the magnetic field is, you know, it can change through terrains. And when we talk about the North Pole of the Earth, it's not like a flat surface. You have mountains, you have different things, okay? So the total magnetic field is actually the square root of the square value of the horizontal component and that of the vertical component, which is the theorem of Pythagoras, okay? Pythagoras has provided this theorem. It's like a rectangular triangle, okay, where you have, this is B, okay, and you have the H component, horizontal component here, and the vertical component here. So B is the resulting vector of both. This is how we get it. Now, of course, the angle between the magnetic field and the horizontal plane is known as the magnetic dip angle, or delta. So this is how you get it. Let me draw it a little bit, okay? So you have Z is the vertical component of the field, and H is the horizontal component, correct? So delta, which is the angle called magnetic dip angle between the magnetic field B and the horizontal plane, which is H, okay? This is the angle. So here, the angle delta is the same as here, okay? You know that. Why? Because these two lines, this one and this one, are parallel. Okay, so what is the value of delta? We know tan delta. The tangent of delta is given by the opposite segment, which is H, okay, the value of H, the horizontal field magnitude, divided by, okay, the vertical component of the field, okay, which is Z. So it is the opposing or the opposite segment divided by the adjacent segment. This is how we get tan delta. This is all the way back to the calculus class, okay? So H over Z. So delta would be the arc, or delta would be the arctan of tan delta, okay? So it would be the arctangent of H divided by Z. And again, as a reminder to go back to how we got the value of B. So this is the theorem of Pythagoras. You have B squared within the rectangular angle, rectangular triangle, sorry. B squared is equal to H squared plus Z squared, correct? So this is B. Here you have is equal to Z square plus H square. Hence, B, which is the magnitude of the magnetic field, is equal to square root of H square plus Z square. That would give you the final value. Okay, now, near the magnetic equator, the horizontal component dominates, while near the magnetic poles, the vertical component becomes more significant. Okay, the variation directly affects the compass behavior. Magnetic compass construction and operation. The magnetic compass is a simple, self-contained direction sensing instrument that senses the direction based on the magnetic field. It requires no external power. This is one of the advantages. So it can operate standalone without any feed, without any external power. It consists of one or more magnetized needles attached to a lightweight compass card, and the needle would rotate to point to the magnetic north. Okay, it's mounted on a low friction pivot, which is necessary so as to guarantee that it would move freely without any drag, because if there's any friction on the axis against the needle might get stuck and not be rotating properly. Now, the compass assembly is enclosed in a fluid-filled bowl, okay, which damps the oscillations and the vibrations and stabilizes the indication. Okay, why? Because without the fluid, the needle might be turning sideways and increasing the friction, like it might get stuck. Meanwhile, the fluid would guarantee that the needle would have more free movement around its axis, and it would guarantee, or it would prevent it from getting stuck, because it would be a big problem if it was stuck in one position. So that would prevent it from rotating to indicate the corrected heading. Okay, and the pilot might go off course due to that needle being stuck in a specific position. Okay, so the compass card aligns itself with the horizontal component of the Earth's magnetic field, pointing toward the magnetic north. As the aircraft turns, the compass housing rotates around the magnet assembly, causing the card to appear to move relative to the lubber line. Okay, so the card is the one that is moving. Meanwhile, the needle is always pointing to the north, but with the card moving, it would indicate to you how much you've veered to the right or to the left, and with how many degrees you have moved away from the north. Okay, that would determine the heading. So the heading is read at the lubber line, aligned with the aircraft's longitudinal axis. Due to the need for the compass to align with the Earth's magnetic field, it must remain approximately level. Okay, tilting introduces errors when the aircraft tilts, caused by the vertical component of the magnetic field. Compass errors. Despite its simplicity, the magnetic compass is subject to several inherent errors that must be understood by pilots and engineers, both, okay, in order to guarantee a proper operation of the aircraft while accounting for the different excursions from the accurate values that should be reported by the instrument. Correct? So, the magnetic variation, for instance, what is that factor? It is the angular difference between the true north, which is the exact north direction that crosses the middle of the North Pole, and that, okay, of the magnetic north, which is the actual vector reported by the instrument due to the field being, in a different direction than the exact north. And why is that? You see, I'm going to try to display it here. For instance, this is the Earth over here, and by the way, it's tilted. the Earth itself is tilted from its axis. It's not exactly a vertical axis. That is in reference to the horizon that houses most of the planets within the planetary system. So the exact north would be this way, correct? On any direction. However, you have at the center line, okay, you'd have, for example, that would be the magnetic field, okay, but in other areas you have a deviancy of, like, you would have a difference of the magnetic field direction that would veer from the exact north, correct? So if you are close to the center line here, okay, you would have an exact north. Meanwhile, on the sides, for example, here, okay, let's say you are here, the north would be pointing like this. Meanwhile, this is the north that you're interested in, which is the exact north, okay, that is normal or forming a 90 degrees angle with the globe as a reference point. Meanwhile, the north that you would be getting with the instrument is the north pointing to the actual north of the Earth. Okay, I might have mistakenly mentioned it in a different way, that, you know, the perfect north is the north pointing to the center pole. No, not necessarily. The perfect north is the north that is 90 degrees perpendicular to the face of the Earth, to the pole itself, okay? From above and below. That would be the north in reference to your flight, okay? Not the north like sideways, the perfect north. This is where the correction is needed. So the magnetic variation, let me re-choose the laser indication, laser pointer. Okay, so magnetic variation is the angular difference between the true north and magnetic north. It varies with geographic location and changes slowly over time due to also the movement of the Earth's magnetic field. Now, the relationship between true heading, the true north, and the magnetic heading, MH, is equal to, true heading is equal to magnetic heading plus the variation, which is the error factor. Okay? Variation is published on aeronautical charts and must be applied when converting between the true heading and the magnetic directions, okay, to guarantee a safe operation of the aircraft. Magnetic deviation, okay, the deviation is the error caused by local magnetic fields within the aircraft, such as electrical wiring, avionics, and ferrous materials, and it varies with heading and is unique to each aircraft. What are we talking about? You see, any electromagnetic field can affect the magnetic field being received by the instrument itself. And how do you get that kind of error or magnetic deviation? Because the aircraft itself houses more than one system. Okay, among these systems, you have the electrical system, where a powered powered wires are crossing through, and whatever has power going through it, it would create an electromagnetic field which would interfere with the instrument relying on detecting the north magnetic vector for the purpose of assessing or like measuring the heading, which is the compass. So the compass would be prone to these deviations that are caused by interference of other electromagnetic fields that are generated by the wiring or other instruments operating close to the heading system, or like the magnetic compass. Among them also, of course, mainly the avionics. Also, you have other factors such as the ferrous materials. Why? Because they can be magnetized and they can affect the magnetic field that's being received by this device, this instrument. So this deviation varies with heading, okay, also, and is unique with each aircraft. Now, Deviation is corrected using compensating magnets installed in the compass, okay, in order to apply a correction to the value being read. And these are documented in a deviation card. The corrected relationship becomes MH is equal to CH, okay, plus the deviation. So the magnetic magnetic heading is equal to compass heading plus the deviation factor. Magnetic dip. Magnetic dip occurs because the Earth's magnetic field lines are inclined relatively to the horizontal plane. Okay, because as we remember, the magnetic field has two components, an horizontal component and a vertical component. The vertical component of the field causes the compass needle to tilt downward towards the magnetic pole. So, if you remember, we mentioned before that the Earth acts as a giant magnet with a north and southern pole. At the north pole, the magnetic field vectors go downward. They penetrate the surface of the Earth at the northern hemisphere, at the northern pole, okay? And at the southern pole, they go outward, okay, to complete this cycle, creating this kind of magnetic fields. So that's why the needle would tilt downward and upward due to or during a turn. Okay, this is where the error comes from. So when the aircraft is within a turn, whether towards the north or the south, okay, it will either resist or so the needle of the compass will either resist the turn, so lagging behind and indicating a value which is lagging behind the actual heading value, or it would be leading the actual heading value, so it would display the value of the heading before the aircraft actually gets there, okay? So it would be preemptive, okay? It would be displaying or indicating a heading which has not, for which the aircraft has not caught up to it yet, okay? Now, so this is when it comes to turning errors. Also, acceleration and deceleration errors implicate some incorrect readings, some incorrect turns of the magnetic, piece within the compass, okay? So the disc would be rotating, would be either leading or lagging during the acceleration, okay? And we're gonna explain why or how it happens. These errors are most pronounced at high altitudes where the vertical magnetic component is the strongest compared to the horizontal component. Let's talk about the turning errors. Okay, so what happens when the aircraft is turning to the north? You see, this would be the aircraft turning to the north, okay? And meanwhile, at the same time, the compass, okay, this displaying disc or actually it would be a disc, an entire disc. Here, if we consider this rod, okay, the magnetic rod, so to speak, during the north turn, that would be turning downward, okay? It would be executing a down pull. Why? Because this north head has the tendency, okay, to turn towards the north pole, okay? So that's why it would down pull the magnet. The magnetic piece would be executing or running a down pull, which is against or opposite to the rotation direction, okay, to the direction of or orientation of the rotation of the aircraft. They would be going opposite to each other, okay, because the north turn is like this, counterclockwise, but the down pull is clockwise. So let's read it. North seeking end of the magnet, okay, would be pulling downwards. That would be the down pull during the turn, and the downward pull increases during the turn, okay? So the compass will resist the rotation and lags behind the actual heading. So the compass, why? Because the compass is turning opposite to the rotation of the aircraft itself. So it will resist this rotation, okay, and will lag behind the actual heading value. Now, when turning towards the south, what happens is that the turn in such case would have the same orientation, the same rotation heading as the downpour itself. So this will increase the rotation of the magnet. Why? Because you have two forces pulling together, adding up together, and like favoring the rotation or the rotative motion. That's why the compass turns faster than the airplane in such case due to this motion, and it leads the actual heading. So the displayed heading would be ahead of the actual heading in such case, opposite to the first case where you would have a turn towards the north, in which in such case what you would notice is the northern turn being opposite, okay, in an opposite rotative orientation than the downpour. So that would resist the rotation or the motion of the magnet, and the magnet would be lagging. It would be displaying a heading less than the actual heading, okay? It would be lagging behind. Acceleration and turning errors. Now we've already discussed the turning errors and how they affect the magnetic indicator, the magnetic field, or actually, yeah, the magnet that's indicating the heading within the compass, to make it short. Okay, so the compass lags or leads the actual heading depending on the direction of turn that we've discussed earlier. Okay, these affect like the heading, okay, and they are summarized by the mnemonic, okay, accelerate north, decelerate south. As we mentioned before, actually, yeah, accelerate and decelerate, we have not discussed that yet. It has to do with the acceleration and deceleration that we're going to talk about right now. So what happens is that during acceleration, the north-seeking head would be pulled downward, okay? So this would be interpreted by the aircraft as if it is heading or turning towards the north due to the power or due to the forces of inertia, okay? Why? Because the motion, the rotative motion of the needle, compass needle, is affected by a centrifugal force due to the rotation movement. This actually applies both during the turns and during or due to the acceleration, because when you accelerate, the rotation of the magnet around the axis, like the magnetic disk, also accelerates. However, and you have acceleration versus deceleration. So you have during the acceleration, it will turn toward the north. Why? Because this seeking head, okay, the north seeking head would be pulled downwards. Okay, so it would be turned toward the north as if it is like indicating the aircraft is turning towards the north. Meanwhile, during deceleration, okay, and due to the lag, what happens is that the north-seeking head would be pulled to the south, okay? So actually, it would be pushed forward, I'm sorry. It would be, instead of being pulled, it would be lagging forward. It would be pushed forward, so it would start pointing towards the south during the deceleration. So instead of rotating northward, it would rotate southward. Why? Because due to the deceleration motion, as if pointing to the south. So this will be interpreted by the aircraft as if the aircraft is turning towards the south. Again, in acceleration, what happens is that you accelerated, okay, due to that acceleration, the head, the north-seeking head, okay, and its rear, it would be pulled downward, okay, so the north would be pulled upward as if the aircraft is turning towards the north. Meanwhile, in deceleration, it would lag, so it start turning in the opposite direction, and it would seem as if it is pointing to the south, okay, the north head is pointing to, yeah, the head of the needle is pointing to the south, as if the aircraft is turning towards the south. I hope it became clear by now. 5.4 Slaved gyro systems and flux valves. Okay, let's start with the flux valve operation. A flux valve is a remote magnetic field sensor that detects the horizontal component of the Earth's magnetic field. It consists of magnetically permeable cores, okay, wound with electrical coils on the inside arranged to sense or to detect the magnetic field direction. As the aircraft changes heading, the induced voltages in the coils, why? Because by the change or because of the change of the electromagnetic field, you have an induced current. Okay, electromotor force, it is called, which is, if you want to measure it in volt, E, it is indicated or denoted by E equal minus derivative of phi, which is the magnetic field, divided by dt, okay? That would be the change of the magnetic field in respect of time, delta phi divided by delta t, or the derivative of phi, which is the change, the differential, or the change, the shift of the magnetic field in respect of time. This is what gets you E, or the electromotor force, okay? Like the induced voltage due to that shift. So, and this can be detected by this device. Why? Because due to the shift of the magnetic field, we can measure the induced current, okay, in different areas of the plaque of the flux valve. As the aircraft changes heading, the induced voltages in the coils vary according to the orientation of the magnetic field. Okay, so V, the voltage, would be proportional to the value of the horizontal magnetic field, which is H, the horizontal component of B, multiplied by cosine theta, which is the angle, okay, that is, in other words, the heading of the aircraft relative to the magnetic north. Okay, so if that is the magnetic north, N, okay, and the aircraft is 30 degrees away from the north, that would be theta. Okay, and this is the value that will affect the voltage. So by measuring the voltage, we can assess the exact north of the aircraft, the exact heading of the aircraft in respect of the horizontal north. Slaved gyroscopic systems. In slaved gyro systems, a directional gyro provides stable short-term heading information, while the flux valve supplies long-term magnetic reference, just for reference. Okay, so a control unit continuously compares the gyro heading with magnetic heading and applies corrective torques to eliminate the drift, because due to phenomena such as gyroscopic precession that we've discussed earlier, you would have the directional gyro that indicates, that would be calibrated and indicates the heading of north, okay, rotating within the directional gyro equipment. So the gyro itself would start drifting due to the gyroscopic precession, okay? So that's why it needs to be synchronized and continuously updated in reference with the magnetic compass, okay? This is the advantage of the magnetic compass, giving an accurate heading, an accurate orientation towards the north. Now, this combination merges the stability of the gyroscopic system with the long-term accuracy of the Earth's magnetic field, which is very advantageous. Advantages over magnetic compass. Slaved gyro systems eliminate most compass errors, including dip, acceleration, and turning errors. They provide smoother, more stable, more accurate directional information, and form the basis of modern navigation system and modern heading systems such as the horizontal situation indicator, or HSI, okay, which is part of the attitude indicator. Actually, yeah, it's part of the entire instrument, but this is the HSI. It's like the compass, but something which is more advanced than compass itself. System limitations: although it is more accurate than a simple magnetic compass, slaved gyro systems remain susceptible to magnetic disturbances themselves. Also electrical failures, because they depend on a powered rotation of the gyro, the directional gyro, correct? Which is the gyro part of that instrument, and sensor misalignment. Okay, also you have other errors that are due to, again, mechanical failures within the gyro or the gyroscopic precession. Okay, other phenomena can affect that device, that instrument. So regular calibration and cross-checking remains essential for safe operation. You need to cross-check it with another more reliable instrument. This is why we need redundancy, so that in case it fails, you have another reference for navigation, which is very important. Chapter or Module 6, Engine Indicating Systems. Okay, let's start with 6.1, Engine Performance Parameters. Engine indicating systems provide real-time information and monitoring about engine operating conditions and performance. These indications allow pilots and maintenance personnel to operate engines efficiently, meaning reducing fuel consumption. That would be part of efficiency. Detect abnormal conditions such as engine overheat, low oil pressure, etc. early, and prevent mechanical damage. Key engine performance parameters include rotational speed, which is the tachometer or RPM, how many revolutions per minute. That would be displayed as N1 and N2 in percent in jet propelled airplanes. Okay, you have intake air pressure, the pressure of the air at the intake of the engines, exhaust and cylinder temperatures such as EGT or exhaust gas temperature, the temperature of the air at the exhaust where you can detect an engine overheat, and cylinder temperatures also, fuel flow and quantity, okay, fuel level indicators for example, and oil pressure and temperature, which is also very important to assess and monitor the performance and the conditions of the engines. Engine power output is fundamentally related to torque and rotational speed. So the power is equal to the product between the torque, which is the force being applied to the motor, okay, the force vector, multiplied by W, which is the angular velocity, or how many degrees per second the motor is rotating. Okay, so again, the torque is being applied perpendicular to the direction of the axis of rotation of the engine. Monitoring these parameters ensures the engine operates within 35 limits under varying flight conditions, whether ice, hot weather, cold weather, etc. Tachometer or RPM indicators. RPM indicators, of course, stand for revolutions, number of revolutions per minute for the engine. Okay, the tachometer measures engine rotational speed, typically expressed in RPM, revolutions per minute. In piston engines, RPM directly correlates with propeller speed. Okay, they are correlated together. While in turbine engines, it is expressed as a percentage of the maximum rotational speed, e.g., or for example, N1 and N2. And you would see these indicators in the ECAS instrument, okay, the ECAS indication within the cockpit of Boeing 737, 747, 787, Dreamliner, etc. Mechanical tachometers use centrifugal force acting on the rotation or the rotating masses, okay, whereas this is how it is measured. Whereas electrical tachometers rely on the magnetic pickups or alternators that generate the frequency signals. Okay, so based on the rotation of the engine, the rotation itself is generating, because the engine is also a generator. Okay, so it would be generating a current of a specific frequency. That frequency can be picked up and evaluated in order to get the actual value of RPM, of revolutions per minute. And that would be the formula. RPM, or number of revolutions per minute, is equal to 60 times F, which is the frequency of the current of the alternator, divided by N, which is the number of pulses per revolution. Okay? So that would give you the RPM, number of pulses, how many pulses is there per revolution. Okay, and these pulses compared to the frequency multiplied by 60, okay, 60 for, 60 seconds, I think, yeah, okay, and we get from it the number, I'm sorry, 60, because 1 is by second, so times 60, that would be per minute, because a minute has 60 seconds in it, so this would get you the RPM value, or number of revolutions per minute, okay? Accurate RPM indication is essential for power setting, for engine efficiency, and for avoiding overspeed conditions and overheating of the engines. Okay, so you have again mechanical tachometers that use centrifugal force acting on rotating masses. Okay, whereas electrical tachometers rely on the magnetic pickups. Okay, or alternators. That is the generated current. That would be the current used to evaluate based on its own frequency and the number of pulses per revolution. You multiply it by 60. This is how we would get the number of revolutions per minute. Also, another clarification concerning the mechanical tachometers and how do they work. So you would have rotating masses, and mechanical tachometers use the centrifugal force which is generated any time you have a rotation motion. So this mass that is rotating, okay, due to the rotation, you would have a force that would go outwardly, okay, it would be perpendicular, okay, or normal, having 90 degrees with the tangent to the circle of rotation. However, it would be in the same, like somewhat just like, but it would exist in the same plane of rotation. So let's say you have a rotation like this, okay, the vector of the centrifugal force, it would be pulling the wheel. So you have a rotating wheel, it would be pulling the wheel in a horizontal direction, okay, so it would be pulling the axis, okay, it would be pulling the axis like this, the axis of rotation, okay. To explain it in a simpler way, I'm trying, okay. So unlike the gyroscopic precession where you have like a rotating disc and the precession force would be normal, forming 90 degrees with the center of the disc, okay, and it would be in the same direction or on the same line of the rotation axis, okay. Unlike that, the centrifugal force exists within the same plane where the wheel is rotating, within the same surface, okay. So it would be parallel to the rotation direction instead of being 90 degrees in delay like the gyroscopic precession, okay. And it would be pulling the wheel like from the axis of rotation, okay. So that motion, that strain and stress on the axis of rotation would be measured, okay, and based on the rotation speed you would get how much strain or displacement of the axis we have. So, or in other words, by measuring the displacement of the axis or the mass in this case, you can get the value of revolutions per minute, because as violently as it rotates, it will be pulling the axis much further from its original position. I need to add also another side note here, that the masses that we're talking about, they are not uniformly distributed around a circle, which is intentionally done by that, so that, because if you have a disk with a uniform mass around the axis, when it rotates, it won't move the axis, okay? because I need a vibrating motion in order to assess how many revolutions per minute. And this you won't get in case you have a uniformly distributed mass around a disk, okay? Or a disk that is uniform rotating around the axis. No, you would need a part of the disk, like, or a mass that is only stranded on one direction, okay? Which will forcefully, like, it is deliberate that it would cause a vibration. Why? Because the mass is only on one side. So as it rotates, it would be moving and vibrating the axis of rotation. Think of it as, you see the component within the PlayStation joystick, okay? Why does it vibrate? Because it is done or designed just like that. Instead of having a uniform disk, you have only a part, a chunk of a disk, okay? Like a pizza. When you have one chunk, one piece of a pizza, okay? So it is designed the same way, okay? The mass is like a chunk of a pizza, so it's not a full disk, it's only a part of a disk, okay? It's only like a cheese, one piece of the cheese, okay? Of the cheese disk. So when it rotates, it will definitely be moving the axis and displacing it in a specific direction. Like it would be vibrating, it would be displacing it by a certain distance from its original position. And as the rotation becomes more violent, more rapid, okay, it would cause more displacement between the original position of the axis and the current position. That displacement would be measured in order to assess the number of revolutions per minute. Manifold pressure gauge. Manifold pressure, or MP, indicates the absolute pressure of the mixture of air and fuel entering the engine cylinder for turboprop type airplanes. It is typically measured in inches of mercury, okay, or INHG. HG is the symbol on the atomic table of mercury. Yeah. Manifold pressure reflects the engine loading and the throttle position, how much power intake it is taking, or how much air it is inhaling, correct? Rather than the engine speed. All right? So it does not assess or measure the engine speed, but rather it reveals how much loading you have on the engine, how much it is consuming fuel, and the throttle position. Engine power in piston engines is approximately proportional to the product of RPM, number of revolutions per minute, multiplied by manifold pressure. So the P, the power generated by the engine, or consumed by the engine rather, is proportional to the manifold pressure multiplied by RPM. At higher altitudes, reduced ambient pressure due to the decrease of the air density limits maximum achievable manifold pressure, which reduces the effectiveness, okay, and the available engine power. In other words, the performance of the engines decays with altitude, okay, because the density of the air decreases, and hence you would have a lower density of oxygen, which would lead to a less effective combustion of the fuel mixture with the air at these higher altitudes by the engine. EGT, or exhaust gas temperature. Exhaust gas temperature measures the temperature of the exhaust gases leaving the engine cylinders. EGT is a critical parameter for mixture control and combustion efficiency. EGT peaks near the stoichiometer air-fuel ratio, okay? That would be AFR, stoich is 14.7, air to 1 fuel, okay? That would be like the ratio of oxygen or air versus fuel consumption. Operating richer or leaner than this ratio results in lower EGT values, okay? So if you have a richer operation, meaning richer like fuel pumping, okay, or leaner, meaning less fuel, that would result in a lower EGT value. So it is a very important efficiency parameter, okay, efficiency indicator, so to speak. Pilots often lean the mixture to achieve peak EGT or a specified temperature offset to optimize fuel efficiency, okay? Not consuming more than required to maximize, while maximizing the performance of the engine, okay? At the same time, while preventing excessive thermal stress to lower the depreciation factor of the engine and lengthen its lifetime. CHT or cylinder head temperature. CHT indicates the thermal condition of the engine cylinder structure. Unlike EGT, which responds rapidly to mixture changes, CHT reflects long-term thermal loading. Okay, so excessive CHT can lead to detonation, meaning like in turboprop engines, that would be the explosion cycle before its time, like prematurely before the compression stage. You would have an explosion that is out of phase with the 4 cycles of the intake, compression, combustion, and exhaust. So that would happen before the combustion. That is called detonation. So excessive CHT, if you have an excessive head temperature, it can lead to detonation, pre-ignition, and structural damage. Why? Because you would be resisting against the compression or compressing motion of the cylinder levers. So while the levers are pushing the cylinder to compress, the detonation, it would react in the opposite manner, pushing in the opposite direction. That can inflict damage and structural damage against the cylinders. Now, the heat transfer from the cylinder head follows this following formula, which is Q equal HA multiplied by temperature of the CHT, okay, cylinder head, minus the temperature of the air, where Q is the heat transfer rate, is equal to H, which is the heat transfer coefficient, multiplied by the surface area, because the heat transfer is always dependent on the surface of transfer. Okay, as this surface increases, the transfer becomes more accelerated. Okay, why? Because it has to do with the thermal flow between surfaces. So Q is equal to H, which is the heat transfer coefficient, multiplied by the surface area, times the difference between cylinder head temperature and the temperature of the air. Proper cooling, airflow, and mixture management are essential to maintain safe CHT levels. Fuel flow measurement. Fuel flow indicators measure the rate at which fuel is delivered to the engine, typically in kilograms per hour or gallons per hour. Engine fuel consumption is directly related to power output. So, MF, or the fuel mass flow rate, is equal to specific fuel consumption, SFC, multiplied by power. This is how you would get mass flow rate, okay, fuel mass flow rate. So the fuel mass flow rate can be measured by specific fuel consumption, SFC, multiplied by the generated power. Accurate fuel flow information enables performance optimization, range calculation, and fuel management. Oil pressure and oil temperature. Oil pressure ensures proper lubrication of moving engine components, which reduces the friction or drag between different components, moving components, basically, of the engine. It is generated by the engine-driven oil pump, which is from the engine itself, okay? This oil pump is powered by the engine and must remain within specified limits. Oil pressure can be expressed by the formula: pressure of oil is equal to the force divided by area, which is the static pressure, where F is the force exerted by the oil and A is the bearing surface area. Oil temperature indicates the oil's ability to maintain proper viscosity. Viscosity meaning that the oil won't flow very rapidly without touching the different components of the engines, okay, the different moving parts. It would flow smoothly, okay, but moderately slowly. So when you have, by the way, and it should be a nominal value, because for high, very high viscosity, it would stick and it would stop, it would stop moving and flowing properly. But if you have a low viscosity, it becomes more like water, and it will no longer be effective in lubricating the different engine parts, while preventing the drag and the grinding between these components, okay? The friction. So high oil temperature reduces viscosity and lubrication effectiveness, while low temperatures impede or block the oil circulation. Oil viscosity varies with temperature according to the following formula. Mu is directly proportional to E, which is the exponential of 1 divided by T, and T is the temperature. Maintaining oil pressure and temperature within limits is essential for engine longevity and reliability. A small part to be added here, or a small note, is that without the oil, the different components that move against each other, okay, that are in contact with each other within the engine would be like gritting and grinding, so they would be damaged at the long term. Plus they would increase the temperature of the engine, causing or leading to overheat and breaking of the parts. This is why lubrication is very important for the aircraft engines. Operational awareness and limitations. Engine instruments must be continuously monitored and cross-checked to verify their behavior and their performance. Abnormal trends, even within limits, can indicate developing faults that may not be serious just yet during the time of detection, but they would develop into a more serious problem. Understanding the relationships between engine parameters allows proactive decision making and enhances flight safety, okay, and efficiency, if I may say. Fuel system part 7, or chapter/module 7. Let's talk about fuel systems, starting from the types and properties. Aircraft fuel systems are designed around the physical and chemical properties of the fuel they use. The two most common aviation fuels are aviation gasoline, avgas, and jet fuel, which is the Jet A or kerosene. Okay. Avgas is used in piston engine aircraft and is characterized by high octane ratings to prevent detonation or like combustion before the time of the combustion phase. Detonation is when the fuel ignites before the combustion phase. We can call it a premature combustion. Common grades include 100 LL or low lead, okay, which is the lead within the fuel itself, which has a blue color for identification. Jet A is a kerosene-based fuel used in turbine jet engines. Okay, it has a higher flash point, higher ignition point, and a greater energy density than avgas, making it more suitable for high performance and high altitude operation. Okay, because you need a faster turn of the engines and at high altitudes. Okay, because there would be no hindering for the rotation of the engines at these altitudes. Meanwhile, for the turboprop, you would need something that combusts a little bit slowly, but has a higher torque. That's the difference. Okay, so if we want to compare, for example, between because imagine the avgas being diesel and the Jet A being what do we call it? The fuel, the car fuel, okay? The benzene, okay? So what would be the difference between them? The avgas combusts a little bit more slowly, but it would combust longer, just like the diesel. The diesel combusts, or like it fires, it goes on fire for longer periods, okay? But it has a slow ignition. It has a slow incendiary effect, which would induce a higher torque for lower altitudes for the aircraft. Okay, higher torque for the turboprop, which is effective to move the engines. Again, here I'm comparing the F-gas with the diesel fuel. Meanwhile, okay, if we compare the Jet A with like the benzene, so the characteristic of the same fuel that is used for motor vehicles such as cars, okay, it has a combustion which is a more like a more explosive ignition. Okay, it can combust at lower temperature. Okay, and it's more like it goes on fire much faster than the diesel itself. However, the combustion itself burns quickly, so it is more suitable for lower torque requirement engines. Okay, for engines that have lower torque, okay, the benzene would be more effective. So this is why a six-wheeler usually runs on diesel, because it requires higher torque. It is a heavy vehicle, okay, a heavy transport vehicle, as you know. It requires a higher torque and a slow combustion rate. Meanwhile, your average car requires more the alternative. Okay, why? Because it needs to combust quickly, and it has a lower torque requirements but more speed requirements. It needs the fuel to ignite quickly, much faster, in order to turn the engine at a higher rate. This is a display of the fuel system. You have the crossfeed when you want to transfer the fuel from left wing to right wing or vice versa. You have like fuel pump, the fueling valve. Okay, you have the engine valve, left engine, right engine. Okay, that opens up and close to increase the intake of the fuel within the engines. Okay, and you have also here the APU, etc. Key fuel properties include density or rho, viscosity, and volatility, how much volatile it is. A volatile substance or volatile fuel, specifically here, means that the fuel would evaporate so quickly if it's not kept within a sealed compartment. Okay, and also calorific value, how much does it burn, how much does it generate heat. Fuel density varies with temperature according to rho equal m divided by v, where m is the mass in kilograms and v is the volume in meter cubed. As temperature increases, it becomes more volatile and the density decreases. Why? Because the molecules separate from each other. So you would have what used to be in the same volume expanding. So the mass would be lower per volume unit. Okay, that would be expressed as a lower density, which directly affects the mass flow and energy delivery within the engine. Fuel energy content. The energy released during combustion determines engine power output, of course. The heat of combustion for fuel, that is the factor that affects the generated power, is expressed by Q, which is the calorific energy or released energy, is equal to M, or fuel mass, multiplied by the energy, specific energy, okay, lower heating value, which is the energy characteristic of the gas itself. Jet A generally has a higher specific energy per unit mass, okay, than Avgas. So it burns much quickly and it produces much energy, but at a higher speed, at a higher rate. This is why it is more suitable for lower torque engines. Why? Because if it does that with engines requiring a higher torque, it will break the crankshaft. Okay, that is what would happen. It would break like the engine handle. Why? Because for heavier vehicles, and again going back to examples on the ground for the six-wheeler, like if you have a fuel that ignites very quickly, it would try to turn the handle of the motor very fast and it would break it. Why? Because it requires, again, a six-wheeler or a heavier carrier of whatever kind, heavier aircraft, We're not talking about jet aircraft, but an aircraft operating at a lower altitude, because the jet is something else. Okay, so it requires a fuel suitable for higher torque. Why? Because it needs to move like a heavier mass with a slow rate, so that the handle of the engine won't break. Just like a six-wheeler. Longer combustion, but a lower rate of the combustion itself, a lower energy delivery rate. Okay, this lower heating value. Fuel tanks, pumps, and lines. Fuel tanks store fuel safely and supply it to the engine under all operating conditions. Tanks may be integral, so a part of the wet wing, okay, bladder type or rigid tanks. Fuel is delivered from tanks through fuel lines using either gravity feed, so by dropping the fuel, that would be in the case when you have the wings are above the engine, or pumps to deliver the fuel to the engines, okay? Because in case they are at the same level, you need the pumps to drive the fuel needed for the motors. Pumps may be engine driven by the engine itself, or electrically powered booster pumps, standalone pumps. Fuel flow through a line is governed by, and this is called volumetric flow, by the way, volumetric flow rate, is given by V equal A times V. E is the cross-sectional area of the pipe, okay? And V, lowercase v, is the fuel velocity, or the speed of the fuel itself. Now, pressure losses due to friction and bends are critical considerations in fuel system design. Okay, why? Because they reduce the velocity of the flowing fuel, which would reduce the volumetric flow rate. So again, how we can visualize it? If you imagine this as being the pipe, and this is the cross-sectional area, so A times V, which is the velocity of the flowing fuel, that product would give us the volumetric flow rate. Fuel quantity indication system or indicating system. Fuel quantity indicating systems provide the crew with information about the amount of usable fuel remaining. These systems may be mechanical, by the way, or electrical. Okay, mechanical sensors, which would be like a floater, okay, a floating part within the fuel tank, or electrical, that would be the sensor, okay, that would short the electricity when the fuel is detected. So you would mount multiple sensors at different heights, just like you would mount in the mechanical indication system, different floaters at different heights within the tank. So whenever a floater is like driven up, or whenever you have a short circuit at one of the indicators, at one of the electrical sensors, that would light up within the cockpit that you would have fuel at that level, okay? Capacitive fuel quantity systems are widely used, okay? So the different level of fuel would change the capacity value of an electrical component, okay, in modern aircraft. The capacitance between the probes varies with fuel level, which is C equal epsilon A divided by D, where epsilon depends on the dielectric constant or permittivity of the fuel. Accurate fuel quantity indication is essential for flight planning, weight and balance calculations, and fuel management. Now here, to give you a picture, that would be the probe, okay, the electrical sensor. When it's dipped in the fuel, it would change the capacity, the capacitance, which is given by A divided by D times epsilon, where epsilon again is the dielectric constant of the fuel itself. Okay? Fuel metering and control. Fuel metering systems regulate the amount of fuel delivered to the engine to maintain the correct air-to-fuel ratio. In piston engines, carburetors, or fuel injection systems meter fuel based on the airflow and throttle position. Position of like the position of the pedal of the fuel within the car, okay? The pedal of the oil inside the car, its position would determine how much fuel the engine is getting, as an example. However, in turbine engines, fuel control units, FCU, or full authority digital engine control, FADEC, systems precisely control fuel flow. Fuel mass flow rate is related to engine power. It's given by M, lowercase f, or denoted by MF, equal to power, engine power, divided by eta, multiplied by H, with eta is the engine efficiency, and H is the combustion rate of the fuel being used. Precise metering ensures efficient combustion and prevents engine damage. Another thing to be noted here is that when you have an excess of the fuel in respect of the air, okay, so when the ratio is more, like when the scale is more being pulled towards the quantity of the fuel against that of the air or the volume of the air, that would result in an overcombustion or an overheated engine, okay? So there would be an excess of fuel being burned within the engine, which would lead at times to engine backfire. It means that the fuel is not being fully combusted, okay? Meanwhile, when you have a lesser quantity of fuel, that would lead to a lower exhaust gas temperature, okay, and a lesser efficient combustion. Fuel system failures and safety measures. Fuel systems are designed with multiple safety features to prevent fuel starvation, meaning the lack or the excess lack of fuel, leakage. So when the fuel is leaking out, it needs to be acknowledged or like detected by the system somehow, or fire hazards. Common fuel system failures are the following, but they include, but not limited, the following rather: fuel pump failure, the pump that propels the fuel all the way to the engines, it can fail, or fuel contamination, meaning a mixture between fuel and water that can lead to devastating consequences at times. Why? Because that can lead at times to fuel icing, okay, and an exceeding waxation due to the presence of water. Also, vapor locks, meaning that you could have vapor locked on the inside of the crossfeed that would lock or pressure, like it would keep the fuel from flowing from one part of the tank to another, from the left tank to the right tank, or vice versa. And fuel leaks, meaning when you have a puncture in the wing somewhere or in the reservoir in lower, like turboprop, smaller airplanes, okay? Because they house the fuel differently than the jet planes that house the fuel within the wings themselves. Vapor lock occurs when fuel vaporizes in the fuel lines, interrupting flow, okay? The likelihood of vapor lock increases when the fuel pressure drops below vapor pressure. So the vapor would keep the fuel from flowing in such case, which is the premise P of the fuel is less than the pressure of the vapor. Safety measures include redundant pumps, which is, one of the most important feature is redundancy within the airplanes, okay, in order to have always a backup for a potential hazard or for a system that seems to be a weak point that can fail, okay, that is a liability, so to speak. You have fuel filters to get rid or to rid the airplane from the contaminants, fuel shut-off valves, okay, in order to shut off the fuel and prevent it from crossing from one tank to another in case you have a leakage in one of the tanks. Fire-resistant lines in order to resist or to counter any potential fire, and proper tank ventilation, okay, because the venting prevents from vapor locks. Fuel system components
are designed to meet strict certification standards in order to ensure safe operation under all flight conditions, including icing, for example. Now, operational awareness. Effective fuel management requires understanding system design, fuel properties, and indication limitations. Continuous monitoring and proper procedures ensure reliable engine operation and flight safety. Module or Chapter 8, Electrical Power Generation and Distribution. Let's start with DC and AC electrical systems. Aircraft electrical systems provide power for avionics, which are different instruments, lighting, flight instruments. Avionics are, the controls, engine systems and engine detection systems, environmental controls such as the air conditioning, etc. Okay? So, depending on aircraft size and complexity, electrical systems may be direct current, DC, which is a continuous current that does not change in amplitude in respect of time. So, its derivative is zero in respect of time. It doesn't change. There's no shift. And alternating currents, AC, where you have an alternating current going from positive to negative values, like a sine wave, okay, having a specific frequency, which is the inverse of the period. The period is the distance between two peaks or two troughs. Let me draw it. So that would be the alternating current, okay? The distance between two peaks or two troughs, that would be the period, of course, distance in respect of time. How many seconds? Okay, so the frequency is the inverse of that period, okay, and it's measured in hertz. So this is one of the characteristics of the alternating current, the frequency and the amplitude. The amplitude is the distance from the reference axis, horizontal axis, and the peak of the sine wave, of the power signal, okay, or I'm sorry, the current signal. So DC systems are commonly used in light aircraft. Let me put back the laser pointer. So they are commonly used in lighter aircraft based on voltage of 14 or 28 volt architectures. Why? Because most of the controls are mechanical. They are directly correlated with the movement of the pilot controls, okay? So the pilot with his own strengths would move the ailerons, the elevators, the rudders, and smaller airplanes. So you don't need a higher amount of power, and DC is sufficient. However, in AC, in like larger airplanes, such as the heavy types, such as Boeing and other larger aircraft, AC systems are more prevalent in transport category aircraft, okay? Due to their efficiency in transmitting higher power levels and their compatibility with large motors or large engines and avionics. The fundamental relationship governing electrical power is P equal VI. V is the voltage and I is the current. Okay, that would be the power being generated by the engine or being fed to the engine. Okay, it goes both ways. Now, as a side note, when we spoke about the avionics, these are the systems in the aircraft that are used to control, navigate, communicate, monitor, and manage flight. Okay, think of avionics as the brain and nervous system of the aircraft. Now, within the formula that we've mentioned before, again, P is the electrical power in watts, V is the voltage, and I is the current. In AC systems, apparent power is defined as S equal VI. Okay, but real power, since you have a since you have a frequency, a changing frequency, real power would be given by P equal VI times cosine phi, where phi is the phase angle between voltage and current. Okay, so phi is not the frequency. Yeah, notice that and pay attention to the fact that phi is actually the phase angle between voltage and current. And here is what I mean by that. So let's say this is the current, and let's say this is the voltage, okay? So the voltage is in blue. Now, mind you that you have from here to here, from peak to peak, you have a full cycle, which is how much? It is 360 degrees, okay? Because this is the sine, correct? Or cosine, whatever you want to, to cite it as. So you have, because they are no different, okay? The sine starts from 0, cosine from 1. Now, so let's say this current here, this is the current, okay? And one full cycle, which is from this point to this point, okay? Or from peak to peak, or from trough to trough, that would be 360 degrees as an angle. Now the voltage in red, that's the V, okay? And also that's 360 degrees from peak to peak or trough to trough. Now the phase angle between voltage and current would be that distance here in terms of degrees, okay? So if you notice here, let's say this entire cycle, actually from peak to peak, yeah, this entire cycle is 360 degrees, right? Okay, from here to here. So here is almost at the middle. That would be around, if it's at the middle, it would be 180 degrees. So pi would be 180 degrees, and cosine pi would be equal to -1. I hope it's clear by now. 8.2 Generators and alternators. Generators and alternators convert mechanical energy from the engine into electrical energy. Okay? Early aircraft used DC generators, which are like the dynamo within your own car, while modern systems predominantly employ AC alternators due to improved efficiency and reliability. An alternator produces alternative current or AC voltage, which is often rectified to DC for distribution. The frequency of AC output is related to the rotational speed of the alternator, which is given by F equal, that's the frequency, P, or the number of magnetic poles, multiplied by N, which is the RPM or the rotational speed of the alternator, divided by 120. Okay, now voltage regulators control output, okay, the output voltage, by adjusting field current, ensuring stable power delivery, because we cannot have a fluctuation of the current that's being delivered to different instruments in avionics, okay? So it ensures a stable power delivery across varying engine speeds and electrical loads. 8.2 Generators and alternators. Generators and alternators are somewhat similar. They convert mechanical energy from the engine into electrical energy. However, early aircraft used DC generators, like this one to the right, while modern systems predominantly employ AC alternators due to improved efficiency, meaning that the rate of conversion from mechanical energy to electrical energy or power is more efficient, okay, so lower waste of mechanical power, and they are more reliable, which means that they can be sustainable, reproducing the same power results throughout their lifetimes. Okay, now an alternator produces AC voltage, which is often rectified to DC for distribution. The frequency of AC output is related to rotational speed, given by the following formula: F equal Pn divided by 120, with P being the number of magnetic poles and N is the number of rotations per minute, or RPM. Voltage regulators control output voltage by adjusting the field current, which is necessary to ensure stable power delivery across varying engine speeds and electrical loads, so that we wouldn't have a fluctuation of the current being delivered and the power, electrical power being delivered to different components, instruments, and avionics. Otherwise, you might burn up or fry an electronic board. You might be risking doing that. This is why the regulators are necessary. If I may add another thing concerning the alternators, so unlike the generator, which uses a commutator, these use slip rings, okay, in order to generate power. 8.3 Batteries and charging systems. Aircraft batteries provide electrical power during engine start and act as emergency power backup sources in the event of generator or alternator failure. By the way, the generator, DC generators, were used more commonly in smaller aircrafts. Meanwhile, the alternators are used in larger, heavy type aircraft such as Boeing airplanes. Common battery types include lead acid and nickel cadmium batteries. Battery capacity is expressed in ampere hours, AH, which is given by Q equal I T. Y, while T is the time. So let's say you have 200 ampere hours, meaning that if you supposedly you're consuming 2 amperes, okay, how many hours does this battery last? Okay, if we won't account for the losses, for how much the battery can be discharged, which is called DOD or depth of discharge. Okay, so if it can be discharged to 90%, okay, and how much it can be filled up. So let's say it's 200 ampere hours. However, it can be filled to 95%, not more. So you multiply it by 0.95, okay, and it can be discharged 90% also to the lower. So you multiply again by 0.9. This is all that you can use. And you divide it by 2 amperes. It gives you how many hours it would last before it disconnects. Battery charging systems maintain power battery state of charge while preventing overcharging, which is important. Charging current depends on the difference between the generator voltage and battery voltage. This is the charging current. I equal the voltage of the generator minus voltage of the battery divided by R, which is the resistance. Proper battery temperature management is essential in order to avoid having an incendiary phenomena or event, as battery performance and lifespan are temperature dependent. Very important, okay? Because when you have an overheat, it would kill and depreciate the batteries rapidly. Bus bar and circuit protection. Okay. So what is a bus bar? Bus bars distribute electrical power to various aircraft systems, okay? So you have different electrical loads are grouped into main buses, okay, essential buses and emergency buses. These are the electrical connections among different, in order to distribute power for different systems. And these systems are grouped based on their own category and preference, of course. So this is like a distribution of buses, again, is based on the operational importance of different groups, with each group having systems that are like interconnected together. They have a dependent functionality among themselves. Circuit protection, when we talk about circuit protection, we're talking about circuit breakers and fuses. Now, the fuse snaps and becomes an open circuit when a specific current value is exceeded. So when you have a fuse of 2 amperes, for example, it would snap above when the current goes above that threshold, which is 2 or 2.2 amperes, depending on the tolerance. Meanwhile, the circuit breaker is like an automatic switch, okay, or like a thermosensitive switch that once the current exceeds a specific value, it would pop here, okay? It would pop to the outside, just like the circuit breaker you have in your house, except your own circuit breaker pops up and down. Here it pops outwardly when you know the maximum current value that it can handle is exceeded. In fact, to be more accurate, when we talk about the circuit breaker that is used in residential application, it flicks rather than pops. This one pops to the outside when the circuit breaker is activated, and it opens up the circuit to prevent like an overheating of the cable or a potential fire. Okay. Meanwhile, the one at your house doesn't pop. Instead, it flicks upward. Okay. I'm sorry. It flicks downward when the acceptable current is reached. Okay. So these devices operate based on the principle P heat, the power of heat, is equal to I square R. When the current exceeds safe limits, heat generated within the conductor that is on the circuit breaker causes the protective device to pop the circuit, okay, to cut the current and prevent like a potential fire or an overheating of the cables or the wires, rather. Bus architecture ensures that critical systems remain powered even in the event of partial electrical failure. Load management and redundancy. Load management involves controlling electrical loads to ensure power availability does not exceed generation capacity. Meaning, if the alternator is generating, let's say, 10 amperes, okay, this is like an example which is fictitious because much more power and current is required to run an aircraft, okay? But let's say, as an example, the alternator has the ability at some point, due to whatever circumstances, operational circumstances, to generate 10 amperes, okay? But the instruments that are running at that moment require 15 amperes. Okay, so automatically, in order to avoid having like a problem with the alternator, like burning or frying the alternator or breaking it, automatically non-essential loads would be shed, okay, would have their own circuit breakers pop up in order to throw them, okay, drop them from the load array, okay, or they can be manually shut down during abnormal conditions. Redundancy is achieved through multiple generators, independent power sources, and cross-tie buses. The total electrical load must satisfy the sum of all the load, the power of the load should be less than or equal to the power available. Otherwise, non-essential systems would be taken down from the power consumption, from the power array, immediately and automatically via the intelligent mechanism of their circuit breakers. Okay? And even the electronic system would trigger that in order to ensure that there's no overconsumption of the power that's not available, okay? That would starve the different instruments and they would start working abnormally. And it even can risk, if there's no protection, surge protection, it can risk frying one instrument or two. Advanced aircraft employ electrical load management systems that monitor power generation, consumption, and system health in real time. Operational awareness and system limitations. Understanding electrical system architecture allows pilots and maintenance personnel to recognize abnormal indications, manage failures, and ensure continued safe operation. Electrical systems are designed to prioritize safety critical loads, the instruments that are the most essential for navigation and situational awareness, okay, and maintain essential functions under adverse conditions. What would be such adverse conditions? If the engine is no longer running properly, okay, the main engine, or if it flames out, then you would need, like if both engines flame out, you would need the deployment of the RAT or ram air turbine, which goes below the aircraft, and it would generate less power than the main engine, okay, which would require many of the non-essential instruments to be shut down in such case. Module 9, Avionics and Electronic Display Systems. This is, for me, one of the most interesting parts of this entire presentation. Okay, so let's start at first with the evolution from analog to glass cockpit. Okay, early aircraft relied on individual analog instruments, each dedicated to measuring a single parameter. There was no integration and no digitization. These instruments were mechanically or electrically driven and required extensive pilot cross-checking. Okay, why? Because they are separated from each other. Each one is located in a different site. Now, the development of digital electronics enabled the transition to integrated avionics system, commonly referred to as the glass cockpit, meaning that you can have such is such as for the case of the ECAS and the ECAM, different displays within the one or on one screen, one integrated screen. In glass cockpits, multiple parameters are processed by computers and presented on electronic displays, reducing pilot workload and improving situational awareness. Another side note I want to talk about is the term situational awareness. So what does it truly mean? Situational awareness is the understanding by the pilot of the different conditions of the airplane when it comes to the attitude, okay? So whether the aircraft is pitching up or down, if it's rolling to the left or to the right, if it's skidding, okay? That's one. Second, the airspeed. And third, the altitude, along with the VSI, vertical speed indicator, so that, and also you add to that the navigation, like location wise, when it comes to the heading, the location, the navigation related parameters, okay? So these are the main premises, the most essential type of data that the pilot needs to be aware of, and they need to be clear and intelligible by the pilot so that he can understand where he is on the map, what is his heading, his altitude, his whether he is in a leveled flight or if he's climbing or descending, okay, which is given by the VSI, the altitude again, and the attitude, whether he's in a roll to the right, to the left, or whether he's pitching up and down. This is what we call situational awareness. Another note here is most instruments used to, like during the early stages of flying throughout history, okay, for smaller aircraft, they used to be mostly mechanical, okay? The electronic systems and electrical were gradually introduced afterwards. This evolution allowed centralized data processing, improved accuracy, automated alerts, and system redundancy instead of single sensor, single display architecture, okay? Modern avionics employ multiple sensors feeding shared display systems. For example, here in this image down below, you have the attitude indicator, okay, at the same time skid or slip indicator, which is this one. So when it's moving away from the upper arrow, when the lower white arrow is moving away from the upper arrow, you would notice or you would understand that there's a slip phenomena going on, whether to the right or to the left. you have to the right here the altimeter or measurement of height, VSI next to it, which is the vertical speed indicator. It would be 0 in leveled flight, okay? And to the left, you have the ASI or airspeed indicator, also here turn coordinator, and the HSI, horizontal situation indicator, which is the compass commonly known, okay? Slip and skid indicator here, as you've seen, okay? Turn rate in degrees. So yeah, this is the turn rate here via the turn indicator. So all of these instruments are integrated in one display, okay? Of course, definitely they are not simply one instrument. No, the reading, the display is integrated on one computerized screen. Now note that in order to have redundancy, you would also have some of the instruments in analog format in case the screen fails for some reason, okay, or the computer malfunctions here. And to add to that, you would have different types of alerts, such as the stall alert and other types of alarms appearing on this very same screen, like when you have a retard in the engine, which is a maneuver during landing that was installed by Boeing. I don't remember which year, okay, and if they had changed it. And you have like the stall warnings. Yeah, different types of alarms would be indicated on this same screen as well. EFIS or Electronic Flight Instrument System. The EFIS or Electronic Flight Instrument System replaces traditional flight instruments with electronic displays driven by digital data. EFIS integrates inputs from PITOT-STATIC systems, inertial sensors, magnetometers for like the navigation and navigation sources, okay? Inertial sources to get the slip and other parameters and the RPM, for example, okay? Yeah, you have air data computers, ADC. This is the like what makes the architecture of the EFIS, the air data computer, attitude and heading reference system, AHRS, the display units, data buses, and processing units. Now, the sensor data is sampled, digitized, and filtered before being displayed, okay? The sampling frequency, meaning that you have the signal is broken down into different samples, and these samples would be coded with the binary system before being like translated or converted into useful data. The sampling frequency must satisfy the Nyquist criterion, which is Fs, okay? That would be the sampling frequency, should be greater than or equal to 2 times the maximum frequency of the signal being collected, okay? Of the frequency of the signal of the message, okay? Or the parameter that's being measured, in other words, where Fmax is the highest frequency component of the measured signal. Now, this is how it works, because it might have seemed ambiguous here. Okay, so you have a measurement of the temperature from the EGT, for example. This is the signal being collected from the EGT. Now, in order to convert it into a digital value, I need to break it down, okay, to take samples, because you cannot digitize all of, you have infinity of values within this analog signal. So I need to break it down into samples, okay? How to break it down? I should like run a sampling frequency. This is the Nyquist frequency of sampler that we're talking about, okay? Which is the inverse of the period of that sampling signal, okay? Fs is equal to 1 divided by t, and the period being the temporal distance between between 2 peaks or 2 troughs, okay? So that would be the sampling frequency. Now, this sampler, whenever is multiplying the signal and its value is 1, because it is a sequence of 1s and 0. So whenever the value is 1, what you get is a part of the signal. When the value is 0, you get nothing, okay? So let me try to make it clearer. So this is the signal, this is the sampler, correct? Okay, so when the signal is multiplied by 1, the value is kept. When it's 0, there would be no value, so you would have, okay, a chunk of values based on the sampling frequency. Now, these chunks are also quantized. Quantization meaning you take only one number from each chunk, okay, and that number should be, I'm sorry, this is sampling here, okay. Normalization, you take one value from each sample. Then quantization, this is what quantization is about. So you would have a preset number of values for the amplitudes from 1, 2, 3, 4. Okay, these are different preset amplitude values for the signal. Now, if this sample is closer to 4, okay, it would take the value of amplitude 4, okay? If it's closer to 3, it would be snapped to 3, etc. Now, for each quantized value, for each like level in the quantifier, you would have a different binary code. So let's say at 1 you have 001, at 2 010, 3 011, and 4 100. Okay? So this signal becomes, how does it become a binary sequence that can be understood by computers, which is the point. The 4 is sent as 100. Here you have, for example, 3, so 011, okay, as a sequence. Then you have here 2, which is, it's called 010. Then you have here 1, 001. Then it goes up again 1, 001, then 2, 010, 3, 011. Okay, so that sequence, when it's read by the computer, it can understand the level of the temperature at each moment and display it on the screen. And also it can now process it and analyze it, because this is what computers do best. They can analyze info and produce alerts based on this info if the values that are being measured are beyond or outside of the normal ranges of operations, okay? And they can fire an alarm or a master caution, for example. PFD, or primary flight display. The primary flight display presents essential flight information in an integrated format. Typical PFD elements include the attitude, the airspeed, altitude, VSI, and heading, which is, by the way, what we've seen some few slides ago, okay? That integrated screen, this was the PFD, primary flight display. Now, these parameters are computed using data fusion techniques. For example, airspeed is derived from the PITOT-STATIC pressure inputs, and this is how we measure the airspeed. We've seen that formula, I believe, before. V is equal to square root of 2 times a total pressure minus static pressure divided by rho. Attitude information is provided by the AHRS system, attitude heading system, AHRS systems using gyroscopes and accelerometers. The attitude solution relies on sensor fusion algorithms that combine inertial measurements with gravity and magnetic references. Now, as a reminder on how we get the value of the velocity, so you have total pressure is equal to dynamic pressure, at first static pressure, which is PS, plus dynamic pressure, which is Q. Now, dynamic pressure is equal to what? Q is equal 1/2 rho V square, with rho is the density of the air, ambient air, and V is the velocity of the flow, okay, of the airflow. So if you place it here in this equation, you get PT minus PS is equal to Q, which is 1/2 rho V square. So rho V square is equal to 2 multiplied by PT minus PS. Hence, V, the velocity, would be equal to the square root of 2 multiplied by PT minus PS divided by rho, which is the density. MFD, or multi-function display. The multifunction display supplements the PFD, or primary flight display, by presenting secondary and situational data. Typical MFD information includes navigation maps, engine parameters, weather data, which is in the weather radar, and system synoptic pages. Now here to the right, we only see the primary flight display, or PFD, because we don't see any maps, any engine parameters. They might be showing on one area or another that I'm not aware of, but this is the PFD. The MFD includes the PFD, okay, and other things such as the map and the weather data, which is not showing in this picture. Data refresh rates vary by parameter type. For example, engine data may update at slower rates than attitude data, which needs to be in real time for the situational awareness to balance processing load and display stability. R update, which is like the frequency of update, is the inverse of the period at which the parameters are being updated, which is 1/T. T is the period of refreshing, or the time lapse between two checks or two refreshing events of the data, or in other words, like the time lapse of a cycle, a complete cycle between the first refresh and the second one, and the one right next to it. Sensors, data buses, and integration. Modern avionics rely on distributed sensors connected through digital data buses. Common avionics data buses include ARAINC 429, ARINC 664, AFDX, and CAN-based systems. Data throughput on a digital bus is defined as D equal RB multiplied by N, where the data rate is D, okay, RB is the bit rate multiplied by the number of active channels, okay? So the number of active lines or active channels, you multiply it by the bit rate at each channel, okay? Because the bit rate is the same for the different channels, okay? It's stable. That would give you the overall data rate, for example, in megabit per second when we talk about the internet. It won't be that fast for aircrafts necessarily. Now, system integration allows multiple displays to access the same sensor data, enabling redundancy and revisionary capability to cross-check between two instruments displaying the same value, the same data, each one operating in a different way. One is a monitored computer, the other would be another type of electronic instrument. This architecture reduces wiring complexity and improves fault isolation. In this display, we have an aircraft sensor cheat sheet. Now, bear with me because it's not high resolution, but I will try to break it down. You have different sensors for different functionalities within the aircraft. For example, the air data sensors such as the pitot tubes, the static ports to detect the static pressure, angle of attack or AOA vanes, which are, yes, mounted, at the front. Okay, these would turn based on the angle of attack to actually measure the angle of attack of the air against the aircraft, against the fuselage. Total air temperature, TAT probe, okay, that would be a resistor that would change based on the temperature. Now, second,
You have engine sensors such as the EGT probe or exhaust gas temperature, N1 and 2 speed sensors that are, like they measure the speed of the engine based on the alternative or the alternators, okay, based on the current or the frequency of the current being generated by the engines. Fuel flow and reservoir sensors for detection of level detection based on the capacitor level or mechanically. Then vibration sensors, okay, for the vibration detection. You have navigation and positioning sensors for GPS antenna, radio altimeter, inertial reference units, IRUs, for the geolocation, and weather radar. Finally, you have landing gear and braking sensors for the landing gears, like squat switches, okay, proximity sensors, proximity to the ground. This is during the landing when the aircraft starts sounding 50 feet, 40, 30 during the landing before touchdown. Brake temperature sensors to detect the temperature of the brakes. Environmental and safety sensors such as the smoke detectors, of course, cabin temp sensors, and ice detection. Now, to the top left of this slide, we observe the illustration of the AOA sensor. AOA, of course, stands for the angle of attack. And this type of sensors works by measuring the shift in the capacitance value of this inner part of the sensor that would be on the inside of the aircraft, and the part sticking to the outside is the rudder-like winglet that would change direction based on the airstream or the airflow. So if the air is streaming in this direction, it would turn in the same orientation, okay, to face the air. If it was facing sideways, like if the air was flowing in this direction, this wing-like structure would turn around, let's say, 30 degrees up, okay, to follow the stream. And this is again how it measures the angle of attack, by measuring and comparing the shifts in the capacitance value. Because if you remember, the value of capacitance is given by epsilon times A divided by D, with A is the area of the armature that is housing the magnetic field, okay, one of the armature, not both of them, and D is the distance between these armatures, okay, in meters. Epsilon is the permittivity, okay, which is the electric characteristic of the material between the armatures. In such case, that would be the air. At the bottom left, what we have is the stall sensor. Now, this is how it works. In normal operation, the air would be streaming and flowing normally around the wing. And by the way, this sensor would be attached at the leading edge of the wing. So imagine that the wing is like this, okay? This is the wing of the aircraft. This is the leading edge, okay? So this is the direction of the wing surface. This stall sensor would be installed at the leading edge, and this is how it actually works. So let me erase a little bit over here. When the air is flowing normally and without disturbance, like when it is flowing in a laminar flow characteristic, okay, which is around the trailing edge, this means that the aircraft is generating lift, okay? At least it's maintaining itself, it's being maintained on a leveled or like controlled leveled flight, okay, whether leveled or in a descent, but the wing, in other words, is still generating lift, okay? And this is how it will work. So as long as the air is flowing normally, it would keep this switch-like sensor pushed down, okay? Now, however, when you have a stall condition, what will happen is that the air, instead of moving around the wing like this, it would move upwards, Okay, the moment it moves upwards, what would happen is that this switch over here, it would go up. Okay, it would become like this within the sensor. So it will move up, activating the stall warning, which would be like, for example, if it's connected to a stick shaker, it will activate the stick shaker. Or in this case, to the right, this switch, when it goes up, it will open a cavity, allowing the air to flow within a tube, and that tube would be connected at the end with a horn. And the horn would start, screaming. It would start whistling, indicating a stall condition that is affecting the aircraft, and this means that the aircraft is at a precarious condition, about to lose lift and to fall from the sky completely. Okay, so this is very important to warn preemptively the pilots so that they can take the proper action in order to avoid the aircraft a full stall where the aircraft would fall from the air. And now in such case, what the pilot should do is lower the nose and increase power. In fact, you increase the power first, then you lower the nose in order to gain more airspeed. And when you have enough airspeed, the flow would go like this, pushing back the button downwards, and this is what will clear the stall warning. And the aircraft would gain enough momentum within the air, it would gain enough airflow that can guarantee keeping it airborne. Failure modes and reversionary displays. Despite high reliability, avionics systems must account for sensor, display, and processing failures, because these things can fail, whether they're mechanical parts, where it applies, of course, or the electronic components, where you have sensors relying on electronics, or the electrical connections, wirings, and other devices. Common failure modes include sensor disagreement, meaning that you have conflicting data or conflicting values coming from two sensors on two instrument displays that are measuring the same value actually, okay? They are working as a redundancy. Or display unit failure, so the unit is failing, like the value doesn't make any sense. Data bus faults, meaning the connection, electrical connections, or the data bus that is relaying the data from the sensor all the way to the indication systems has a faulty connection or is problematic, or you have a short circuit. And power supply interruptions, so when you have a power failure, like for example, two engines or both engines flame out, okay, during a flight with the heavy aircraft type, what you would have in such case is like the interruption of display. Okay, why? Because these instruments are mainly powered by electricity. Reversionary modes automatically reconfigure displays to present essential information following a failure as a backup. For example, a single display may assume both PFD and MFD functions. Okay, it can integrate both PFD, primary flight display, and multi-flight or multi-function display functions. Fault detection relies on comparison logic and voting algorithms. And this is how you judge it. Let's say you have two sensors collecting the same type of data. Okay, we have two sensors for the purpose of redundancy. Now, how can we judge whether a value is correct or not? Okay, like how do we assess whether the measured value that's being displayed is accurate and acceptable, or in other words, valid, or should it be rejected? X valid is equal to 1, or a value, a measured value, would be voted as 1 as acceptable when the difference between the two measurements, which is xi minus xj, okay, so the distance or the excursion between these two measurements coming from the two sensors should not exceed epsilon. Epsilon in such case is the allowable tolerance. In case the difference between the two measurements is much larger than this epsilon value, okay, which is a small, tiny, acceptable gap between the two measured quantities. If it's larger than epsilon, then the value, the measured entity, should not be taken into consideration and the value should be rejected otherwise. Operational considerations and limitations. While glass cockpits enhance situational awareness, they also introduce new challenges, such as automation dependency and failure management complexity. Okay, so it's much more complex to troubleshoot in such case. Pilots must understand system architecture, reversionary logic, and backup instrumentation to ensure safe operation under all conditions. So if the PFD and MFD fail, pilots should be able to rely and to be able to understand and read the other instruments that are backing up the PFD and MFD, which is the primary flight display and the multifunction display. PFD is part of the MFD actually. So in case of a failure, and more than that, in case when you have an emergency that requires a manual operation, the pilot should be aware to disconnect the autopilot. Why? Because the computer systems would rely on these measurement data in order to automatically fly the aircraft. In case these values, these measurements, and the sensors, one or more of them, are faulty, so the autopilot would be operating on false premises, which can bring down the entire aircraft or cause like dangerous maneuvers to take place. So that's why the pilot should understand when to disconnect the autopilot in case you have an emergency as such, or like an incorrect sensor reading. Module 10, Flight Control Systems. Now, for Chapter 10, let's start at first with the overview of the flight control system. Flight control systems enable the pilot or automatic systems to control the aircraft's attitude, okay, pitch up and down, roll right and left, trajectory, meaning the heading, and aerodynamic performance, meaning how much lift, drag, deceleration, acceleration, stall, etc. These systems manipulate airflow and the stall aversion rather. These systems manipulate airflow over control surfaces. These are the control surfaces. And the controls are the ailerons, elevators, rudder. Okay, the control surfaces are the wings and stabilizer. Also the fuselage. Okay, so these systems manipulate airflow over control surfaces to generate moments about the aircraft's axis to enable the roll and change of direction or up and down pitching. Aircraft motion is described about three principal axes. You have the longitudinal axis, which is for the roll. This is the longitudinal axis for the roll, right and left. Lateral axis, which is this axis here this is the lateral axis, okay, for the pitch up and down. And finally, vertical axis for the yaw or the rudder, which moves the airplane to the right. It can do it without turning via the rudder, okay? Although the rudder is also used to perform an efficient roll maneuver. So longitudinal axis, which is crossing longitudinally the aircraft, and it is where the roll action takes place, okay? Lateral axis, which is about the wings, it is for pitch up and down, rotation. And vertical axis, like going in the middle of the aircraft, is for the yaw, rudder yaw, for right and left yaw motion. Control effectiveness depends on aerodynamic forces generated by control surfaces, surface deflection, airspeed, and surface area. Another note is that the elevator, when it moves upwards, okay, it is for the pitch, by the way. So when it's rotated upwards, the air would push against it and it would push the tail downward, rotating the nose of the aircraft up, okay? So in order to pitch up, the elevator should go up so that the air would push the tail down and the aircraft would turn upwards. Meanwhile, or on the other hand, if the elevator goes down, then the air would push against it upwards. So the tail would be pushed upwards and the aircraft would pitch downwards. As for the rudder, when it goes to the right, the tail is pushed to the left and the entire aircraft, the tail would be pushed sideways here and the aircraft would go to the right. But when the rudder goes to the left, so the air would push the tail to the left, okay, and the entire aircraft would be pointing to the left as well. Now, again, another explanation to break it down more simply how the elevator works. So imagine this being the elevator, okay, this part here. So when the elevator is up, the air would push it like this downwards, so the nose of the airplane would go up. All right. Meanwhile, if the elevator goes down, so the air would push it upwards, it would push the tail upwards, so the aircraft itself would go downwards. It would be pitching down. Primary flight controls. Primary flight controls are essential for maneuvering the aircraft in all phases of flight. So what are these? At first, you have the ailerons on these two sides that are responsible for rolling the airplane to the right or to the left. You have the right wing, the left wing. Okay, you have the elevators that are responsible for pitching up and down the aircraft, and the rudder, which is part of the moving part of the vertical stabilizer that would yaw the airplane. It would turn it right and left, not roll it. It would turn its heading right and left. Along, of course, when you're turning, you should be using both the aileron and the rudder so as to reduce the strain and the air pressure on the rudder alone, okay? So you should not be using just the rudder. The rudder is usually used for heading correction during landing and during takeoff. And the horizontal stabilizer that is housing the two elevators. Now, starting with the ailerons. Ailerons are hinged control surfaces located near the trailing edge of the wings. Here and here, these are the ailerons. They control roll by producing differential lift between the left and right wings, okay? So one goes down, the other goes up, so the air would push this one, okay, upward, and this part downward, so it would roll to the left, and vice versa. Now, the lift generated by a wing is given by L, which is the lift force, is equal to 1/2 rho v square SCL. S is the surface of the wing, CL is the lift coefficient, V is the velocity of the moving air, the airflow velocity, and rho is the density. Now, aileron deflection alters the lift coefficient, CL, producing a rolling moment. The moment of rho, m rho, is equal to delta L, okay, the difference or the shift of the lift force, because as you roll, the lift power decreases, okay? It actually turns into two components. Horizontal component that aids the aircraft to roll, to turn, and the vertical component that is actually would be the lift itself, okay? So m rho is equal to delta L times B, where B is the wingspan. Wingspan is this distance over here from the from the leading edge to the trailing edge. Now let's explain a little bit on how does the lift force change, okay, and what causes it to change. You see, when we spoke about the moment of rolling is equal to delta L multiplied by B, okay? Why do we have a difference of lift? And what is B? At first, B is the wingspan, which is the distance from one tip of the wing to the tip of the other wing. That is the B value, okay? Or wingspan of the wing. Now, delta L. Imagine the aircraft flying in a leveled flight, meaning it is horizontal, okay, flying parallel to the horizon with no roll, no banking. That would be the leveled flight, okay? So without any roll. And actually, yeah, when we talk about leveled flight, we talk about it's not ascending or descending. No, what I mean here is that it's flying with 0 degrees angle. So what you have is the entire lift force would be vertical, but at the same time it would be like it is always 90 degrees to the wing itself. That would be the lift force. So this force is always forming 90 degrees with the wing, and it is absolutely vertical. Meanwhile, during a roll or a turn, what happens is that this wing, okay, would be turning, let's say, 30 degrees or 40 degrees, whatever. So that angle would cause the level, okay, of or like the orientation of the lift vector to change. Now, the lift vector is always 90 degrees to the wing. However, it's no longer generating lift completely. It becomes broken down or divided into two different components. The LH, which is the horizontal component that would start like assisting, it will assist the aircraft during the motion of rolling during the turn, and the vertical component, which is the vertical part of the force that is actually generating lift. So in other words, you see, LV would be much smaller than L. Why? Because the lift force, what used to be pulling completely the airplane, is now broken down into two components. One component is LH, which is pushing the aircraft sideways and assisting with the roll maneuver, and LV, which is actually generating lift. So the differential between lift during a leveled flight and lift during a roll, so L minus LV, so to speak, multiplied by the wingspan, which is the distance from one tip of the first wing to the tip of the second wing, okay, that would give us the rolling moment of the aircraft. Elevator. Elevator is mounted on the horizontal stabilizer. That is the horizontal stabilizer. And the deflection of the elevator changes the tail force, which means it creates a pitch up or pitch down moment. So creating a pitching moment about the center of gravity, okay, of the aircraft. So the pitching moment is expressed as the moment of pitch is equal to the force exerted at the tail multiplied by the distance from the tail to the center of gravity, okay? L is the moment arm between the tail and the center of gravity of the aircraft. So to visualize it graphically, when you have the elevator pulled up, what happens is that the force would push the elevator down, okay? That would create a moment that is equal to F, or force exerted against the tail, multiplied by L. L is the distance between this line, okay, at the elevator and the center of gravity of the aircraft, which would be somewhere here, okay? Actually, it would be at the front, okay? Close to the engine, because the other parts are not so much heavy. So L would be somewhere here. That would be the L distance. Multiplied by F, the force exerted against the tail, this would give you the moment of the pitch. So where L is the moment arm between the tail and center of gravity. And by the way, in such case, it will pitch up. If the elevators are turned in the other direction, the air would push the tail up, so the aircraft itself would pitch downward. 10 to 3, the rudder. The rudder is attached to the vertical stabilizer, this part here, which is the vertical part of the tail, and controls yaw, which is the right or left-sided movement, okay? The left or right push against the aircraft. The rudder deflection produces a lateral force going this way and this way, not a row, that generates a yawing moment, like actually the rudder of the ship. The moment of yaw is equal to the force pushed at the side of the rudder, okay, multiplied by LV, which is again the vertical tail moment arm. The moment arm is actually this length here going all the way from the vertical elevator at the side, like at the point of the rudder, the connection of the rudder, all the way to the front of the aircraft. This distance is the arm of the moment that's being generated. 10.3 secondary flight controls. Secondary flight controls enhance performance and handling but are not required for basic control. Let's start with the flaps. Flaps increase wing camber, which is the wing curvature, as you see here. They are extended, and surface area, which allows higher lift force at lower speeds. Maximum lift coefficient increases with flap deflection. Okay, so the lift coefficient would be CL0, which is before the deflection or the extension of the flaps. That was like the original lift coefficient of the wing, plus delta CL, which is the lift coefficient due to or the lift coefficient change due to flap extension. This reduces stall speed, okay, which is the speed at which a wing on an aircraft can no longer produce lift. So, in other words, this allows the aircraft to generate lift even at lower airspeeds. So, V stall, or the velocity of the stall, is equal to square root of 2W, which is like the width of the wing from leading to trailing edge, I believe, divided by rho S CL max. Exactly. Rho being the density of the air times S, which is the wing section, multiplied by the maximum lift coefficient, which is the CL0 or the original lift coefficient, with the added lift coefficient that has been accounted for after the extension of the flap. 10.3.2 slats. Just like the flaps, the slats extend except from the leading edge of the wing instead of the trailing edge. And like Airbus has both of them, the slats and the flaps. Okay, so they extend from the leading edge to delay flow separation and increase stall angle of attack. So it means that they allow the aircraft to increase the angle of attack against the air, okay, without stalling, where it can stall on lower angles when the slats are not extended. And by the way, slats and flaps are usually extended during takeoff and landing. So they improve low speed handling and reduce stall severity. During takeoff, both flaps and slats are extended in case they both exist on an aircraft, okay? Some aircrafts only have flaps without the slats, so they extend in order to provide more lift to the aircraft at lower airspeeds, allowing it to take off and to lift off from the ground at lower airflow velocities, okay? And this would allow the aircraft to actually separate from the ground and fly off. Meanwhile, and of course, there is a drawback, which is an increased drag, but you don't mind having an increased drag during takeoff. Meanwhile, in landing, the slats and flaps are extended in order to increase the drag, intentionally in order to slow the aircraft down, but at the same time it uses some part, like a part of the airflow, in order to generate lift and lower the descent rate so that the touchdown would be smooth. So two objectives would be accomplished in such case. These are slowing down the aircraft, so reducing the airspeed by increasing drag, while at the same time reducing the descent rate or the VSI so as to enable the aircraft to touch down at lower descent rate and lower velocities. Then 3.3 trim systems. Trim systems relieve continuous control forces by adjusting the neutral position of control surfaces. Okay, these are the trims, like a small part of the rudder of the elevator that is controllable. Like these are trimmed, these are placed down or up in order to release the burden of continuously controlling the yoke by the pilot or even the autopilot. Trim changes the equilibrium condition without altering aircraft attitude directly. 10.4 Mechanical, hydraulic, and fly-by-wire controls. Okay, 10.4.1 Mechanical control systems. These systems use cables, rods, and pulleys to transmit pilot input directly to control surfaces, meaning that the same force that the pilot is applying to a control, that same force, that very force is being transmitted to the wing control to move it. So the pilot is directly moving the rudder or the aileron or or the levels, okay, the elevators. They are simple and provide direct tactile feedback, but become impractical for large aircraft. Why? Because they would require much higher control forces. Then 4.2 hydraulic control systems. Hydraulic systems use pressurized fluid to move control surfaces. Significantly, they reduce pilot effort. Why? Because it's no longer required to have the exact force exerted by the pilot himself in order to move these controls. So they use pressurized fluid and hydraulic systems to relieve the pilot from being strained and from applying force in order to move controls. Control force is given by F equal P multiplied by A, where P is the hydraulic pressure and A is the actuator piston area. Now, hydraulic controls allow large high-speed aircraft to be maneuvered efficiently. 10.4.3 fly-by-wire systems, or FBW. These systems replace mechanical linkages with electronic signal transmission. The pilot inputs are converted into electrical signals that are then processed by flight control computers, then sent to actuators. What the actuators does, by the way, is that the same signal that has been transmitted, okay, by the command, it would be analogous to the same action, mechanical action, executed by the pilot. So when he moves the handle, the very same movement should be replicated by the actuator, which receives a higher amplitude current, but the current would be the same value, like the same analogous signal, mechanical signal, okay, mechanical variation. The actuator would be moving the control surface. Actuators, by the way, convert electrical signal into a mechanical signal, okay, into a mechanical electrical energy into mechanical energy, and the actuator itself would be controlling the surface instead of the pilot directly. So the pilot signal would be processed by the computer as an electronic signal and then replicated to the actuator with the same frequency and the same, like it needs to mimic perfectly the action of the pilot himself, except it should be amplified, okay, so as to be capable to move the actuator. Now, the control laws ensure stability and envelope protection. The control command can be expressed as delta equal K multiplied by U, where delta is the surface deflection and U is the pilot input. They should be proportional. FBW systems allow automatic trimming, load alleviation from the pilot, okay, relieving the pilot from burden, and fault-tolerant operation. 10.5 Control surface position indication. Control surface position indication systems provide feedback on the actual position of different controls. This is very necessary, especially like, for example, during control check, where the pilot would check if the controls are responding correctly to his own input, okay, before verifying the airworthiness of the aircraft at that moment, before like taking off. This is a part of the checklist before takeoff. Sensors such as potentiometers, resolvers, or linear variable differential transformers, LVDTs, are used, okay? Sensor output voltage is proportional to surface displacement. So in other words, when the surface changes, okay, when it is displaced, it creates or changes or alters, yeah, like it creates a current. So when, for example, this air brake, this spoiler here moves upward, its own rotation would generate a current, okay? Why? Because it is like connected to an LVDT or variable differential transformer, okay, potentiometer, which means it would change the resistance value, or resolvers, etc. Different types of sensors that would be detected in the cockpit, and it would be processed and analyzed to get the significance or like the actual value of the angle in respect of the value of the current or the alteration of the current when we're talking about a potentiometer which changes the resistance value, okay? So or the voltage value being collected, okay? So that when the resistance changes, the value of voltage being detected would change. That would be like processed and analyzed to understand the current angle of deflection for whether the spoilers, whether the flaps, or like the rudders, the ailerons, all of these controls. Sensor output voltage is proportional to surface displacement, which is V equal, exactly, it is based on the voltage change. V is equal to K multiplied by X, where X is the surface position. Accurate position indication is essential for monitoring system health and detecting asymmetry, whether like one elevator is moving further than the other elevator, although, yeah, like one is moving more than the other, or the ailerons, which are very necessary for the role, like indispensable for the role. One is moving erratically in respect to the other. So this is important so as to ensure safe operation, especially in hydraulically or electronically controlled aircraft. Operational awareness and limitations. Understanding flight control system architecture allows pilots and engineers to recognize abnormal behavior, anticipate failure modes, and apply correct procedures. Modern aircraft relies on layered redundancy, which is necessary and important to ensure that in case you had a failure, another system would back you up and to guarantee a continued controllability under all operating conditions. Module 11, Hydraulic Systems. Hydraulic systems are fundamental to modern aircraft, providing a reliable means of transmitting large forces, again, as we mentioned before, with precise control using pressurized fluid. They are widely used to operate flight controls, landing gear, brakes, spoilers, thrust levers, or thrust reversers, and steering systems. Principles of hydraulics. According to Pascal's law, the operation of all hydraulic systems is based on that law of pressure. A pressure applied to a confined, incompressible fluid is transmitted undiminished in all directions through the fluid. Okay, mathematically, pressure is equal to force divided by A, which is the area that the force being applied against. So P is the pressure in Pascal or PSI, Pascal per inch. F is the applied force in Newton or lbf, pound. And A is the area over which the force is acting, whether in meter square or in inch square. If pressure is constant in a closed system, such as F1 divided by A1 is equal to F2 divided by A2, this allows a small input force to generate a much larger output force
by increasing the actuator area. In other words, you would have the force being applied by the pilot, for example, during the steering of the rudder, okay? That force would go into a smaller area, okay? When it goes to a smaller area, this force increases. Why? Because it's being constricted since the pressure is constant throughout the pipe, okay? The fluid hydraulic pipe. This will cause a much larger force to be exerted against the actuator, which would transform that force into like a mechanical force. Actually, yeah, actuator area that would cause mechanical force. Yeah, the electrical force to become mechanical, okay, moving a hard part like or a heavy control such as the rudder. All right, so the force would increase when the area section, the cross-sectional area of the hydraulic pipe decreases, which will increase this force output against the actuator, which in its turn, it would allow it to move a heavy part such as the rudder within a large aircraft such as Boeing. Force multiplication. The output force produced by a hydraulic actuator is F equal P times A. For example, with a system pressure of 3000 psi, the force would become 3000 multiplied by 2, okay, equals 6000 pounds. This capability makes hydraulics ideal for high load aircraft applications, okay? Why? Because with a small force, when you have a high pressure, a much higher force would be exerted against the sectional area, okay, at the output. Why? Because you have a high pressure being transmitted within the pipe. And by altering the cross-sectional area of the pipe, you can have a larger force at the output since the pressure is constant. So you can variate the cross-sectional area at different locations of the pipe to change or alter the pressure being outputted. Fluid characteristics. Aircraft hydraulic fluids must possess low compressibility, meaning that they should not change in volume, okay, during pressure. Thermal stability, so thermally stable, meaning that the pressure should not change also due to an alteration of temperature through hot or cold weathers, for instance. Lubrication properties, okay. Fire resistance, so they should not inflame due to heat as well. Lubrication means that they flow freely within the pipe without sticking, so low viscosity, okay? And common fluids include mineral-based fluids and phosphate ester fluids, which is the sky drone. Hydraulic components. You have at first the hydraulic pumps. Pumps convert mechanical energy into a hydraulic pressurized energy by pressurizing fluid, okay, by pushing the fluid within the piping system. Types of pumps, you have EDP or engine-driven pumps, electrical motor-driven pumps, air-driven pump, which is caused by the air pressure, and ram air turbines or RAT, which is generated, like the RAT is deployed again when you have a malfunction, a flame out of both engines on the aircraft. It is deployed and it rams, like it goes through the airflow, generating enough power to run vital instruments such as the attitude indicator, the VSI, the altimeter, okay, providing situational awareness that is very necessary in such case for the pilot so as to give him a chance to be able to land the aircraft. Pump flow rate, okay, or in other words, the volumetric flow rate. It is given by the cross-sectional area A multiplied by the velocity of the fluid. Q is the flow rate in liter per minute or GPM. A is the cross-sectional area, which is the area of the pipe at that position, okay, cross-section of it. And V is the fluid velocity. Hydraulic power delivered by a pump is given by P multiplied by Q. Okay, so PH, the hydraulic power, is given by P, which is the power, okay, multiplied by Q, or the volumetric flow rate. Reservoirs. Reservoirs store hydraulic fluid and serve several purposes. First, you have supplying the fluid to the pumps, of course, allowing air separation so as to avoid the formation of air bubbles within the pipe system, which can stifle the transmission of the fluid pressure within the pipes, compensate for thermal expansion so that when you have a thermal expansion, the fluid won't dilate, blowing up the pipes, okay, or cracking them. And now the aircraft reservoirs are often pressurized using the bleed air, which is the air from the airflow of the aircraft, or equipped with quantity indicators like sensors for quantity, okay? So again, supplying fluid to pumps, also separating the air from the fluid to avoid formation of bubbles and compensate for thermal expansion. So if the fluid had expanded, which is normal for all fluids, the thermal expansion would be dissipated in the reservoir. Hydraulic actuators. Actuators convert hydraulic pressure into mechanical motion, okay? So you have types of actuators are linear actuators, pistons and cylinders, and rotary actuators. Also, you have another type of actuator is the one that converts electrical power or electrical current into a mechanical electrical energy into a mechanical energy. Here, the hydraulic actuators are the ones, like the pieces, that convert hydraulic pressure, not electrical current or energy, a hydraulic pressure into a mechanical motion. Types of actuators, linear actuators like pistons and cylinders, and rotary actuators. The actuator force for a single acting cylinder is given by F equal P multiplied by A, with A is the area of the piston or cylinder in such case, okay? For a double acting cylinder, F extend is equal to P multiplied by A piston, okay? And the force of retraction is P multiplied by the area of the piston minus the area of the rod, okay? Like the moving rod of, the area of the moving rod of the cylinder. Now here, P is the pressure, okay, not the power. So P here is the pressure, A is the area. So the force being exerted on the inside of the cylinder, okay, F, that would be the pressure against that cylinder section here, okay, multiplied by the area which is pi r square, okay, the area of the cylinder cross-sectional area, okay, which is the cylinder bottom in this illustration. So that would be the area. The pressure is the force acting against that area. So F is equal to PA. Now for a double acting cylinder, when you have the extension, okay, like when you have the extension motion, this would be F extend is equal to P multiplied by A of the piston. When you have a retraction, like a reverse motion of the rod, okay, the pressure would be applied against the piston, the cross-sectional area of the piston, okay, minus A of the rod, okay, the cross-sectional area of the rod that's moving the cylinder, okay, that would be the force of retraction. Hydraulic system instruments and indicators. Hydraulic instruments allow flight crews to monitor system health and performance, of course. You have the pressure indicators. Pressure gauges indicate system pressure, typically ranging from 2,500 to 5,000 psi, Pascal per inch. You have low pressure warnings activate when the pressure is less than the minimum pressure allowed, okay? Now, the pressure sensor can be a capacitor, for example, that would change based on the pressure value. It would change its own capacitance based on the pressure that would in its turn alter the area, okay, between the two armatures in which exist or between which exists the magnetic field. So by altering that area, the entire field, the entire current or the entire capacity value would change, and this would be translated into the current value of the pressure. Now, quantity indicators, reservoir quantity is displayed as a percentage or volume. So, given by Q available is equal to Q total minus Q used. Abnormal quantity changes indicate external leaks for the hydraulics, okay, hydraulic fluid, or internal actuator leakage. Temperature indicators. Hydraulic fluid temperature is monitored to prevent fluid degradation and seal damage. Typical warning condition when the temperature starts becoming greater than the maximum allowed temperature, which is Tmax. How is it measured? Again, as a recap, you have a resistance that can change value. It can change its own a resistive value based on the temperature, whether it is hot or cold. So in hot conditions, when you have an overheating, the substance or the conductive material within the resistance would start dilating, okay, and separating more and more, which would increase the resistance and it would reduce or kill the current that can pass through it. Okay, that would be translated into the current temperature within the reservoir or within within the pipe, okay, for the fluid or within the reservoir. So by measuring this temperature, you can detect an overheat or some kind of problem, okay. Now, when you have a cool temperature, which is acceptable, it shouldn't be too cold, by the way, but for a moderate temperature, like the conductive material within this resistant would be close to each other, okay, allowing more current to pass through. This is how you can interpret the fluctuation of current as fluctuation of temperature and derive from it the exact value of the temperature at that moment. Failure detection and redundancy. Failure detection, you have common hydraulic failures include loss of pressure, fluid leakage, and loss of pressure can be also caused by a fluid leakage as well. Pump failure, so the pump is no longer working properly. That's why the fluid cannot be pushed through the pipes in order to activate different controls. And overheating, okay, which can degrade the chemical characteristics of the hydraulic itself. Now, failure detection relies on pressure sensors, quantity sensors, and temperature sensors. These are the three main most important sensors within the system. Redundancy concepts. Aircraft hydraulic systems are designed with redundancy to ensure safety. So as to when one system fails, another would be backing it up. Multiple hydraulic systems transport aircraft typically have System A and System B, and also standby or backup system. Each system operates independently. They need to be standalone so that the fault in one system won't trickle down into affecting the other system and taking it down with it. This is very critical and important in safety, okay, as a safety measure. PTU or power transfer units. A PTU transfers mechanical power between systems without fluid mixing, okay? So that would be the pressure in system A or the power in system A, which can also translate as a pressure, would translate into the power in system B. And how can this take place without fluid mixing? you would have, like, for instance, let me visualize it as an example. Like, you have here a valve, or not a valve, okay, somewhat like a moving part within the pipe where you have two different fluids to the left and to the right, and the pressure here would lead to increased pressure to the right, okay? This is how you would translate the power from one part to the other, okay? Now, let's talk about emergency systems. Emergency hydraulic power may be provided by electric backup pumps and RAT, or ram air turbine. Okay, the RAT deploys automatically when the normal power is less than the critical power. Okay, so one moment. The RAT, or ram air turbine, automatically deploys when the normal power, or like the current power, is less than the critical power, which usually happens when you have both engines at flame out, okay? When you have loss of both engines, loss of power in both engines. Summary: hydraulic systems enable aircraft to perform high force operations with precision and reliability by activating the actuators through hydraulic pressure, okay? By applying Pascal's law, utilizing robust components, and incorporating extensive monitoring and redundancy, aircraft hydraulic systems ensure continued operation even in the presence of failures. Another detail I may have missed to talk about is how to detect the quantities in the hydraulic fluid. Okay, now you have different methods. You can use a mechanical arm that would be pushed by buoyancy. Okay, so when you have the fluid available at that level, it would move an arm as a floater. So that arm, when it floats, it would turn and like switch on or off an electrical circuit, which in its turn, okay, it would be detected as the presence or absence of the hydraulic fluid. Or another type of sensors would be the sensor that changes capacity based on the fluid that is available between the armatures, the positively charged and negatively charged armature. Okay, so when the fluid is no longer there, when it drops, what happens is that the absence of this hydraulic fluid and the presence instead of the air between the armatures would change or alter the value of capacitance. That would be detected and interpreted as the lack of hydraulic in this level, okay, at this point. So this is how it basically works to detect the absence, okay, of or the presence of the fluid at a specific level within the reservoir. Chapter or Module 12, Environmental Control and Pressurization. Environmental control and pressurization systems, ECS, maintain a safe, comfortable, and habitable cabin environment by controlling air pressure, temperature, humidity, and air quality. Because we as humans, we cannot handle low pressure environments at 35,000 feet above the earth, okay? That's why we would need this controlled environment where like it would be livable, okay? So pressurization systems are necessary and essential for high altitude flight, allowing aircraft to operate efficiently while protecting passengers and crew from hypoxia, which is the lack of oxygen, and decompression hazards, in which like a low pressure would cause a high pressure of your own body. Okay, the blood within your own body would try to escape. It would start pushing outwardly against your skin. Why? Due to the low pressure. Cabin pressurization principles. The need for pressurization: atmospheric pressure decreases exponentially with altitude, reducing the partial pressure of oxygen, okay, which can lead to suffocation.
more than suffocation, you have the problem of decompression, okay? So above approximately 10,000 feet, supplemental oxygen or pressurization becomes necessary. Standard atmosphere pressure variation, okay, pH is equal to P0, which is the sea level pressure. Okay, pH is the pressure at an altitude h, is equal to P0 multiplied by the exponential of minus m, which is the molar mass of air, multiplied by g, gravitational force, or acceleration rather, times h, the altitude, divided by RT, R being the universal gas constant, and T is the absolute temperature. So this is how fast the pressure decays with altitude, which is why it is necessary to provide pressurization, having enough oxygen in a contained environment. Cabin differential pressure. Cabin pressurization maintains a cabin altitude significantly lower than aircraft altitude. Okay, in other words, the apparent pressure within the cabin would be much higher than that at the outside of the aircraft itself. Okay, so the key parameter is differential pressure, which is delta P equal the pressure of the cabin on the inside where the passengers are sitting, minus the ambient pressure, which is the pressure of the atmosphere outside of the aircraft. Typical transport aircraft limits are a maximum delta P of 7 to 9 psi, Pascal per inch. This is the acceptable difference or differential pressure. Cabin altitude would be 6,000 to 8,000 feet at cruise. Now, we have structural considerations to be taken, to be minded. The fuselage must withstand cyclical pressurization loads. Why? Because you have the internal pressure is going, like it is pushing against the skin of the airplane, and it has the tendency to move the air to the outside in order to attain equilibrium. So you have the hoop stress against the fuselage in a cylindrical fuselage is given by sigma h is equal to delta P times R divided by T, where delta P is the difference of pressure between the cabin and the external, multiplied by R, which is the radius of the fuselage, divided by T, or the skin thickness. So let me draw it for you. Let's say this is the fuselage, a section cut of the aircraft, and these are the different passengers sitting. Okay, the radius would be from the center to the external circumference. This is R. The thickness is the thickness of the skin of the aircraft. Okay, thickness of the metal, that is T. So sigma h, which is the structural hoop stress, is given by pressure differential, or the difference of pressure between cabin and ambient, delta P, multiplied by the radius of the fuselage, divided by T, which is the thickness of the skin of the aircraft. Air conditioning systems. Functions of aircraft air conditioning are the following: temperature control, to provide a more moderate temperature that is comfortable to the passengers, ventilation and air renewal, humidity regulation, so that the humidity within the cabin would be acceptable. Also, pressurization, air supply. Now, ACM or air cycle machine systems, most modern aircraft use air cycle refrigeration rather than vapor compression systems. So the air is compressed by the ACM compressor. Secondary heat exchanger removes the heat from the air. Then expansion through turbine produces cooling. Okay, the ideal gas relation, and you might be familiar with that from the class of physics. You have PV equal nRT, okay? Pressure times volume equal nRT. R is the constant of the gas times temperature. Temperature change during isentropic expansion is T2 equal T1 multiplied by P2 divided by P1 to the power of gamma minus 1 divided by gamma. Gamma, I'm trying to remember if it's something like it is a constant that has to do with the gas. I will pick it up. One moment, okay? And temperature control, mixing hot and cold air achieves desired cabin temperature. So Tmix is equal to M1 T1 plus M2 T2 divided by M1 plus M2. This is the minimum temperature, okay, given by mass 1 times T1, the original temperature, okay, plus M2 T2, like the cooling air, okay, divided by M1 plus M2. This is the exchange temperature formula, okay, between the gas that's going in and that is existing in the cabin, okay, during a heat transfer, okay, or a cooling transfer here in this case. Another side note here is that when we talk about isentropic expansion, what happens in such case is that the gas would be expanding in volume or increasing in volume without an alteration of temperature, meaning without losing its heat or cold characteristics to the transfer system, to the pipe system. So, which is another word called a fixed entropy. So it won't lose its entropy. Plus, more than that, the process is reversible, meaning that you can reverse the process without incurring any friction or drag that will change the characteristics of the gas. Also, as for gamma in this formula, it is the calorific capacity or the heat capacity for a specific gas in respect of the volume. Bleed air systems. Bleed air sources. Okay, what is the bleed air? The bleed air is extracted from engine compressor stages, low or high pressure, auxiliary power unit or APU. This is the main starter at times of the engines, okay? In case something wrong happens, the APU would restart the engine in mid-flight. Ground air supply. Okay, bleed air pressure typically ranges from 30 to 50 psi with temperatures exceeding 200 degrees Celsius. Bleed air control, pressure regulating, and shut-off valves maintain safe operating limits. Okay, the pressure of bleeding should be less than or equal to the maximum acceptable pressure. Heat exchangers reduce bleed air temperature. Okay, which is Q equal MC delta T. Okay, the mass of the air times C, the calorific capacity, multiplied by the temperature at the input minus temperature at the output. Okay, so this kind of exchange for the heat and cold, it controls like the environment or the atmosphere within the cabin, and by keeping it within the acceptable limits so as to not have like an over a high temperature or a very cold temperature. Bleed air distribution. Bleed air supplies air conditioning packs, pressurization system, which is the system that keeps a pressure similar to sea level altitude pressure within the cabin, okay, to maintain the comfort of the passengers, and wing and engine anti-ice systems, which is the de-icing boots that are inflated, deflated continuously during icing conditions in order to prevent the formation of ice on the leading edge of the wing. Okay, bleedless aircraft concepts. Modern aircraft, which is like Boeing 787 Dreamliner, use electrically driven compressors, reducing fuel burn and maintenance, which is very important. Okay, so it uses electrically driven compressors to lower the fuel consumption rate. Okay, this would reduce the fuel burn and it would be better for maintenance. It would also reduce maintenance. This, in fact, would lower the strain or like the pressure on the engines. This is how it lowers the consumption of the fuel. Okay, why? Because it would be mainly driven by power, electrical power, then rather than mechanical power derived from the engines themselves. Pressurization instruments and warnings. Cabin pressure indication. Okay, the key cockpit indications include cabin altitude, cabin rate of climb and descent, and differential pressure, okay, So the cabin rate of climb is given by DHC, difference of altitudes, divided by dt, or the derivative of altitude in respect of time, okay, cabin altitude. Pressure sensors and controllers. Electronic cabin pressure controllers, or CPC, regulate outflow valves based on flight phase, okay? So delta P commanded, or differential of pressure, is given by F. It is a function, in other words, of the altitude and cabin altitude, W, and phase during the flight. Now, outflow and safety valves. Outflow valve, primary pressure regulation to adjust the pressure by releasing some of the held pressure within the cabin. Safety valve, overpressure protection. So in case you have an overpressure, it releases the pressure to also reduce the strain and the stress against the skin of the aircraft, the fuselage. Negative pressure relief valve also, this would be to increase the pressure instead. All of these working together would keep the pressure of the cabin at an acceptable value. Overpressure condition is given by delta P greater than delta P max. In other words, for the overpressure condition to be met, the difference between the cabin pressure and the external pressure should exceed a certain threshold for it to be considered as an overpressure, which would be dangerous against the skin of the airplane and also against the passengers, okay, at times. Warnings and emergency systems. Okay, you have cabin altitude warning horn, typically at 10,000 feet. Automatic passenger oxygen deployment, which occurs when you have a sudden depressurization of the cabin or decompression, or in other words, loss of cabin pressure. And third, master caution and ECS alerts. ECS, of course, stands for Environment Control System. Time of useful consciousness decreases with altitude. Why? Given the fact that as the altitude increases, the pressure of the air, or the density rather, decreases, which also leads to a starvation in oxygen. So the hypoxia becomes more severe and more prominent. Actually, it would occur at a shorter period at high altitudes. So this is why the time of useful consciousness decreases as altitude increases. Decompression scenarios. You have a slow decompression. This is usually when you have a small leak or crack within the airframe. So it would start manifesting as a small depressurization, very gradual, very slow, and very minimum, okay, of the cabin. So it would be like a small leakage. Rapid decompression, when you have a sudden blow in, for example, let's say you have the hole of a bullet, okay, a hole caused by the bullet, that would cause a rapid decompression and a rapid loss of cabin pressure. And third, explosive decompression. This type of decompression would rip the airframe apart, okay? Like in one of the instances, it was a flight over the ocean. Don't remember the number of the flight, but what happened is that the decompression actually ripped off the entire upper part of the fuselage, okay? So, and by the way, in some instances, it brought airplanes down. So it can be very serious. Now, the cabin pressure decay is given by dP over dt, so which is the decay of pressure or the decrease of pressure in terms of time. That would be less than 0, okay, for abnormal condition. Now, summary. Environmental control and pressurization systems integrate pneumatic, which is the wheels, okay, the brakes, thermal and control subsystems to ensure aircraft safety, comfort, and structural integrity throughout all phases of flight. Chapter 13, Landing Gear and Braking Systems. All right, now for this chapter, the landing gear and braking systems enable safe ground operations, including taxiing, which is rolling the aircraft on the pathway before getting to the runway. The taxiway is the inner, like the inner runways that are not made for or designed for takeoff. Then takeoff, landing, and rejected or aborted takeoff scenarios. These systems must absorb high impact loads, provide directional control like steering on the ground, and ensure reliable stopping performance under a wide range of operating conditions, meaning that the braking system should be highly performant and work very intensely, even when you have severe conditions like an emergency landing with no flaps and with a high load of fuel still being carried on board. Okay, so they need to perform an immediate, almost an immediate or short stopping, okay, without overshooting the runway, guaranteeing the safety of the landing in such case. Landing gear types and configurations. Functions of the landing gear. The primary functions of the landing gear system are to support the aircraft weight on the ground, absorb landing and taxi shock loads like a damper. So you have a damper to absorb these shocks, just like the wheel of a car. Provide the braking and directional control. Again, directional control is, in other words, steering. Okay, because the aircraft, in order to turn left or right, it needs to be steered via the wheels themselves as long as it is on the ground, okay, before it gets to the takeoff runway. And also, finally, enable retraction to reduce aerodynamic drag in order to increase the efficiency of the flight and reduce the drag. Retraction meaning that like the wheels need to be pulled back up, okay, and housed or sealed within their housing compartments. To the right here, we see an illustration of the landing gear. So you have down lock and drag brace, okay, which is the lock when the gears are extended so that they won't budge during landing, okay. Metering pin extension, okay, rotation lock pins, yeah, after braces, oleo cylinder, okay, many parts here, axle beam assembly, sensing wheel, okay, you have sensors also on the inside, tires and wheels, these are 4 tires here, brake assembly, that is part of the braking system, axle beam fold and compensating actuator, which by the way, as the wheels run, they generate power, okay, that would be sensed like read as a signal that the landing is, that there's a touchdown. So when you have a rolling of the wheels, this would work like an actuator, okay, an alternator, I'm sorry, generating a signal. That signal would be read by the computer system and interpreted as a touchdown that is successful, okay, that the landing gear has touched the ground, and which would enable the RTO, like the auto brake system, to fire off, okay. And here you have the retraction actuators, which would be fed by a power, an electrical power, and actuators again convert from an electrical energy here in this case to a mechanical energy to retract back the wheels to like pull them back to their housing, okay, during the flight. And so you have rotation actuators, okay. Landing gear configurations. You have tricycle landing gear, the most common configuration in modern aircraft, consisting of 2 main gears and a nose gear. Advantages include good ground stability, and improved pilot visibility. Okay, you have tail wheel, which is conventional landing gear, consists of two main wheels and a tail wheel. More common in older or lighter aircrafts, but less stable during ground operations. And this is where, when the aircraft lands, it would be in a nose up position, which has the drawback that the pilot would have a hard time seeing the ground. Okay, but it wouldn't be that serious here in such case because the aircraft is not as large as the ones such as the Boeing 737 types and larger. That's where you would need a lower pitch during landing so that the pilot can see the runway. And multi-bogie landing gear used in large transport aircraft to distribute weight over multiple wheels, reducing pavement loading. The ground pressure in such case would be W divided by A, where W is aircraft weight and A is the total tire contact, total tire area, but not the area exactly of the tires, but the area of contact between the tire and the tires in total and the ground. So that would be the part of the tire that is actually touching and in direct contact with the terrain. Shock absorption. Most aircraft use oleo-pneumatic shock struts combining compressed gas as a damper solution and hydraulic fluid. Energy absorbed during landing, this is how you evaluate it, okay, because you have speed of landing, which would be descent speed, and the mass of the aircraft. So the energy that would be generated is a kinetic energy equal to 1/2 mv squared. M is the mass of the aircraft and v is the velocity of the touchdown. Strut force approximation would be F equal PA, pressure multiplied by the area of contact. Retraction and extension systems. Actuation methods. Okay, so the landing gear extension and retraction may be accomplished using hydraulic systems. This is the most common, okay, through the hydraulic power being transferred via pipes. Using electric motor driven systems, okay, like actuators that would receive an electrical power then converted into a mechanical power, or pneumatic systems, which is, has a limited use. Okay, hydraulic retraction systems. Starting from that, okay, hydraulic actuators extend and retract the landing gear using system pressure. As we've mentioned before, the actuator force would be F equal pressure times cross-sectional area. The actuator speed is given by V equal Q divided by A, where Q is the volumetric flow, which is the velocity multiplied by the cross-sectional area where the flow of the fluid is taking place, okay? Or through which the fluid is flowing with that streamline velocity, okay? With that circulation velocity. Up locks and down locks. Mechanical locks secure the gear in the up or down position, preventing it from budging or from retracting by mistake, for example, if it was extended, or extending falling down and dropping and extending by mistake if it was retracted, especially during mid-flight. Down locks are critical for landing safety and are often gravity assisted. Okay, they are assisted with gravity. So as the aircraft lays its own weight on the terrain, on the runway, that very same weight driven by gravity is what locks the landing gear in place. Okay? Emergency extension. Now, in the event of hydraulic failure, emergency extension methods include gravity free fall systems. This is when you have an emergency landing and there are no hydraulics that are necessary to drive the extension of the landing gear. So in such case, you would extend the landing gear using the gravity free fall system. Okay, like you would release it from the lock, from the up lock, to extend on its own weight. You have another choice would be manual hand pumps, okay, in other types of aircraft, and blow down systems using compressed gas in order to push the landing gear in place, okay, forcefully. The potential energy which aids this free fall would be EP equal mgh, which is the mass of the landing gear times g, the gravitational acceleration, times h, which is like the height of the gear from its extended position. Now I want to revisit the necessity for having locks, whether an up lock or down lock, for a landing gear system. So why do we need the locks to begin with? At first, the landing gear is so much heavy in weight. Once it is extended, it is subject to massive aerodynamic loads. That's why we need a guarantee that it won't budge. It won't retract by mistake, and it would be fixated, like it would be stable during the landing. Okay, it won't like collapse by due to the aircraft's weight. Okay, now more than that, keep in mind that the hydraulic system is not fail safe. Okay, is not completely not reliable, the word, but you cannot guarantee it fully. Okay, it has the possibility to fail, so you need something that would lock the landing gear to ensure, okay, to make sure that it would stay in place during the landing. That's why we need the both systems, you know, the up locks and down locks. For the up locks, what you have is like a spring driven roller that will enter in place, okay, like a hook. When you have the landing gear retracted, that will guarantee that it won't drop on its own weight. Okay, actually during emergency landing, when you know the hydraulic system fails, which is, by the way, this is what releases the landing gear, it would be the hydraulic system disengaging this hook, okay, turning it in order to allow the gear to be retracted via the hydraulic pressure. When you have a failure, you need to allow the gear to drop on its own weight through the force of gravity, and you have a safety button that would release the hook, allowing, you know, the gear to be retracted again by the force of gravity. As for the down lock, when you extend the gear for the purpose of landing, you have another hook that will go in place. Actually, it is a side brace that will go ahead of the landing gear on purpose, and this side brace, once the gravity pulls down the aircraft, actually this side brace would be pushed like yeah, the landing gear would have the tendency to go back in a straight formation. However, the gravity would itself, it's a very intelligent trick, the gravity itself would be pulling that brace sideways in order to like guarantee that the landing gear would always remain fixed, okay, in the same position. So it would push it outward. Meanwhile, this strut, like this brace, was having the tendency to push it inward, okay, landing gear. So once the aircraft lands, the gravity itself would push this brace outward to guarantee the landing gear having like a straight standing on the runway without any possibility for it to retract by mistake. Brake systems and anti-skid. Okay, wheel brake systems. Modern aircraft use multi-disc hydraulic brakes located in the main landing gear wheels. The braking force required would be FB, or force for braking, is equal to mu multiplied by N.
Mu is the coefficient of friction, and N would be the normal force, okay, exerted by the rotating wheels, like the gear wheels, against the wheel itself to allow it to brake, just like the brake of your own car. The braking torque is T equal the braking force multiplied by R. R would be the radius of the wheel, of course. Kinetic energy dissipation during landing or rejected takeoff, brakes convert kinetic energy into heat. This is how they actually stop. Okay, so EK, or kinetic energy, is equal to 1/2 m, the mass of the aircraft, multiplied by v squared. V is the velocity of the aircraft. Now, I might have made a mistake, which wasn't like a mistake, but it was not accurate when I mentioned in previous slides when I said that the velocity is actually the descent speed. No, it is actually the both the vertical and horizontal velocity. It is the velocity vector altogether. Okay, it's not the vertical or horizontal component alone. Okay, mostly the horizontal it would be. Okay, now it's actually divided into horizontal and vertical components, the sum of which would give you the velocity. So the brake temperature rise is given by delta T. Okay, the rise of temperature is equal to EK divided by MB CP. CP is the calorific capacity. Okay, heat capacity, and MB is the mass of the brake. Anti-skid systems. Anti-skid systems prevent wheel lock-up by modulating brake pressure. Okay, so this is how they work. So they prevent wheel lock-up by modulating the brake pressure, meaning the brake pressure would be converted into a current, and this is what would be used. All right. So wheel slip ratio is lambda equal to velocity of the aircraft minus the velocity of the wheel divided by the velocity of the aircraft. Optimal braking occurs at a specific slip ratio, typically 10 to 20. Okay, the auto brake systems automatically apply braking after touchdown to achieve a selected deceleration rate. A equal delta V over delta T, or dV over dt. The acceleration is actually the derivative of the velocity in respect of time. Now again, the slip ratio, how is it measured? It is equal to V aircraft minus the velocity of the wheel divided by V aircraft. But how do we get these values? You see, the velocity of the aircraft is given by the airspeed or the ground speed. Okay, the ground speed during the landing, it would be more accurate. The velocity of the wheel can actually be detected by the alternator that is connected to the wheel. So as the wheel rotates, it would generate a current, and by detecting or measuring the frequency of this current, you can evaluate or calculate the velocity of the wheel. Okay, so we subtracted from the velocity of the aircraft divided by the V aircraft. That would give you the slip ratio. Okay. Gear position and warning systems. Landing gear indication. Cockpit indicators show the status of the landing gear. So if you have green lights, it means that the gear is down and locked. Red or amber lights, it means that the gear is either unsafe, which is it did not lock properly, or in transit. Now, you have different types of sensors to get that type of information. Okay, so the gear position is sensed using proximity switches, limit switches, and WOW, or weight on wheels sensors. So what is the difference between these three types of sensors and how do they actually work? If we start with proximity switches, these are the switches that do not detect the position of the landing gear via a direct contact, but instead they are like detectors of proximity. So when it's retracted, if it's in proximity of the sensor through the measurement of the inductance or sending a signal and receiving a return signal like a sonar, so to speak, or like a perimeter detection. This is how it senses the position of the gear. Now, for the limit switches, unlike the proximity switches, they work in direct contact. So when the landing gear is locked upwardly, so if it's retracted and locked, once it's locked, it comes in contact with the switch that would fire a signal to the cockpit that it is up and locked. Otherwise, if it's locked down, so that would be the uplock. If it's locked down, also, it would be in direct contact with a switch to indicate that it is extended and locked. For weight on wheels or WOW sensors, they work through strut compression or decompression. So, and it is a very completely almost different mode than the operational mode of the proximity or limit switches. So when the landing gear is fully extended and on the ground, it would be compressed, the strut would be compressed. Meanwhile, when the landing gear is retracted, it would be decompressed. Warning systems, oral or visual warnings, alert the crew of unsafe configurations. Okay, so you have, for example, unsafe landing condition when throttle is low and gear not down. Brake and tire monitoring. You have modern aircraft include brake temperature monitoring system or BTMS, so which considers the operation normal as long as the temperature of the brake is less than or equal to the maximum allowed temperature. Because as you know, that the heat is used as a way to slow down the aircraft by converting the kinetic energy into heat, okay, during touchdown. And as long as the temperature is acceptable, okay, the airplane remains under safe conditions. Now, the tire pressure monitoring ensures structural integrity. So the pressure of the tire should be like it is equal to F divided by A, which is the area of contact between the wheel or the tire and the ground. Okay, so the temperature of the brake again should be evaluated via like the RDS, okay, RDS resistance system, so as to detect whenever the temperature becomes overheated in a dangerous way. Actually, this once has caused a fire on board and downed a DC-9, I think, in Saudi Arabia, okay, many years ago. It was around 1984, something like that, okay, I don't, 1986, yeah, around that period of time, okay, and the entire fire was caused by the overheating of the landing gear, okay, that had its own rubber ripped off, okay, because it needed a change and it wasn't changed on that day. So that compromise lit the entire aircraft on fire. Summary: landing gear and braking systems integrate structural, hydraulic, and electronic subsystems to ensure safe ground operations, effective stopping performance, and reliable crew awareness through indication systems and warning systems. Chapter and Module 14: Ice and Rain Protection Systems. Ice and rain protection systems are essential for maintaining aircraft safety and performance in adverse weather conditions, especially during extreme cold and icing. Why? Because ice accumulation can significantly degrade lift while increasing drag and weight to the airplane, disrupt airflow into engines also, and sensors. Okay? And this leads to erroneous instrument indications and readings, okay, due to the icing within the engine. So, aircraft are therefore equipped with a combination of anti-icing, de-icing, detection, and warning
systems. One of them is the de-icing boot. In one of the flights, and it was during a cold weather, I think it was an MD-11, not remembering exactly, okay, which is like a more contemporary DC-10. So what they had is, because of icing, okay, the ice broke off the wing, both of the wings, and went into the engine, causing an entire flame out. So this is how important de-icing is, okay, and rain protection. So what happened during that day is that the de-icing was not as efficient as needed, which brought down the entire airplane after the flame out, okay, and caused some people to actually perish during that event. Types of aircraft icing 14.1. You have atmospheric icing conditions. Aircraft icing occurs when an aircraft flies through visible moisture, clouds, rain, snow, fog at temperatures near or below freezing. Supercooled water droplets freeze upon impact with the aircraft surfaces. Okay? Atmospheric icing is most likely in the temperature range T between 0 and minus 20 degrees Celsius. So, atmospheric icing is most likely in the temperature between 0 and minus 20. Types of ice accretion. Clear ice, which forms from large supercooled droplets that spread before freezing. It is dense, transparent, which is the dangerous part because it cannot be easily spotted, and difficult to detect visually. Second, rime ice, which forms from small droplets that freeze instantly, creating a rough edge, a rough surface, opaque, and brittle texture, which is even more dangerous. And third, mixed ice, a combination of clear and rime ice together, often forming rapidly in severe icing conditions, which is the case for the aircraft I mentioned like moments ago, okay? It had both a clear and rime ice together. Now, the rime ice, like some of it washed off during takeoff, okay? But the clear ice kept stuck against the surface of the wings, which, severely, like it kind of broke off during takeoff and went into the engine, okay, causing engine flameout. Aerodynamic effects of ice. Ice accumulation modifies airfoil shape and affects its lifting properties also, okay, and disrupts boundary layer flow. The lift equation is given by L equal 1/2 rho v square, and this alone is Q, or the dynamic pressure of the flowing air, multiplied by S, which is the wing area, times CL. CL is the lift coefficient. Icing reduces the lift coefficient, CL, while increasing the drag coefficient, CD. Now let's look at the formula of the drag. D is equal to, again, Q, which is 1/2 rho v square, or the dynamic pressure of the flowing air in motion, times S, which is the surface of the wing, multiplied by CD, or the drag coefficient. So the drag coefficient would increase while a decreasing, or meanwhile, what would happen with the lift coefficient is the exact opposite. Okay, it would decrease. So the lift curve, notice here in this graph, airfoil with ice, the lift has dropped like immensely, okay, more than 60%. Meanwhile, for a clean airfoil, the lift coefficient would be much higher, okay? And this would be noticed based on the variation of the angle of attack, okay? That it would increase the stall velocity, okay? The stall airspeed. Now, the drag curve, as you see, for the airfoil with ice, the drag would increase extremely even after the third quadrant. Meanwhile, the drag would be would remain nominal for a clean airfoil. What would be the structural and system hazards of ice and rain systems? Let's start with ice. So you would get an increased stall speed, so the aircraft would stop producing lift even with higher air speeds compared with a clean airfoil. Reduced control effectiveness, so even the controls would not respond properly due to ice formation, and engine flame out or surge, which is the case that we've spoken about, and it can happen both in extreme rain, okay, very dense rain, and during when the ice breaks off the wings, which what happened with the MD9. I think I'm sorry, it was the MD11. Okay, it has a similar design like the DC-10, the McDonnell Douglas aircraft. Okay, since the two engines are mounted at the rear, okay, at the tail, and situated above the wings, when the ice broke, it went right through the engines, causing both to flame out. All right, so this is what caused the accident in that event. And also, it can lead to blocked pitot tube and static ports, which also in its turn would cause erroneous readings of the airspeed. Okay, as we mentioned before, because in one of the cases the pitot tube was blocked by something else other than ice, which leads to the same result. So the airspeed seemed to be very slow during takeoff. Why? Because the density of the air was very high, restricting the flow of the air from moving through that blocked pitot tube. But once the aircraft became airborne, due to the decrease of the pressure, not the pressure, like the density of the air at high altitudes, the air right now in this phase started to flow much quicker within the pitot tube, leading to an erroneous reading of overspeed. But at the same time, after a while, the aircraft had stalled. Okay, so these conflicting readings had disturbed and confused the pilots, and the aircraft went down. Okay, like killing everyone on board due to that faulty pitot tube system, and which was caused by this blockage. Pitot and static heating 14.2. Purpose of pitot-static heating. Pitot and static systems are highly susceptible to icing. Okay, heating prevents the blockage and ensures accurate airspeed by melting the ice before it accumulates and while it's still forming within the tube. So this would lead or would guarantee accurate airspeed, altitude, and vertical speed measurements and indications. Electric heating systems, pitot probes, and static ports are typically heated using electrical resistance elements. The electrical power dissipation will be measured by P equal R I square. Okay, R is the resistance and I is the current, electrical current, which is equal to VI. V is the voltage times I. Okay, same thing. The heat generated must exceed the convective and latent heat losses. So it should be hotter, much hotter than the formation, like in order to compensate for the formation of ice and to have enough time to melt them. So the heat generated must exceed convective and latent heat losses. Q of heat, the capacity, temperature capacity of heat, should be greater than the loss Q. Okay? And this is the architecture of the pitot system. You have ellipsoidal nose, flow in, and flow, static pressure hose, spaces, supporting stem, static pressure, total pressure here, and alignment arm. Failure effects
Blocked pitot or static ports lead to erroneous indications. So for the pitot blockage, it would affect the airspeed, as we mentioned before, which would read 0 or frozen. And static blockage would lead to erroneous altitude and VSI readings, okay? So that would get you a frozen altitude and VSI. The pitot heat monitoring, you have systems on board include current or temperature sensing to detect heater failure. Okay, so the measured current, whenever it's less than the minimum current, that would indicate a fault occurring. Okay, in other words, you don't have enough current going through, so the heater is not working. Okay, this is how it's detected, whether through current sensing, okay, if you have a current going through it, or through temperature sensing. So if there's no heating, it means like the sensor won't capture any heating. It wouldn't be like presenting normal values. So this means that there's a drop of temperature, okay? And a cold temperature would reflect at the resistance level with a low resistance or high current. Like this would be the exact opposite of the modus operandi of the current. For the current system, when you have a low current, when you have a low current, it would mean you have a fault. Okay. Wing and engine anti-icing systems. 14.3. Thermal anti-icing systems prevent ice formation by maintaining surface temperature above freezing, okay, via heaters, for example. You have the bleed air anti-icing, in which a hot compressor bleed air is routed through wing leading edges and engine inlets, okay. The heat transfer rate, so it would be like an air conditioner for the aircraft leading edge, okay. The heat transfer rate would be, its formula is Q equal mass MCP, okay, so the mass of this air multiplied by Cp, which is the heat capacity, times the temperature of the bleed minus the temperature of the surface of the wing, okay. So the temperature of the bleed should be hot enough in order to transfer that heat to the surface, avoiding the accumulation of ice. Surface temperature condition should be greater than 0 degrees at all times in order to avoid the freezing conditions and the formation of ice. Electric anti-icing, used in smaller aircraft and modern bleedless designs. Okay, the electrical heat flux is given by Q equal P divided by A. Okay, the de-icing systems remove ice after it forms, okay, like the de-icing boots, which inflates and deflates by a constant feed of air pressure, and this is how it breaks the formation of the ice, okay. So Q again is equal to P divided by A, okay, we covered it. Pneumatic de-icing boots. These are rubber boots that are installed at the leading edge of both wings, and they inflate and deflate cyclically in order to crack and shed ice. So this is how they prevent the icing conditions. Inflation pressure condition is the following. The pressure of the boot should be greater than the pressure of ice adhesion that's forming on the leading edge. Second type is sweeping wing systems, where porous panels release anti-icing fluid continuously that would lower the freezing point. According to the following formula, this is how it would be lowered. So the freezing temperature would become equal to the original freezing point, T0, minus Km, which is the rate of
temperature drop per meter. Finally, engine ice protection. It protects engine inlets and fan blades to prevent flame out and compressor damage, just like the aircraft that we mentioned before. The engine airflow requirement is given by mass of the airflow entering inside or flowing on the inside of the engine is equal to rho, which is the air density, multiplied by A, or cross-sectional area of the engine, times V, which is the velocity of the air flow. Ice detection and warning indicators. Ice detection methods, you have the visual detection, where the pilot observes the ice on wing, leading edges, or windshield frames. Second, probe-based ice detectors, which would be like more accurate. You have vibrating probes that detect frequency changes due to ice accretion, a very smart way to detect ice. So these vibrating probes, as they generate frequency and as they detect the frequency fluctuations, okay, so because once you have ice formation, it would change the vibration frequency. So that would become F equal 1 divided by 2 pi square root of K over M, where the ice accumulation would increase the mass M, okay, reducing the frequency of the vibration of wings. You see here in this picture the vibrating probe, the strut, mounting plate, and the housing. Another note here to be added is that K is actually the stiffness of the probe, which is measured in Newton per meter. Electronic ice detection systems. Capacitance-based sensors, this is one of the models, and optical ice detectors, okay? Now, for the capacitance-based sensors, and we've mentioned that before, the capacitance change is given by the formula C is equal to epsilon A divided by D, where A is the area of the armature, the charged armature that's housing the magnetic field, and D is the distance between both armatures, the plus and the minus, the one that is charged positively and the one negatively. Now, what changes due to the icing formation is epsilon, which is the electric property of the material. Okay, so epsilon, it would change based on whether you have air within the capacitor or water or whatever. So this change would be interpreted and it can be measured so as to assess what you have on the inside, okay, and what type of ice even, okay. So if you have a pure ice, it would be detected as an exact value of permittivity, which is epsilon is given by epsilon r divided by epsilon 0. Epsilon 0 is empty space permittivity. Another interesting part of the detection is the optical ice detectors, okay, which can read or detect the presence of ice based on the optical reflection of light on it. Okay, that would be a little bit more advanced, but even also complex. Warnings and indications. So ice advisory or caution messages would be like firing inside the cockpit, automatic activation of anti-ice system or the de-icing system, and master caution alerts. Operational limits and certification. Aircraft icing certification is defined by FAR /CS 25 Appendix C, safe operation condition, which is what defines the ice accretion rate, should be less than or equal to the protection capability against that ice. Because you can get to a point where like the de-icing boots can no longer work effectively in order to break all the ice that has formed on the wings. Summary
Ice and rain protection systems integrate aerodynamic, thermal, electrical, and sensing technologies to prevent or remove ice accumulation, ensuring reliable aircraft performance and accurate instrument indications in adverse weather conditions. Chapter or Module 15, Fire Detection and Protection Systems. Fire detection and protection systems are critical safety systems designed to rapidly detect, warn through a notification on the alarm panel, okay, on the display panel in the cockpit, and suppress fires in aircraft compartments. Because in-flight fires pose an immediate threat to aircraft integrity and occupants. These systems are designed with high reliability, redundancy, and clear crew indications, which means that they can be counted upon to warn and to suppress fires, okay? And they are redundant so that the system would be fail-safe. In case one sensor had failed, you would have multiple other sensors that can detect the same thing. This is below an illustration for different fire sensors that are mounted. Of course, one of them would be inside the engine, okay, another would be at the wings, different compartments of the aircraft. Here you would have the fire detection card that would measure the change of the resistance. Usually the detector would be the RDS, that is a resistance changing because of the temperature or the heat. This card would send the detected signal to the AMS. Okay, once actually it detects fire, it would send the warning or like the alarm back to the cockpit. Okay, you have like fire indicators for the engines, both left and right, and you have the fuel control cutoff that would be necessary in case you have a fire in one of the engines, plus an extinguisher that would extinguish the fire within the engine. That would be in flight. Also a speaker that is connected to this card for an early warning of fire on board. So in this illustration, you have the engine fire extinguisher bottles. Okay, these are mounted to the engine. You have a controller that would be connected to the engine and APU fire panel. Okay, this button would be pressed in order to extinguish the fire by activating these two extinguishers in case of engine fire. And the warning systems all are connected also to the engine sensors, okay, and the extinguishers, all of that panel. Fire zones and detection methods. 15.1. Fire zones in aircraft. So the fire zones are areas where you would have a potential fire, okay? These are the zones where fire detection and or suppression is required due to the presence of flammable components or fluids or any type of wiring that is susceptible to heat, and like you can consider anything that can be incendiary, that can cause a fire event or that can feed into a fire. So any area of high temperature or electrical equipment, electrical wiring, electronic components, like the areas near the wings which house the fuel, definitely. All of these, okay, require the capability to detect the fires and also to suppress the fires, all the way to like extinguish fires on board. So these fire zones include engine nacelles, auxiliary power unit, APU, compartment, which starts the engine in mid-flight in case of a flameout. It can start the engine on the ground as well. Usually they started using like a power truck. Cargo compartments, also the undercarriage, because you have luggages that are susceptible to fire. Lavatories, or the bathroom on board, and also electrical and avionics base. Each fire zone is classified based on accessibility. What are these classes? You have Class A, which is accessible in flight, like the lavatory, for example. Class B, inaccessible, but with fire detection and crew intervention. Okay, that would be like it can be intervened for via the crew, okay, and it can, like the fire can be detected. And finally, Class C is inaccessible with fixed fire suppression, like the engines, for example, okay? These are inaccessible. Fire detection methods. Thermodetection. Thermodetectors sense abnormal temperature increases. So you have overheat detectors that trigger at a preset temperature, and rate of rise detectors that trigger on rapid temperature increase. So overheat trigger at a preset temperature value, but the rate of rise detector type, it triggers on rapid temperature shift, but it would be an upshift, a sudden increase or a rapid increase in temperature. That would be the trigger. The rate of rise condition should be greater than the critical rate of rise for it to be considered as an incendiary event that should be alarming for the crew, okay? That should trigger the alarm. So dt over d lowercase t, which is the change of temperature in respect of time, or the derivative of the temperature in respect of time, should be greater than the critical change for it to be considered alarming and trigger the notification at the cockpit. Now, the detector works like this. So you would have an RDS, which is like a thermal resistance, that would change its value. The resistive value would change based on temperature. So when you have an overheating event, the material within the resistance, which is a conductive material, would start dilating, and the molecules would start going apart from each other, which would decrease the value of the current going through it. Okay, so once this current value decreases, that would be perceived as an overheat, as a high temperature. On the other hand, like in reciprocity, when you have a cold temperature or a normal temperature that's not hot, this conductive material would be compressed against each other, okay? So it would be recessed and it would be close to each other, allowing more conductivity and more current to flow through. That would be perceived by the system, by like the device, the card, the detection card, as acceptable low temperature. So in other words, it would be an indicator that the engine is running without overheat, okay? And there's no fire on board. Continuous loop detection. Continuous sensing elements run through fire zones and change electrical characteristics, mainly the resistance value, when heated. Resistance variation is given by RT, so the variation of resistance in respect of the temperature, because it would be a function of temperature, is equal to R0, which is the original resistance in cold weather, okay, the original value of the resistance, multiplied by 1 plus alpha delta T. Delta T is the temperature change, multiplied by alpha, which is the resistance sensitivity to temperature variation, okay? Alpha, or the sensitivity of the RDS, of the thermal resistor or thermal resistance detector, is given by 1 over R0, the original resistance value, multiplied by the derivative of the resistance in respect of temperature, okay? Or the change of resistance rate, the change rate in respect of the change of temperature, or the R divided by dt. Optical and smoke detection, which is another type, used mainly in cargo compartments and lavatories, and it uses the light scattering principles. So, the amount of scattering of light, or the percentage of scattering of light, is proportional to the number of smoke particles. Now, let's elaborate further on how the smoke detector works. You see, the smoke detector is made of, on the inside, of a light source that would be projecting its light on a photodiode. The photodiode is like a diode that is sensitive to light. So, as long as it is receiving light, it would be conducting the current, acting as a closed circuit, okay? A closed switch. Now, when smoke goes between the light source, so during a smoke event, when the smoke goes between this lamp and the photo sensor, the photodiode, what will happen is a blockage of light, even if it is a partial blockage depending on the sensitivity. This blockage of light, when the smoke prevents that light from getting to the photodiode, would cause the photodiode to actually switch off, meaning it becomes like an open switch, okay, creating an open circuit, interrupting the current that's being detected on the other end, okay, by the electronic card. And this would be perceived, so this dip of current, of electrical current, would be immediately perceived as smoke on board, which is, by the way, very important because it is like an early warning system for incendiary events. In other words, the fire might have started in a compartment or in an area where you won't have necessarily a detector, a heat detector. Even like when you do have, at times, the heat detector is a little bit slow to act. Why? Because it takes time for an area in the aircraft to heat up, even if it's not a long time, but it would take some few minutes for that detector to heat up in order to signal an alarm in the cockpit, okay, of a fire. However, the smoke detector would detect the fire even before it actually develops and becomes mature. It would detect the smoking event, which is due to the overheating before, like while the fire is still under control, okay? While the fire is still smoldering before developing into destructive flames. This is the very importance of smoke detection systems. 15.2 Fire warning systems. Fire warning architecture. Okay, the fire detection systems interface with cockpit warning logic to provide clear and unmistakable alerts. Typical indications include master warning lights, fire warning lights like engine fire and APU fire would start flashing, and auto warnings, which is the fire bell, okay, fire horn. The warning logic and redundancy. Most systems require confirmation from multiple sensors in order to confirm that there is actually a fire on board. So most systems would require confirmation from multiple sensing devices in order to prevent false warnings. Because if one resistor breaks off, it can sound a wrong or a false fire alarm. That's why we need redundancy and backup so as to get the information from multiple sensors at the same time so as to confirm that there's indeed a fire on board. You have two loop logic, so fire warning is equal to loop A and loop B at the same time, okay? So the intersection between loop A and loop B. And fault detection logic, the fault is equal to loop A XOR loop B. That is an electronic logic over here. This actually means that both A and B should be detecting a fire, okay, in order for that to be considered as a fault, okay, as a fire event. So in other words, let me write it down. This is the electronic XOR. So this is A and B. If A sensor had detected a fire while B sensor had not detected fire, so that would be considered as no fault, okay? There's no fire. If A did not detect a fire, but B did. Also, it's considered as negative, okay, negative alarm. So there's no fault so far. But if A and B both had detected fire, then this would be considered as a correct fault alarm, okay? This would be like perceived as real fire detection, okay? So it would be validated. So if A is yes, B is no, A no, B is yes, or both are zeros, by the way, also. If both did not detect a fire, then also that would be negative. Meanwhile, only if A and B both had detected fire, then this would be considered as a valid alarm, as a valid fire detection on board. Fire handles and crew interface. Fire handles allow the crew to shut off fuel supply in order to try to mitigate the fire and stop feeding it, isolate bleed air in order to suffocate or to starve the fire from oxygen. 3, disconnect electrical power, also to like disconnect to try to shut off any other contributing factors to the fire through electrical energy. And finally, arm fire extinguishers in order to extinguish the fire, especially within the engine. 15.3 Fire suppression agents and controls. Fire suppression principles. The fire suppression removes one or more elements of the fire triangle. This would be the heat, fuel, and oxygen. The three of them need to be taken into consideration, okay, and worked on in order to extinguish the fire. So the heat through cooling, the fuel to cut off what is feeding the fire, and starving the fire from oxygen in order to suffocate it, okay, to put it down. The heat release rate is given by Q equal mf delta hc, okay? That is the heat release or transfer rate, equal to the mass of the fluid being, used for extinguishing the fire, multiplied by delta hc. Fire extinguishing agents, you have the halon agents, traditionally used due to effectiveness and low toxicity, okay? The suppression effectiveness condition is given by C of agent of the extinguishing agent should be greater than or equal to the minimum capacity, okay? Minimum extinguishing capacity. As for the formula, Q equal mf delta hc, m is the mass of the extinguishing fluid again, and delta hc is the differential of the heat of combustion, okay? So this would be the factor that would play a role in the extinguishing or the fire suppression. Alternative agents, environmentally friendly replacements include HFCs and inert gas blends. You have water and foam used in lavatories and portable extinguishers. Fire bottle discharge systems. Fire bottles are pressurized containers discharged electrically or mechanically. Discharge mass flow rate is given by M equal CD, capacity of discharge multiplied by A, square root of 2 rho delta P. Rho is the density and delta P is the differential of pressure between the inside of the extinguisher, okay, like the inner gas of the bottle, and the pressure outside, on the outside, which is, in such case, the pressure of the cabin, in case you are extinguishing something within the cabin, okay? Or in general, it would be the pressure of the outside environment, all right? So M is equal to capacity of discharge times A, which I believe to be the area of the hose, times square root of 2 rho. Rho would be the density of the fluid, the suppression fluid, multiplied by delta P, or the differential of pressure between the inner container of the extinguisher and the external ambience or the external atmosphere. Now, time-limited protection for cargo compartments, okay? So that time-limited protection would be given by CT is equal to C0, original capacity, multiplied by E, the exponential of minus KT. Now, in case you are wondering, C is the capacity of the extinguishing agent or the fire suppression agent within the bottle is given by the original capacity multiplied by the exponential of minus KT, with K being the decay rate of the agent, okay, because the agent concentration would decay with time. So after a specific interval of time, it would no longer be reliable and effective in fire extinguishing, and it would need to be replaced. Multiplied by T, which is the time. Okay, so this would be the formula correlating the running capacity or like the current capacity in factor of time and decay. 15.4 System testing and safety procedures. BITE or built-in test equipment. Okay, modern aircraft use BITE to verify system integrity. Test condition is when the test passes, all the channels would be nominal. It would mean that all channels are nominal. Crew fire tests, cockpit fire test switches verify detection loops. Warning, because it's a loop circuit, okay, around a resistance that would detect the fire. And that resistance value would change based on the heat that is exposed to it. Warning lights and bells, these are the indicators and the sounding alarm, and fire handle illumination, which means that, for example, the engine fire would light up the fire handle, okay? It would be lit in order to verify that the alarm is actually working. The indicator is correctly functioning. Maintenance safety procedures. Okay, you have fire bottles, safety pinned before maintenance, electrical power isolated, leak and pressure checks performed, bottle pressure verification. So the pressure of the bottle should be greater than the minimum pressure. That's why it has like a pressure sensor, a pressure measuring device in bars. Okay, that would be like a needle, an instrument for measuring the pressure of the extinguisher itself. Certification and reliability requirements. Fire protection systems must comply with FAR/TS25 requirements. Okay, now the system reliability for redundant detection loops is given by R equal 1 minus R1 times 1 minus R2. That would be two resistors that are working together in order to verify the occurrence of fire. Final summary, fire detection and protection systems combine thermal, optical, and electrical sensing with robust warning logic and suppression mechanisms in order to ensure rapid response to fire hazards and maintain aircraft safety throughout all phases of flight. Module or Chapter 16, Warning, Alerting, and Monitoring Systems. Okay, modern aircraft rely on integrated warning, alerting, and monitoring systems to ensure timely crew awareness of abnormal conditions. These systems prioritize information, reduce pilot workload because there is too much automation going on, and enhance safety by combining sensor data with alert logic and human-centered display philosophies. In other words, you would have all the possible alarms that you would want to see being displayed on the MFD, the multifunction display, with all the indicators for the engines, the oil pressure, all of that on one screen, usually one extended screen or multiple 2 or 3 screens, okay, for redundancy, and all the warnings or the alarms that you would need, that would be required, or the notifications would be displayed on these screens integrated with the instruments themselves. So you would have an indicator for the engine. Also, in case there was a problem, a warning would fire on that indicator as a LED description, okay, for what's happening on the inside of the engine as an abnormal functionality or something wrong going, okay, as an abnormal behavior, so to speak. You have also the sound. You have the different, like the master caution, the fire warning, all of these displays that are very important in order to give awareness to the crew of the different situations on board, okay, of the different like of the current conditions for the engines, for the cabin, and different compartments of the airplane. Master caution and warning systems. What's the purpose and philosophy? The master warning and master caution systems provide immediate crew attention to unsafe or abnormal aircraft behavior or conditions. The master warning indicates conditions requiring immediate crew action, like a prompt action in order to alleviate, like in order to prevent a more serious, dangerous behavior in the airplane and to alleviate like the problem promptly and swiftly before it can develop into a more serious, more dangerous situation. Master caution indicates conditions requiring timely but not immediate action. Okay? Now, these systems act as attention getters rather than diagnostic tools. They are only designated to warn, okay, the crew in order so that the crew would act promptly to like rectify the faults and troubleshoot the problems. Activation logic. Warnings and cautions are triggered when monitored parameters exceed predefined thresholds. Okay, the threshold logic. So the alert would be a warning when X is greater than or equal to a critical value, whatever X would be. Okay, so when you exceed a specific operational value, that would become a warning. Okay, but a caution, unlike the warning, like it's a little bit different than the warning, that you would have a specific margin of error, not allowable, so to speak, but it would be less than the warning. So the master caution is when you have a value between two different values, the first one being the first limit, okay, and the second one would be the critical limit. So, for example, when you have a device that starts overheating, it did not yet cross the critical value for it to be a warning. So it would be displayed as a caution. Why? Because let's say the engine had started overheating, it had not hit yet like the critical value that would start causing a damage to the engine and that would lead to a fire, okay, to an engine backfire. However, the value had stepped above a minimum threshold where it started to become more serious, but it's still less than the critical, the X critical for it to qualify as a warning. So it entered into a precarious margin between the first limit, which is like a start of a or a development of a serious problem of overheat, but below a critical value or threshold where it would be considered, for example, as an engine fire starting within like the engine housing. System architecture. The master alert system integrates sensor inputs, system computers that analyze these inputs, visual annunciators like for example the master caution alarm and the visual indicators within the cockpit, and you have the aural alerts like the sounders and the horns that would sound a specific kind of frequency in order to bring the crew to attention, okay, to trigger the crew alert. Redundant channels improve reliability, so you would have R is equal to 1 minus R1 times 1 minus R2. These redundant channels would improve the reliability of the sensing device and the detection mechanism. So when you would have more than one system, more than two systems actually running together to detect the same thing, you would have more reliability and the detection would be more trustworthy, okay? The detection system. Annunciators and alert logic. Annunciator panels. So annunciators provide system-specific alert messages using lights, text, or symbols. But you have different color coding conventions for that. Okay, based on the convention, so the red would indicate a serious warning. That would be like the highest kind of alarm, the most serious, crucial, or dangerous type of warnings or alarms would be a warning designated by a red coloring. Second to it, you would have an amber indication, which means caution. So the difference between the warning and the caution, as we mentioned before, the warning is when a specific value X exceeds the maximum allowed threshold. Okay, so it becomes very serious, like when the fire breaks out in the engine. Meanwhile, the caution is during the engine overheat, the X value would be above a specific value, which is the minimum value, so as to designate it as a warning, like a serious problem, but below the like a designated value for fire, okay, but below the maximum allowed value of heat to like acceptable value of heat before the warning fires off. Okay, so the caution would be when the X value is between a minimum critical, okay, above the minimum critical, but below a maximum acceptable. That would be the most dangerous threshold. Now, for the green indicates the normal operating conditions, and finally blue would be advisory. Alert prioritization. Multiple alerts are prioritized to prevent crew overload. The priority ranking should be evaluated as follows. The priority for an alert is a function of severity and time criticality. How much time critical, or in other words, how much an alert cannot wait before it should be fixed. Also, how severe the alert is. Only the highest priority alert is presented orally using the sound buzzer, okay, or the sounding alarm horn. Alert inhibition and logic. Alerts may be inhibited during certain flight phases to prevent nuisance warnings. Inhibition logic example, when the alert is equal to 0, okay, the alert should be equal to 0 if H is less than the H of inhibitance, okay? So the alerts may be suppressed during certain flight phases because they don't make any sense in such case. So they should be inhibited, okay, because they present a nuisance and a distraction for the crew. Alert confirmation and filtering. To avoid false alerts, systems require persistence or multiple confirmations altogether, summed up in this integral. Okay, this integral function would sum up multiple systems, or multiple confirmations coming from different kinds of sensors, different types of measurements, in order to verify whether the alarm is valid and true, or if it is a false alarm. So the sum of all confirmations should be greater than the X threshold. It is the sum of multiple confirmations, multiple sensor measurements that had led to these conclusions on different instruments at the same time, on different measuring sensors. So the sum of all of these indications in a specific period of time or during the time of detection should be greater than the X threshold that is needed in order to fire the actual alarm in the cockpit. So you might have different measurements that don't add up at times, you won't have an alarm. But when different sensors that are measuring the same thing from different angles come up together and they sum up to a value that crosses the threshold of detection, that would be validated as a true alarm, okay, as a serious problem that needs to be indicated in the cockpit. Meanwhile, if you have only one sensor acting up, other sensors that are measuring the same thing, they are not giving that result, in such case, you would suspect that this is a fault in the sensor itself, not a real warning or a real event that is taking place. Because sensors are prone to short-circuiting, they are prone to false measurements, or if they break up, they would also signal a false alarm. 16.3 ECAS and ECAM overview. ECAS is the Engine Indication and Crew Alert System. ECAM is the Electronic Centralized Aircraft Monitor. Okay, now for the ECAS or Engine Indication and Crew Alerting System, the ECAS integrates engine parameters altogether and alerting into a centralized display, commonly used in Boeing aircraft. The monitored engine parameters include N1 and N2 speeds or rotations, which is the RPM percentage of N1. For N1 is the low pressure compressor, which is at the beginning stages of the engine. N2 is the high pressure compressor, which is a high pressure blade compressing the air against a stator blades in the middle of the engine. Okay, they have like small ventilations between the blades so as to guarantee a higher pressurization of the intake air on the inside of the engine to lower its to condense it, lower its temperature, so that when it combusts, it would expand so quickly, creating an efficient thrust. Second indicator is the EGT, or the exhaust gas temperature, by which you would measure the temperature of the gas exiting the hose of the engine. 3, fuel flow, which measures the flow rate of the fuel. And 4, the oil pressure and temperature, okay, because a low oil pressure would indicate a malfunction or a rollback in the engine. And temperature of the oil is also very important. The engine parameter limits should be between X normal and X max, okay, before an alarm would start being sounded, okay, before a notification appears in the cockpit. The ECAM, or Electronic Centralized Aircraft Monitor. ECAM used in Airbus aircraft provides both alerts and associated procedural guidance. Okay, so the ECAM logic: alert would lead to a procedure display, okay, in order to inform the crew on how to rectify the problem. You have system pages automatically present relevant information to the crew. It's like a checklist that is displayed by the computer on the screen. Alert levels: you have level 3, that would be a warning, red, very serious alert. Level 2, that would be caution, okay, amber color. And level 1, that is advisory and white, meaning only informative but no no serious problem is taking place. For example, if we look at the right display here for the ECAM, so you have flat control, okay, so you have slow spoilers, you have the hydraulic B reservoir overheat, meaning a hot temperature in the hydraulic B reservoir, and B system low pressure. Also, the failure message is a low pressure in the B reservoir hydraulic system. Okay, now flat control, so this hydraulic low pressure is affecting the spoilers, okay, so you have a low control of the spoilers, which are the air brakes, require hydraulic pressure in order to be deployed. So because of the low pressure, which is due to a reservoir hydraulic overheat, this is leading to a low spoiler or slow spoiler deployment, okay, or flat control. Crew interaction: the crew response time is critical, so the time of the response should be less than the allowed time to wait before taking action. Why? Because it is required to promptly jump into the checklist and to swiftly rectify the problem, especially when you have a critical fault in the aircraft. Acknowledgement silences auto alerts but does not clear the fault. So, okay, so the crew response, it would acknowledge silence, auto alerts, and it should not, like, they should clear the fault after that. Okay, so the time of response or the time allowed, that would include from the time when the alarm is sounded until the time that the crew should start responding to the fault. Now, response time is by definition the acknowledgement silence all the way to rectify the fault. Now, in this display, lower display, you have, for example, landing gear is inhibited, okay, during flight, APU bleed, okay, you have no alarms here, just indications. This is the quantity of oil, fuel that has been used, okay, CAS, cabin VAS, okay, feet per minute, altitude of the cabin in feet, which is 4,150, indicating the pressurization of the cabin, okay, and different other measurements as well. 16.4 Human factors and situational awareness. Human factors considerations. Alerting systems are designed with human limitations taken into account, okay, in mind, including the attention span of a person, the reaction time that needs to be invoked in order to rectify and troubleshoot the problem, and workload, meaning a person cannot focus on multiple things, especially if they are taxing if they are taxing work assignments, he cannot focus on multiple things at the same time to effectively do them all. Okay, and situational awareness. Situational awareness, or SA, consists of 3 levels. Okay, what are these 3 levels? Perception of elements, comprehension of meaning of these elements being involved, and projection of future status. The situational awareness effectiveness is equal or is a function of I, C, and T, where I is the information quality that's being displayed on the screen. C is the cognitive processing. Cognitive processing means that the person is understanding the data that's being displayed and what it means. Okay? And a function of time, meaning the time that it takes the crew or a pilot in order to read the data that's being displayed on MFD, for example, or ECAM, be able to also process that data and drive from it a meaning, okay, like an analysis and an assessment to the current situation. So T is the time that it would take the pilot in order to understand and read these parameters and to analyze what these parameters actually mean. So again, another thing, that from these parameters, when they are analyzed by the pilot, he can project for future processing, meaning he can understand what the airplane is going to do next, especially when you have, for example, an airplane during a climb. He would understand that at this speed you would have a stall, outside of this speed you would be safe. So he needs to, so that he would lead the aircraft to guard specific margins of airspeed, of angle of attack, in order to enhance the performance of the entire flight. Workload and information management. Pilot workload increases with alert frequency. Okay? When you have multiple alerts, the workload for the pilot becomes so unbearable at times. Proper alert filtering reduces the overload and the overwhelming of the pilot. So the number of presented alerts should be less than the number detected, so as to represent aggregated alarms, okay, in a way that the most crucial alarm would have a priority, okay, and the precedence over the less critical alarms. Also, the alarm from which other problems would stem, that root alarm would be displayed first and foremost. Let's say, for example, to give you a simple scenario. Okay, so in your house, let's say the power is cut and you have different sensors connected to your TV, to your fridge, to other utilities within the house. So all of these would go down. Can you imagine the amount of alarms that you would getting from your telephone, from your TV, your microwave, your fridge, okay? But all of that become very distractive to the person. Why? Because the root alarm is a power cut. So the alarm that has a priority over other alarms should precede and should be displayed first and should be the glaring alarm on the screen. Okay, because all the other problems stem from the very first main alarm, which is the root cause for other systems being shut down. The design philosophy, modern alerting systems follow principles of consistency, clarity, meaning the alarm should be clear, the indication should be readable, clear, and understandable. It should make sense for the pilot and to give him an idea of understanding over what situation has came up and what is going on within the aircraft. Okay, now prioritization, meaning again the alarm that is most serious should be displayed above the other alarms that would stem from that very same problem. And also minimal distraction, which means using the alarm that is the most important and crucial to be solved first in precedence to other types of alarms. Finally, warning, alerting, and monitoring systems combine reliable sensing, intelligent alert logic, and human-centered design to maintain crew situational awareness and ensure timely, effective responses to abnormal aircraft conditions. Also, if I may go back to the previous slides here, when we've spoken about consistency, what does consistency mean? So consistency is that the alarm is always reproduced in the same manner. Okay, so whenever you would have a problem of that same sort, the same alarm would be displayed. That would be the consistency and in a consistent way. So it's not like at times detected, but at other times it would be missed. No, there's an importance for consistency in the display and the display analogy and also the clarity of the display and what each alarm actually means. Chapter 17, Integrated Aircraft Systems, Case Studies. Starting with the introduction, modern aircraft are highly integrated systems in which avionics, propulsion, electrical, hydraulic, pneumatic, environmental, and flight control subsystems operate as a coordinated whole. Understanding these interconnections is critical for pilots, for engineers, and maintenance personnel, as failures rarely remain isolated. One failure would lead to another. Okay, not one failure can bring down an airplane. It would be a sequence of events. This module synthesizes acknowledge or the knowledge from previous chapters and applies it to operational scenarios and real-world case studies. Briefly, not too much extensively. 11.2 System interconnections and dependencies. Aircraft systems are designed with multiple layers of dependency to optimize efficiency, weight, and safety. Electrical, hydraulic, and avionic integration. Many primary systems rely on electrical power generation and distribution. Engine-driven generators supply AC power. Transformer rectifier units, TRUs, convert AC to DC and rectify the voltage level, meaning that if you have a low voltage, it would bring it back to the correct level, or if it was a high voltage, it would pull it down to stabilize the voltage being produced, okay, just like the power supply, by the way. The rectifier in the power supply in the UPS system works the same way. DC buses power avionics, sensors, and control computers. Okay, so these three are powered by or fed by the DC buses. Electrical pumps provide backup hydraulic pressure. The electrical power balance may be expressed as P gen, or the power that is produced by the generator, is equal to the power consumption of avionics, power of the hydraulic system, power of environmental system, which is the air conditioning, plus the lost power, which is the transmission losses, okay, or the power losses within the transmission lines, okay, the power lines, the electrical wiring, resistance, and other stuff that waste power due to heating effects, okay. We're not talking about dangerous heating, but every wire that has a current passing through it would generate heat, so not all the power would be effectively used by the different systems of the aircraft. Some part is wasted. 11.2.2 Pneumatic and environmental dependencies. Bleed air extracted from engines supplies cabin pressurization, wing and engine anti-icing system, air-driven hydraulic pumps. Okay, bleed air mass flow is given by M is equal to rho AV, where rho is the density and A is the cross-sectional area. V is the velocity of the airflow. So rho is the air density, A is the duct cross-sectional area, and V is the airflow velocity. Again, so the bleed air extracted from the engines would supply the cabin pressurization, making sure that the pressure in the cabin is comfortable for passengers. The wing and engine de-icing systems, like the de-ice boot at the wing leading edge and engine heating. Air-driven hydraulic pumps, okay? So these three are the main systems powered, okay, or that consist the pneumatic system, and they are powered by the, or like fed by the pneumatic system. Flight control and sensor integration. Fly-by-wire systems integrate air data computers, or ADC, inertial reference system, IRS, which is called, by the way, in Boeing 777, I think, ADRU, Air Data Inertial Reference Unit, flight control computers, or FCC. Control law inputs may be simplified as delta is equal to a function of alpha q Vn, where delta is the control surface deflection, alpha is the angle of attack, q is the pitch rate, v is the airspeed, and n is the load factor. Okay, so the deflection of the control surface is a function of the angle of attack of the air, which resists that deflection, q, which would be the pitch rate, v is the airspeed of the flow, the airflow, and n is the load factor. Normal, abnormal, and emergency scenarios. Normal operations. Under normal conditions, systems operate within design envelopes with full redundancy available. Monitoring systems continuously verify that system pressures and temperatures are nominal, electrical bus integrity is correct, and data consistency between redundant sensors, meaning they are pulling the same correct values. Okay, that is data consistency. Abnormal scenarios. Abnormal operations involve partial system degradation without immediate safety threats, such as single generator failure, hydraulic leak in one system, and sensor disagreement warnings when two sensors are conflicting values. Reliability of redundant systems is expressed as R total is equal to 1 minus pi, which is the sum of 1 minus Ri, the different reliability factors, okay, from 1 to n, depending on the number of the independent channels. Emergency scenarios. Emergency conditions require immediate crew action, such as dual engine flameout, smoke or fire warnings, rapid decompression. Okay? Time critical response may be modeled as T response should be less than the critical time, which is the time before loss of controllability or survivability. 11.4 Real-world accident and incident analysis. Okay, now this would hopefully be more expounded like in a different session. So let's start here with some scenarios. System interaction failures. Many accidents result from cascading failures rather than a single fault. Exactly what we mentioned before. Typical contributing factors include sensor failures leading to incorrect automation behavior. So the autopilot would be relying on false data in order to control the aircraft. Misinterpretation of warnings, that would be a human factor error, and loss of situational awareness where the aircraft loses vital instruments and no longer can tell whether he is going up or down, pitching, whether he's in a roll, in a dive, in a climb, all of these things, especially during night flights. Okay, example, analytical chain, you would have sensor fault leading to incorrect data, leading to automation response that is incorrect. Why? Because it's based on false premises and false data collection, which would also get us to a crew confusion. Okay, that would be the final result, which can be fatal, by the way. Human-machine interface considerations. Alert overload probability increases with system complexity. So the probability for error is directly proportional to the number of alerts multiplied by the cognitive workload factor. So as the number of alerts increase within the cockpit, this becomes more taxing to the pilots in order to deal with it. Okay, so the crew would become confused. Plus, you add to that the cognitive workload factor, how much cognitive ability the crew has in order to deal with the number of alerts that are being displayed. So when you have a high workload, okay, that would decrease the ability to factor in the different alerts and to deal with them, which would increase the human error, okay, that can happen during the processing and the troubleshooting of the fault. 11.5 System failures and troubleshooting approach. Fault isolation philosophy. Aircraft systems use structured fault isolation, which means that the pilot should identify the affected system, verify indications, and cross-check sensors, because you would have different readings at times from different sensors. So he needs to verify that the fault is actually occurring. 3. Apply checklists and procedures in order to troubleshoot the problem. And 4. Isolate the failed component. Logical troubleshooting model. Troubleshooting follows Boolean logic. So F, which is the system failure, is equal to A, standing for power availability, and B or C. B stands for sensor integrity, which means the sensor is together and working properly, and C stands for or represents the control logic health. So, in other words, for a system failure to check out correctly, to pass, in other words, also, for a system failure to be validated as failure, as an existing fault, it should meet the following conditions. A, at first, meaning the power should be available, A should be true, and at the same time, one of these two arguments would be true. So, either the sensor integrity is standing also, which means that the sensor is reliable for the measurement, and or C, which is the control logic health, would be true. So either one of them is true or both of them is true, and the power is available at the sensor. This would check out correctly with a correct system failure being reported to the cockpit or the notification instrument, the notification display. Let's talk about BITE, or the built-in test equipment. So what is it about? Modern aircraft employ BITE systems to record fault codes or register fault codes, for later assessment or online like real-time assessment and troubleshooting. Perform post or power on self-test. By the way, this is the very same procedure that your own computer performs the moment it starts up. So when you start up your computer, before loading the operating system, what happens is that the firmware, which is stored within the ROM, the read-only memory, it is loaded at first, and it runs and it goes to check the different faculties or different boards of the system, such as the RAM, random access memory, which is the dynamic memory of the computer, the hard drive, different chips, different USB buses, your hard drive itself, your CD-ROM, if you have one, if you still have one. So the same operation, and by the way, this is the operation that runs, and once everything has been checked correctly, this is when the operating system would be loaded and your Windows would start on your own computer. So the same process goes for aircrafts. The airplanes do the same thing. You have a post test, and when the post checks out correctly, so when it passes, the aircraft passes the test, especially in the Boeing 777 Boeing, it will beep twice, signaling that the system had worked correctly. It had passed all the tests and everything is proper and in order. Okay, so the same thing goes for your own aircraft. And this is when you would see the displays such as the PFD, MFD, all different displays would run. They would open up. Okay, now, third, to assist in maintenance diagnostics. So the BITE system is necessary to assist in diagnostics, to understand what kind of faults have occurred or occurring during the flight or during ground operations, okay, during ground maintenance. Summary: integrated aircraft systems demand a holistic understanding of interdependencies, failure propagation, and human factors. Effective monitoring, well-designed alerting systems, and disciplined troubleshooting procedures are essential to maintain safety in increasingly automated aircraft environments, because aircrafts are becoming more relying on computer systems than manual pilotage, so to speak. Chapter 18, Maintenance, Inspection, and Troubleshooting. Now, let's start with the introduction. So, maintenance and troubleshooting are critical elements in ensuring the continued airworthiness, meaning the flyability of the aircraft, reliability, and safety of aircraft instruments and systems. This module introduces systematic troubleshooting philosophies, how to troubleshoot, modern diagnostic tools, inspection and replacement procedures, and the structured use of maintenance documentation in accordance with aviation regulatory standards. Basic troubleshooting philosophy. Okay, you have the systematic approach. Effective troubleshooting follows a logical, step-by-step process designed to isolate faults efficiently while minimizing unnecessary component replacement in order to precisely locate the fault, okay, and the fault source. The general philosophy includes verifying the reported fault, understand normal system operation so that we can differentiate between the fault and the normal operation of the system, identify symptoms and affected subsystems, isolate the fault through testing and analysis, rectify the fault and verify correct operation. Okay, the troubleshooting efficiency can be expressed as eta is equal to n correct, which is the correct approach, divided by the total, like the number of correct fault identifications is n correct, divided by all or the total troubleshooting actions performed. That would give us the troubleshooting efficiency. You can say here, this is a metric that measures the difference or the ratio between all the correct actions that had been taken in order to rectify the problem versus the total number of actions that some of which might not have been the correct measures to be, decided over in such scenario. In order to kind of memorize these steps that should be taken in order to troubleshoot, we can take the first letter of each sentence here and place them all together with one word. Okay, so that word would be VUIIR, which is verify the reported fault, understand normal system operation, identify symptoms, isolate the faults through testing and analysis, and rectify. Okay, so VUIIR, verify, understand the normal system operation, okay, then isolate the fault to check which are or what are the systems that have been affected through testing and analysis. Then, okay, so identify the symptoms, what is going on, then isolate, and finally rectify the fault or the problem. Fault isolation logic. Fault isolation commonly relies on decision trees and Boolean logic in order to identify a system fault. So let's say F is the system fault. A, B, C, and D represent contributing conditions such as power availability, signal integrity, sensor input, or control logic. So let's start with that. And we need to understand the Boolean logic so that we can understand when is a fault validated and identified as being a legitimate fault, not a glitch within the system. Now let's understand the Boolean logic so that we can learn when does the system check out as being failed, okay, or when does a system failure check out to be a true failure, not a system glitch, and based on what premises. So F is equal to A and B or C and D. What are A, B, C, and D? A is the power availability at the sensor. B is the signal integrity. So in other words, whether the signal is together or if it's like kind of cracked, can it be reliable and trustworthy? Can we read it and rely on its value? C, and C is actually the sensor input, okay, the input at the sensor. And finally, D is the control logic. So CTRL logic. Now, according to this formula over here, for F to be validated as a true system failure, either A and B should be true or C and D should be true. So A and B should be true. Okay, to give you a picture here. A and B should be true, meaning that A should be 1 and B also should be 1. If either of them is 0, it would give 0, which is false. Okay, so if one of them or both of them is 0, the result would be 0. Okay, now for C and D, the same thing. Both of them need to be true, okay, for the result to give true. So C and D both should be 1 to give 1 as a like passed test, okay, as a result. If either of them is 0 or both of them is 0, it will all of these possibilities would give 0 at the input, which is a false test. Now, for the OR, what does OR mean? It means that either A and B should be true or C and B should be true. One of them, okay, should be true so as to check out as true. So if you have A and B here is 1, C and D is 1, or one of them is 1, the other is 0, in all these three cases, it would give you a true check, meaning that the engine would be, or sorry, the system failure would be considered and validated as a true failure, not as a defect within the checking system, okay, within the sensor, or like you have an interference at the data being collected from the sensor. This is the premise by which the computer would assess a system failure as a true failure, not as an error in reading the data from different sensors. Now, redundancy considerations. Modern aircraft systems employ redundancy to enhance reliability. Troubleshooting must consider the possibility of masked failures that are hidden. They are not necessarily reported on the screen. System availability is given by A equal MTBF divided by MTBF plus MTTR. MTBF means the mean time before, or I'm sorry, the mean time between failures, and MTTR is the mean time to repair. So the time between failures should be less than the mean time between failure plus the mean time to repair, so as to give the ability to the pilot to troubleshoot and maintain the problems of the aircraft. I'm talking about during the flight, okay, to troubleshoot and to fix the defects based on their capability in the air. This would be measured by this equation. In order to have an available system, this ratio should be as small as possible. BITE or built-in test equipment. Purpose and function. Built-in test equipment or BITE provides automated fault detection and isolation within the aircraft systems. So automated detection of faults and also isolating these faults while recommending potential fixes, okay, or potential solutions for the problem, okay. So the BITE functions include post or power on self tests. Actually, it is pronounced power on self tests, okay, which means the self test of the computer system during the power on. Second, continuous background monitoring in the background of different systems. Fault code generation and storage for the diagnostics, later diagnostics on the ground. So the fault would be generated and stored for like later repair and reference, and for preemptive maintenance, and also maintenance data reporting. BITE architecture. BITE systems typically consist of sensors and monitoring circuits, test signal generators, so generators that generate test signals in order to test the different faculties of the aircraft, non-volatile fault memory, which is a constant stable memory that would store permanently at times the faults that are being generated and that are being rather reported by the computer system, which are generated by the sensors, okay. Through the sensor readings, these faults are assessed as faults, and actually they would be packed as faults by the computers and generated by the computers rather, but the source is usually the readings from the sensors or the computers themselves. And these faults should be stored almost permanently within a memory on board, okay. So you have non-volatile fault memory, and the detection probability may be modeled as probability of detection is equal to 1 minus exponential of minus lambda t, where lambda is the failure rate and t is the monitoring time, okay. This is something like the law of Poisson, by the way, if I'm not mistaken. So the probability of detection is equal to 1 minus the exponential of minus lambda t, with lambda is the failure rate, and t is, or the frequency of failure, and t is the monitoring time. Limitation of BITE. While BITE improves maintenance efficiency, it may not detect, for example, intermittent faults, the faults that keep coming and going, okay, in an intermittent, like in a stuttering way, wiring degradation of the buses, for example, and environmental induced anomalies, like anomalies that are induced due to the environment, the ambient air, etc. False alarm rate is expressed as FAR, or false alarm rate, is equal to number of false reports divided by number of tests. Instrument inspection and replacement. Inspection intervals. Aircraft instruments are inspected according to flight hours. Also cycle count, which is each compression and decompression. Each time the aircraft flies and then lands, that would be one cycle. And calendar time. Inspection scheduling may be approximated by a function, okay, I being a function of HCT, where H is the flight hours, C are the number of cycles, and T is the calendar time. Calibration and accuracy. Instrument accuracy must remain within certified tolerances. Delta X is equal to X measured minus X true. Okay, so the allowable error limits ensure delta X, an absolute value, should be less than or equal to the maximum allowed number of errors, delta X max. So, in other words, delta X is the excursion or the difference or the gap between the measured value and the true value. This gap, this difference, should not exceed delta X max, which is the allowable error margin, so as to assess it or accept it as an allowed measurement premise, okay, an allowed measurement quantity on which we can rely to make a specific decision. LRUs, or line replaceable units. Most modern aircraft instruments are designed as LRUs to reduce downtime. Okay, so replacement procedures emphasize correct part number verification or correct model, ESD protection, which stands for electrostatic discharge, meaning that these instruments should be protected against any electrical discharge from a person's hand. Okay, this can be done by wearing the anti-static wrist strap, which is a strap around the wrist that is a good conductor for electricity. It would be connected to a ground bus so that while working with an instrument, any electrostatic charge within a person's hand would not go into the instrument, damaging it. Okay, it would be dissipating and discharge within the ground bus, which is very important. Okay, protecting the instruments from any type of electrical surge that can actually damage the instrument itself. And post-installation functional tests, meaning after installation we need to recheck whether the instrument is working properly or not. So by conducting a test, we can verify that the instrument reinstallation or the maintenance had passed. Its check had passed correctly. Replacement effectiveness can be expressed as ELRU is given by, okay, T saved divided by T traditional. So replacement effectiveness can be expressed as T saved divided by T traditional. This is the ELRU. By the way, T traditional is the classical maintenance time. Meanwhile, the T saved is the time saved by employing the LRU approach of replacement, which is replacing the unit itself, okay, that is defected, not the entire instrument, so to speak. Maintenance documentation and manuals. Types of maintenance manuals. You have aircraft maintenance relies on structured documentation, including AMM or Aircraft Maintenance Manual, IPC or Illustrated Parts Catalog, FIM or Fault Isolation Manual, WDM Wiring Diagram, and MEL or Minimum Equipment List. Documentation hierarchy. Maintenance actions must follow approved data precedence. AD greater than AFM, greater than AMM, greater than company procedures. These are this is the sequence of priority for actions to be taken. First document to be to qualify as a guideline for maintenance, then AFM, then AMM, etc. Record keeping and traceability. Accurate maintenance records or accurate maintenance records ensure regulatory compliance and traceability, so that in case you had a misdiagnosis, a misrectification, you can go back to the maintenance document so as to be able to assess what went wrong. The probability of undetected maintenance error decreases with documentation, so you can keep a complete tracking of the instruments and the entire situation or the entire condition of the aircraft. Okay, so probability of undetected maintenance error decreases with documentation completeness. The probability for error is proportional to the inverse of the quality detection. Okay, safety and human factors in maintenance. Human factors play a significant role in maintenance errors. Risk increases with fatigue and workload. So, the ratio of maintenance error is actually proportional to F times W, with F representing fatigue and W representing workload, or the total number of tasks that should be executed on an aircraft during maintenance. Final summary: maintenance and troubleshooting of aircraft instruments and systems require a disciplined, methodical approach supported by diagnostic tools, accurate inspections, and strict adherence to approved documentation. Effective maintenance practices directly contribute to aircraft safety, reliability, and operational efficiency. Finally, thank you so much for watching. I hope that you enjoyed this little bit long session, and see you next time.